Hello, and welcome to the Computer Vision with Embedded Machine Learning course. By the end of the course, you'll be able to make something like this, a fully functioning object detection system that runs on an embedded system. Computer vision, or the idea of having computers interpret images and videos, has been around since the 1960s. A lot of advancements in technology are possible because of computer vision. One of the most notable applications in recent years is self-driving cars, which rely on a variety of sensors to survey their surroundings. A few of these sensors often involve cameras and require complex vision models in order to detect various objects and road signs to assist the driving algorithms. Without such models, the car would not be able to figure out what's a pedestrian or another vehicle to avoid. Computer vision has plenty of uses in manufacturing too. You could use anomaly detection on images to look for things like rust or mechanical parts not moving correctly. Many robots rely on cameras and vision algorithms to figure out where to place an object, turn a screw, or weld two pieces of metal together. For example, this engineer built a robotic arm in his garage that automatically looks for the charging port on his Tesla and attaches the charging plug. He does this with a Raspberry Pi 4. Vision systems can also be used to identify different types of components that need to be sorted or picked for an assembly process. This is something we will explore in this course. Computer vision can be used for analyzing satellite images to look for things like wildfires and deforestation. My WISE camera here has a built-in person detection model that can alert me whenever it sees a person in the frame. This has a lot of potential security applications where you may not want to have someone, say, watching a screen all the time. As machine learning and computer vision technology gets better and more efficient, we can start running these algorithms on embedded systems. That allows us to create smart sensors that are capable of making decisions without needing to stream raw video data out to a more powerful computer all the time. In this course, we'll start by going over what makes up a digital image and how we can use that information as input to a neural network. We'll also give a brief overview of how neural networks operate, but I highly recommend taking my Introduction to Embedded Machine Learning course first if you have not done so already to get more information about general machine learning on embedded systems. We'll start by going over image classification, where we'll construct a simple neural network that attempts to predict the main subject of the image. Note that it won't be able to identify multiple objects in that image or tell us where they're located. We'll use Edge Impulse to create and train the model, and then I'll show you how to deploy it to the OpenMV camera as well as a Raspberry Pi. Note that in this course, I recommend having some experience with Python, as I'd like to have you do some work in Google Colab to examine and manipulate images, curate your datasets, and analyze your models. My goal is to give you enough examples and reference material so that you can successfully complete any of the projects, but knowing some Python ahead of time will definitely help. For the initial release of this course, I plan to show the Raspberry Pi 4 and OpenMV Camera H7 Plus. You can get most of the examples from this course working on either of these boards. Note that deploying a model to the Raspberry Pi requires writing code in Python, and deploying a model to the OpenMV requires writing MicroPython. The OpenMV IDE with MicroPython also supports the Arduino Portenta, which should work for most of this course. However, note that the camera on the Vision Shield only does grayscale, which will limit the capabilities of some vision models. Once we have a trained model, I'll show you how to write some MicroPython code for the OpenMV or Python code for the Raspberry Pi to use the model. You're welcome to try using other boards for this course, but I likely won't be able to help you troubleshoot any issues you might run across. I recommend using the discussion forum in this course to ask me and fellow students about the content and projects found in this course. If you run into technical issues with Edge Impulse, I highly recommend posting something to their forums at forum.edgeimpulse.com. If you ask in the discussion forum for this course, there's a good chance I'm just going to copy your message to the Edge Impulse forum anyway. You will likely get a faster answer from the Edge Impulse team if you post there for technical help using their tool. It should be possible to write C++ programs to perform inference. However, I found it a lot easier just to stick with Python so we can focus on the concepts. That being said, if I happen to find some examples or create some that are in C++ that run on something like the Arduino Nano 33 or the Arduino Portenta, I'll make sure to include them in the recommended reading sections. From there, we'll dive into convolutional neural networks to see how they work and why they make for better image classification models than regular dense neural networks. Finally, we'll look at several popular object detection models that can be used to locate and identify more than one object in an image. I'll show you how to train one such model to identify objects of your choice and then deploy it to an embedded system. Note that at this time, object detection models are still quite slow, even on something like a Raspberry Pi 4. At the initial release of this course, the object detection model only runs on single-board computers like the Pi. Once there is support for them on microcontrollers, I will update the course to hopefully show it working on something like the OpenMV camera. My goal is to give you enough tools and knowledge so you can get started creating your own embedded vision systems with machine learning. Let's get started. While I plan to cover most of the topics in this course myself, I've invited some guests to talk about their active areas of research and to showcase some projects. Computer vision and machine learning are very popular topics right now, so I think it'll be worthwhile to see what some other people are working on. Matt Kelsey is an applied machine learning research engineer at Edge Impulse. He's previously worked at Amazon and Google, and he's advised a number of startup companies when it comes to implementing machine learning. His interests include deep reinforcement learning for robotics, information extraction, and search ranking. We'll hear from him about how features from models can be reused to create self-supervised learning systems. We'll also hear from Dmitry Maslov, who is a computer vision engineer with a background in machine learning and robotics, and who works for the Seed Studio single-board computer department. He also runs the Hardware.ai YouTube channel that talks about various applications of artificial intelligence in robots. He'll give us a demonstration of his latest project that uses multi-stage inference to detect cars in a video and then identify the type of car. And this is me. I run my own freelance and consulting business where I make courses like this and help companies create technical content. I used to work at SparkFun Electronics first as an engineer designing products and then as a content creator making videos and writing blogs. I'm currently enjoying working with embedded systems and machine learning to teach these concepts as well as make fun projects like this. This is an OpenMV camera running a machine learning model that looks for a particular Lego brick. It's a bit slow, but the idea is to have something that would save you time searching through such a pile. It uses a convolutional neural network, which is something we will cover in this course. I hope that this project, along with the projects of our guest instructors, will inspire you to use embedded computer vision in your next project. Computer vision is the science and engineering of teaching computers to assign meaning to images and video. The idea of capturing an image has been around for a long time, and digital cameras have been around since the 1970s. To capture an image, we need some kind of sensor. Most modern digital cameras have a complementary metal oxide semiconductor, or CMOS, image sensor. You'll sometimes find charge-coupled device sensors, but these are usually found in older digital cameras. Light entering the camera can be bent or refracted through lenses and possibly bounced off a mirror, as in the case of my DSLR camera. Either way, as light strikes the sensor, tiny sections of the sensor respond to the amount and color of that portion of light. Each of these tiny portions, known as pixels, generate an electrical signal proportional to the amount of color and light hitting it. A computer or microcontroller reads these electrical signals and stores them as numerical values in an array. Often, you'll find 3 arrays, one for red, one for green, and one for blue. These arrays, which represent the full color photo that we just took, are saved to some non-volatile memory such as an SD card. Sometimes you'll find that these arrays are compressed in a way that saves storage space, even if it means losing some of the information in them. For example, JPEG images are compressed this way. We can then plug the SD card, or maybe it's our phone, into our computer and view the image. The computer knows how to read those stored arrays of numbers and convert their individual values into colors on our screen. This allows us to view the image we captured. The more pixels in the image, the greater the detail we can make out. This is not the only way to construct a digital image, however. A variety of sensors can be used to create a digital representation of the world around us. An image sensor in a camera works with visible light, so it's similar to how we might see with our eyes. However, we can use infrared sensors to create an array of infrared values, which is great for seeing things at night or looking at the relative temperature of objects. We can also use things like radar to get an idea of how far away things are or map out terrain. Or maybe we use something like ultrasound to get a cross-section inside our bodies. In all of these cases, we are producing digital images. While this hopefully gives you an idea of how digital images are captured and stored, simply recording something isn't computer vision. In all these cases, it requires a human to interpret the digital images. Computer vision is when we have a computer automatically interpret and assign meaning to images or parts of an image. For example, we could use computer vision to locate the trees in this photo, or maybe we automatically identify potential energy leaks in a home from a captured infrared image. Computer vision might be able to identify dangerous lava flow routes from a terrain map. Healthcare workers could rely on computer vision to automatically identify potential issues when taking X-rays, ultrasounds, or CAT scans. I'm not a doctor or ultrasound tech, so I don't actually know what I'm looking at in this particular image, but you get the idea. Most people credit Larry Roberts as being the founder of the field of computer vision. His 1963 PhD thesis, Machine Perception of Three-Dimensional Solids, proposes methods for extracting information about 3D objects from a simple two-dimensional image or photo. From here, a whole field of study was born that attempts to automate the process of extracting meaning from images. Throughout the 1970s, the British neuroscientist David Marr published a number of papers that describe how images captured by two eyes can be constructed into three-dimensional representations of scenes in the brains of living creatures. From there, researchers have worked to automate this process in computers. For example, we can use two cameras mounted a fixed distance from each other to take photos of the same scene. These photos will be ever so slightly different from each other thanks to how the cameras are separated, much like human eyes. Here is an example taken from this Arduino stereo hat for Raspberry Pi. The two grayscale images are from each of the cameras. With some math, it produces the image on the left. Greens and blues are objects that are farther away, and the orange and red blobs are images that are closer to the cameras. This is known as a depth map, and it helps us figure out where objects are in relation to the cameras without relying on distance sensors like ultrasound or LiDAR. The process of extracting three-dimensional information using a pair of cameras set at a fixed distance from each other is known as stereoscopic vision. Another common objective in computer vision is to find the boundaries between objects. This is often accomplished using edge detection algorithms which filter an image and output one or more images such as these. You can see how only the edges of the objects in the photo are shown, much like someone drawing a sketch of the scene. You can choose to pick up more or less detail in the edges depending on the particular algorithm and parameters used. Image segmentation is another popular area of study in computer vision. Various algorithms exist to help divide a picture into various parts or objects to assist in providing meaning to that image. The goal of most image segmentation algorithms is to assign a value to each pixel and group associated pixels together. These groupings can be colored and redrawn as shown in the right image to help detect or classify objects in that image. While all of these are great examples of computer vision, we haven't yet seen how machine learning fits into the picture. As I just showed, computer vision is not the same thing as machine learning. However, machine learning can be a very useful tool for computer vision, and computer vision can be a very useful tool for machine learning. Both fields are usually considered to be a part of artificial intelligence. They are different from each other, but there is some overlap. In this course, we will focus on using machine learning to accomplish computer vision goals, but there are plenty of things in computer vision that we will not cover. Specifically, we will go over image classification and object detection using neural networks. Image classification is the process of attempting to comprehend an entire image. For example, we might train a classifier to recognize the first image as that of a dog and the second image as that of a cat. It would not be able to tell you where in the image each animal was found, just that the image contained that animal. However, it would likely struggle with an image like this, which contains instances of both animals. It would make a guess based on prominent features in the image and depend on where the model looks in the image for those features. Object detection is a harder problem than image classification, but it allows us to identify things in a picture and where they are located. It also allows us to identify more than one object per image, which is a big limitation of image classification. OpenMV comes with a person detection example. Here, if the camera thinks there is a person in the frame, it will update the label in the output image to show that. This could be useful for determining if someone is at your front door, or maybe monitoring a room to automatically control the lights and air conditioning. Now, let's say you've been tasked with designing a new smart lighting, heating, ventilation, and air conditioning system for an office building. Rather than old passive infrared sensors, you've decided to deploy person detection cameras, which you found to be much more reliable at determining when someone is actually in the room. However, you need 30 of them to cover all the office spaces. You could stream all this video data to a central server on the network or across the internet. This server would be in charge of doing the vision processing to determine if a person was in each frame. Let's calculate what kind of bandwidth you might require to do that. We'll assume each camera needs a modest 240 by 240 pixel resolution to correctly identify people in a frame. We don't need color, so each frame is a grayscale image where each pixel is an 8-bit value. We'll need 30 cameras, and we'll say that each camera really only needs to take a photo once every second. This isn't a live video stream. We just want to know if someone is in the room every second to make changes to the lights and air conditioning systems. Under these conditions, we need around 13.8 megabits per second of network capacity devoted entirely to this new sensor system. Of course, there are ways to compress the images to reduce this sum, but you get the idea. While modern Wi-Fi can support at least 10 times that amount, it still seems like a big waste. Alternatively, we could move that classification problem to the cameras themselves. These smart cameras could be just like the OpenMV camera demo I showed you a moment ago. Each camera would perform whatever inference was necessary to determine if a person was in the frame and just send that result to the server. Now, we essentially need 1 bit for that value. Was a person in the frame or not? 30 bits per second is a lot less than 13.8 megabits per second. I'm making some assumptions about minimum packet length and message headers, but you get the idea. As you can see, using microcontrollers or low-power computers can save bandwidth and processing power on remote servers. This form of embedded computer vision offers an alternative to streaming raw or even compressed data to a centralized location for processing. Self-driving cars rely on a variety of sensors to help them navigate the roads and avoid collisions. Most use cameras with a combination of radar or distance sensors to help create a clear picture of objects in the distance. The car needs to use computer vision and likely some machine learning to figure out what's around it. For example, it needs to be able to read road signs and signals, watch for other cars, and avoid pedestrians. Object detection can help the car see these things and take appropriate actions, like turning on a light or stopping for pedestrians. You can't necessarily guarantee an internet connection in cars, so a lot of this has to be computed in the car's computer. While a car can transport a powerful computer, it's still somewhat of an embedded system. I hope this helps illustrate the need for using embedded machine learning to tackle some computer vision problems. Alex Fred Ohala talked about the ethics of data acquisition and machine learning algorithms in the introductory course. So let's revisit that topic and see how it applies to computer vision. Alex talked about the 3 pillars that help create trust in an artificial intelligence system. The system should follow laws, be robust against any sort of attack, and guarantee high reliability. They should also guarantee fairness by not promoting any sort of discrimination, biases, or social injustices. For example, here is a tweet that went viral in 2017 showing how a soap dispenser struggles to work with a dark-skinned individual. Bias in a soap dispenser is pretty benign, and that soap dispenser likely wasn't using machine learning anyway. However, you can see how this might be a problem for critical computer vision systems like self-driving cars. If you are designing a system to work with and for people, make sure you take everyone into account when training and testing the model, not just people who look like you. There's also the notion of privacy. Are you creating a new type of smart security camera that says records every face that walks by a corner? Let's say you then attempt to identify each person by matching their face to available photos on their social media account. Even if this is legal, you have to consider the privacy implications of this type of project. Do these people consent to having their faces and possibly names recorded whenever they walk by that corner? For more information on ethical and trustworthy AI, I highly recommend checking out the European Union's AI Alliance page. They offer some good guidance on the various factors that make up an ethical AI system. Licenses.ai has some good templates for creating end-user license agreements. These cover various ethical concerns that someone creating an AI system might have and hopefully prevent its misuse. Edge Impulse uses a similar responsible AI license that outlines how you may or may not use their tool. I definitely recommend reading through this license before getting started. I hope this has helped give you an understanding of how embedded machine learning can fit into computer vision and how you can use it to create responsible AI systems. Now I think it's time we dive into some technical stuff. Before we go over using images with machine learning, I'd like to cover some concepts about how digital images are made and stored on your computer. Some of you may be familiar with these concepts already, but I find that it provides a useful vocabulary when working with images. Let's start with a simple grayscale photo. Then let's zoom way in on a portion of this elephant's ear. Digital photos are made up of a grid of simple building blocks known as picture elements, or pixels for short. This grid of pixels can be expressed as a simple two-dimensional array of values. Let's take an even smaller subset of these pixels to examine. One way to express these pixel values is by using a number between 0 and 1, where 0 is black and 1 is white. This could be interpreted as the amount of light being given off or reflected by each pixel. White is 100% or 1. However, storing and doing math with floating point numbers like this is often difficult for computers, especially low-power devices like microcontrollers. So one way to handle that is to quantize these values to some integer values that fit nicely into bytes. For example, we can quantize those 0 to 1 percentage values to 1 byte or 8 bits. Now, 0 is black and 255 is white. However, this means that only 256 shades of gray can be represented by these values. This is known as bit depth or color depth. Each pixel or element of this array is an 8-bit number that describes the shade of gray to be displayed. Higher bit depth for these grayscale images means that more shades of gray can be displayed. Remember that we were only looking at a small piece of the whole image. The original image contains 2,290 pixel columns and 1,487 pixel rows. In other words, the image is 2,290 pixels wide and 1,487 pixels high. These dimensions are known as the resolution of the image. You will almost always see resolution expressed as width by height. You can find how much space this raw photo would take up by multiplying the width by the height by the number of bytes per pixel. If stored raw, this photo would need around 3.4 megabytes. However, most image formats need some bytes reserved for header information, so this might be higher. Additionally, many image formats like JPEG use one or more algorithms to compress the image, resulting in a smaller file size. Lossy compression, like JPEG, can lose some information in the data, resulting in a slightly imperfect picture. We won't get into compression in this course, but know that it's what allows us to store digital images in smaller files than what we calculated here. Let's examine our 5x4 segment of the elephant's ear using Python. We'll use NumPy to store our number arrays. NumPy is incredibly popular in the machine learning community as it's free and offers efficient ways to perform matrix operations. We'll also need pyplot from the matplotlib library to view our array as an image. PIL, short for Python Imaging Library, is a common Python library used to read and write to various image files. All three of these packages should come pre-installed in Colab. Remember that you can press Shift-Enter to run a cell in Colab. Next, I'll upload the image. I'll open the image in an editing program. I cropped out the tiny section from the elephant photo that we looked at earlier. I saved this test image in bitmap or BMP format with a bit depth of 8 bits. The bitmap format is not compressed, so it's useful for storing and working with raw images. If I zoom in, you can see that it really is just a 5x4 grayscale image. In Colab, I can click on the file browser and click the upload button. I then find the 5x4 bitmap image and click open. If we go up one folder, you can see that we're working with a Linux instance on a remote computer. Colab is limited to essentially Python and a few system calls, but it's very helpful for working with things like TensorFlow for machine learning. Our files will be stored in the content directory, so I save the path to the uploaded file in this image path variable. Note that you can also right-click on the file and select Copy Path. Next, I use PIL to open the image. PIL attempts to automatically scale the values in the pixels, so we need to call the convert function with the L parameter to keep them in the 8-bit grayscale format. This image object has some extraneous information as it's unique to the PIL library. However, we can call the numpy asArray function to convert it to a numpy array. All numpy arrays have a .shape attribute that we can print to see the shape of the array. Even though image resolution is given as width by height, two-dimensional numpy array shapes are given as number of rows first, followed by number of columns. This means arrays are given as height by width. So if I talk about image resolution, it will be width by height. If I talk about two-dimensional numpy arrays, it will be height first, then width. When we print the array, you can see the pixel values that we saw earlier. These go between 0 and 255. We can also normalize the array by dividing all the values by 255 to convert the pixels to that 0 to 1 scale. You normally don't want to store an image in this floating point format, but this will be helpful later when working with some neural network inputs. Finally, we can use pyplot to draw the image for us. Note that we want to draw the 8-bit grayscale image, and we need to tell IMShow to use the grayscale map for drawing, and that it should expect a minimum value of 0 and a maximum value of 255 for each pixel. For the first couple modules in this course, we will stick to grayscale images. In many computer vision applications, you will find that color is probably not necessary. However, in some cases, it is necessary as it can convey extra information about the image. Let's zoom in on a section of this sea turtle. Here we have another 5x4 section of pixels, but they're in color this time. Instead of a bit depth of 8 bits, each pixel now contains 24 bits of information. 8 bits describe the amount of red in the pixel, 8 bits are for green, and 8 bits are for blue. Now, each pixel has 3 bytes needed to describe it. You can see that the bluish pixels have more of the blue channel than the others, and the reddish ones have more of the red channel present. As with the grayscale images, we can use more bits to describe colors than what we're showing here, but you'll often run into 3 bytes per pixel for many color images. Sometimes you'll see an alpha channel present. This determines the transparency of each pixel and is common in image formats like PNG. We won't need to worry about the alpha channel for this course. The red, green, blue, or RGB color model uses additive light to describe colors. The higher the value of one of those color channels, the more light is emitted in that color. We can combine the 3 different colors to produce any other color. When all 3 are at their max, they combine to create white. Computers use this model to interpret RGB images and then light up pixels on our monitors to display images in a variety of colors. I created a Colab script to load a color image just like we did for the grayscale image. However, I'm using that 5x4 pixel sample from the edge of the turtle's shell. I use PIL to open the image, but I need to convert it to RGB format this time. Then I convert it to a NumPy array. The first 3 elements are the red, green, and blue values of the first pixel. The next 3 elements belong to the second pixel in the first row. So this group describes the 5 pixels in the first row. This continues to the last row of pixels. Here you can see that the final pixel has more red and less green and blue. We'll verify that in a minute. Now let's draw the channels separately. You could extract each plot, but Matplotlib has a habit of coloring grayscale images in an odd manner. So we're going to create 3 copies of the original array. In the first, we'll set all of the green and blue values to 0. In the second, we set all of the red and blue values to 0. Then, in the third, we set red and green to 0. Notice that I can index into the arrays as follows. A colon means give me everything from that axis. So, colon colon 0 is a 2-dimensional array containing all the values in the red channel. Colon colon 1 would be all the values in the green channel. Finally, we print the channels separately. You can see how there's more red in the bottom right and more blue in the top left. There's a bright stripe of green going diagonally from the bottom left to the top right. Now, let's print all of these channels together. I hope you can see how those channels combine to form this image. There's more blue in the top left, mostly green in the middle diagonal, and a lot of red in the bottom right. I find it easiest to think about color images as a collection of 3 different 2-dimensional arrays. When those arrays get combined, the computer is capable of producing nearly any color in the visible spectrum. As with grayscale images, there are lots of ways to compress them, but we won't get into that. Having the extra information in color channels can be useful, but I recommend seeing if grayscale will meet your needs first as it uses less data and less computing power. I hope this helps you get an idea of how images are stored on your computer. In order to create an image classifier, we first need to collect some data. There are plenty of pre-made datasets out there that include thousands of images, but I encourage you to try collecting your own. I will show you how to do this using the OpenMV camera as well as a smartphone, but you are welcome to collect digital images in any way you see fit. The goal is the same. You'll want to collect around 50 images of the same object for each class you want to identify. I recommend starting with 3 or 4 classes so you can see how to work with multiple classes. You can choose to identify anything you want, clothing, fruit, animals, and so on. There should be a large difference between the shapes of the objects as our model will be fairly simple. For example, the model might have trouble classifying breeds of dogs, but it has a good chance of working if it's trying to pick between dog and cat classes. Each photo needs to be scaled and cropped to 96 by 96 pixels. They can be color or grayscale, but we will ultimately convert everything to grayscale to make the model smaller and easier to understand. We will also resize or scale these images to make them smaller before feeding them to our neural network. Additionally, you will want them in bitmap or PNG format, as those are commonly used uncompressed formats. The object you're trying to identify should be mostly centered in the image and take up a large portion of the frame. Multiple photos should have the same object in a similar position with similar lighting and the same background every time. You'll also want to keep the camera at about the same distance from the subject each time. The background should be the same among all your classes. If you want to train a model to identify something in a variety of situations, lighting conditions, and positions, you're going to need a lot more than 50 images, probably on the order of a few thousand. You'll also likely need a more complex model, which we'll explore later, but for now, try to keep everything about the same. I collected photos of a few different electronic components, a resistor, a capacitor, a diode, and an LED. I have 50 photos of each stored in a folder named after the class. Note that I only used one component for each. I didn't try to use different sizes, shapes, or colors of LEDs, for example. Also, I highly recommend collecting some photos of just the background. This will be its own class. Many times, you'll find that you want to identify when something is in the frame or not, such as detecting a person in a room. So you'll want photos of the empty room, or of the white background with no electronic components in my case. You are welcome to use my dataset if you do not want to collect your own. Head to github.com/SeanHemel/computer vision with embedded machine learning. Click on the datasets folder and download the electronic components zip file. The BMP files are good for examining raw data, but you'll ultimately need the PNG files for uploading to Edge Impulse. Unzip it somewhere on your computer. Feel free to look through the folders. Each folder has 50 color images in them. I kept them in color in case you wanted to try working with color images, but we'll be converting them to grayscale in a future project to train the actual classifier. Note that the images are fairly similar with little variation. I tried to keep the component body close to the center of the image, and the leads point either left or right. To capture photos with the OpenMV or Portenta, head to openmv.io. Go to Downloads and download the latest OpenMV IDE. Run the installer, accepting all the defaults. If you're working with the OpenMV H7 basic model, you'll want to use a micro SD card as there's not enough internal storage to store images. Make sure it has been formatted with the FAT32 file system. Plug the SD card into the OpenMV camera and plug the board into your computer with a USB cable. If you're finding that your photos are not in focus, you can adjust the focus of the lens by unscrewing the set screw and twisting the top. This might take some experimentation to get the images to look right. In the same GitHub repo, go to the data collection folder, OpenMV, and view the raw code for imagecapture.py. Copy this code. Paste the code into a new file in the OpenMV IDE. Feel free to look through this code and see how we capture and store images to the SD card. Note that we initialize the camera with a 320 by 240 QVGA resolution, but we crop it to 96 by 96, which is what ultimately gets displayed and stored. Whenever we run this program, it will show what the camera sees in the upper right, count down from 3, then snap a photo, which it saves to the internal storage or SD card. Let's run it to collect a couple of samples. Click the Connect button. If asked, agree to update the firmware on your board. Click the Serial Terminal button to open a console connected to the board. Click the Run button. It will take a moment to initialize, so use that time to frame your object. You should see it count down from 3. When it reaches 1, it should flash black for a moment to let you know that the photo is being saved. It should print the name of the path and file to the serial terminal. If you want to take another photo, you'll have to run the program again by clicking the stop button and clicking start. Continue doing this until you get your entire sample set. Remember, try to keep the object in about the same position with the same background, same lighting, and about the same distance from the camera every time. Note that I took pictures of my electronic components on a white background with a desk lamp nearby to provide consistent lighting. You can move the camera around a little bit, but try to make sure the object is centered and in about the same orientation or position for each photo. To copy your files, you'll need to either remove the SD card and plug it into a reader on your computer or cycle power on the OpenMV board. This should cause it to enumerate as a mass storage device. Go into the drive and copy the photos. I recommend taking a group of photos of the first object, copying those photos out to a directory with that object's name, and then repeating the process for the next object. You can also capture these images with your phone or webcam. Take a bunch of photos of your objects. Note that the cameras on most modern phones have a pretty high resolution. As a result, you'll want to open each image in an editing program and crop and scale as necessary. Save them as 96 by 96 bitmap or PNG files in a folder with the class label. Finally, you can also use your Raspberry Pi. I recommend the Raspberry Pi 4 as that seems to work best with the Edge Impulse examples. I'll be using the official Pi camera as I know that works with the Pi and the examples in the rest of the course. You're welcome to try a USB webcam, but I can't guarantee it will work. Since I probably don't have your exact model of webcam, it will be really difficult for me to help troubleshoot any issues you might run into. So I recommend using the Pi camera if you can, as I won't be able to help you with webcams. You'll want to load the latest version of Raspbian onto a microSD card and plug it into your Pi. Make sure the camera is connected and plug in the USB-C connector for power. In a terminal, run sudo raspi-config. Go to Interfacing Options and select Camera. Click Yes to enable the Raspberry Pi camera interface. You might need to reboot the Pi when you're done. For this course, you'll want to make sure you are working with Python version 3.7 or newer. From the same GitHub repository we were looking at earlier, you can find two scripts for previewing the camera and capturing images. Copy the code from the preview script into a new Python document. When you run it, it will simply provide an output of what the camera sees in a preview window. The capture script will save whatever is in that preview, so make sure your objects are in focus and can be seen. If you're working with close-up objects like electronic components, you can adjust the focus by carefully twisting the lens housing with some needle nose pliers. When you're done, click on the console and press Ctrl-C to exit the preview script. If you have the preview window selected, you need to press the Q key to exit. Then enter Python PyCameraCapture.py to run the capture script. This will give you the same viewfinder and you'll have about 5 seconds to put the subject in the preview window. The script will take a photo and automatically save it as an image file. Just like with our OpenMV example, these files will be sequentially numbered. I recommend using the PNG format as it will save us a step later on. PNG is a compressed image format, but it is lossless, which means we can fully recover the uncompressed image using some math. Feel free to look through the preview and capture scripts. The capture script is similar to the one on the OpenMV, but it uses the Pi camera package. Note that this only works with the Raspberry Pi camera and not a USB webcam. The script starts the camera and displays a preview window. It then counts down from 5 and then saves the last image captured from the camera to a file. There are a bunch of pre-made image datasets out there that machine learning folks like to play with. You're welcome to try using one of them, but I find that some are very trivial, like the MNIST digits set. Others, like Fashion MNIST, don't look anything like real photos. And some have so many images with thousands of photos that it can be unwieldy to work with for this intro project. Also, many of these pre-made datasets do not contain background samples, which makes it harder to do things like object detection. In reality, if you're training an embedded machine learning model for a vision project, you're probably going to have some special use case in mind where you'll need to collect your own dataset anyway. Because of that, I recommend trying to take your own photos and construct a dataset if you can. It might take some time to collect all of these photos, so be patient with it. We're going to need them in our upcoming project. first problem we're going to tackle is image classification. It's one of the most important challenges in computer vision because it attempts to answer the question, what am I looking at? Remember that a digital image is an array of numbers. There might be 3 of these two-dimensional arrays for a color image. If we load this image as an array into NumPy, it would have a shape of 1536 by 2048 by 3. Here's the problem. As humans, our brains are wired for image recognition. We can easily tell that this is an image of a cat. If we shift all the pixels over by 1, we could still tell it's a cat. However, if we just did a strict comparison of the arrays, the computer would tell you it's a very different image. Image classification is the process of comprehending or assigning a label to an image as a whole. For example, we might want to train a model to identify the type of animal present in this photo. A well-trained model would tell us that it's a cat. We are not so worried about figuring out where the cat is in the photo, we just care that it's a photo of a cat. The most basic classifier is the binary classifier, where you only have 2 classes. This might be identifying cat versus dog. This is known as a 1 versus 1 classifier. However, if you feed an image to this classifier that's neither a cat nor a dog, the model will still predict one of those 2 classes. Alternatively, you can train a model to positively identify a cat as opposed to anything else that's not a cat, which is known as a 1 versus rest or 1 versus many classifier. Here, cats would be considered the positive case and everything else would be the negative case. Our brains are much more capable than doing simple binary classification. However, binary classifiers can still be incredibly useful in computer vision if all you need to do is, for example, identify if there's a person in the frame or if a part of an image contains something that looks like, say, a tumor. In addition to binary classifiers, we also have multi-class classifiers. Rather than saying something is either cat or not cat, we want our model to be able to determine if the image is of a cat, dog, person, dolphin, bird, empty field, and so on. This is closer to how our brains work. We are constantly identifying animals, people, and other objects. However, it turns out to be quite difficult to create a single model that does this. There are 2 basic approaches to tackling the multi-class problem. The first is to expand the 1 versus 1 technique and train a model for each possible pairing of the desired classes. For example, the first model would compare cat versus dog and give us the probabilities that it thought the input image belonged to each of those labels. Then it would compare cat versus human and give the probabilities. It would continue doing this for all cat versus other classes it had been trained for. Then it would compare dog to each of the classes to get those probabilities. It would continue doing this until every possible pairing had been analyzed. The class with the most predictions or votes would be labeled as the winner and be given as the output of the multi-class classifier. As you add more classes, you will need to train more models for this to work. The other approach is to perform as many 1 versus rest comparisons as there are classes. So you would compute the probability that the input image is a cat versus not cat. Then you'd compute the probability that the same image is a dog versus not a dog. You'd continue this for all the classes. Whichever class has the highest probability would be declared the winner and offered as the most likely label for the input image. As you can see, this requires far fewer models than the 1 versus 1 method. In fact, we would only need to train 1 classifier for each class. While neural networks and deep learning is the most popular way to accomplish this task at the moment, and it's what we'll be focusing on, please remember that it's just one possible tool of many for solving classification problems. I'd like to talk about a few other algorithms for a minute just so you are aware of what else is out there. The first is the k-nearest neighbors algorithm. Here, let's say we plot out the pixel values for all of our images. Note that for even something simple like our 5x4 pixel grayscale image, that would be a plot with 20 dimensions, which is kinda difficult for humans to visualize. So we're going to assume that our images have 2 pixels to make this visual representation easier. These are grayscale images with a bit depth of 8 bits, so each pixel can be between 0 and 255. Let's say that these are extremely low resolution photos of cats with white coats and low resolution photos of dogs with dark coats. You might expect something like this. The cat images would generally be lighter than the dog images. Each point on this chart represents a single 2-pixel image, and we've labeled our training data as such. Note that there's really no training in this algorithm. All the processing is in the inference stage. So we capture a new 2-pixel photo and we want to figure out which class it belongs to. In k-nearest neighbors, we would compare it to the closest images in the training set. With k equals 1, we find which of the training samples is closest to our unknown sample by computing the Euclidean distance to all the training samples. Let's say that we find the Euclidean distance to be the shortest to this sample, which has the ground truth label of dog. As a result, we would assign that label to our new sample and predict that it's an image of a dog. With k equals 2, we would compare the unknown sample to the 2 closest labels and assign the label based on a simple vote. However, this would be a 50-50 split, so you need to find a way to break the tie, such as by looking at whatever the closest neighbor is. Alternatively, you could stick to odd numbers for k. With k equals 3, we'd look at the 3 closest samples in this plot. Here we have 2 dog labels and 1 cat label. There are more dog labels, so we would assign dog as the label to the new sample. There are a number of problems with this algorithm, however. K nearest neighbors suffers at high dimensions, which is common when working with large images. It also isn't really examining the subject of the image, but rather looking at pixel values. Images with similar colored backgrounds might be classified the same because the pixels in the backgrounds are so close in value. Finally, inference is actually the computationally expensive part. For embedded systems, we usually want most of the effort on training and require as few resources as possible to do inference. Next is the support vector machine. This algorithm tries to find the best line or plane that linearly separates one class from another. However, its real power comes from something called the kernel trick, where we can use a mathematical transform to change the number of dimensions that these samples are plotted on. For example, we'd find a way to take these 2-dimensional points and plot them in 3-dimensional or 4-dimensional space. By raising the number of dimensions, it becomes easier to find a clear separation between the different groupings. Then, when a new sample is submitted to the model for classification, we would just see which side of the line or plane it falls on. This is on the cat side, so we'd give the image the label of cat. Support vector machines work well with high dimensions, but they lose some effectiveness when the number of training samples is less than the number of input dimensions of each sample. Remember that the number of input dimensions for images is determined by the total number of pixels times the number of color channels. For many applications, support vector machines work well, but are often outperformed by neural networks. There are other classifiers that I didn't talk about, like decision trees and linear classifiers, but let's look at neural networks. Neural networks, or artificial neural networks, were loosely modeled based on how neurons in the brain are connected. Layers consist of one or more nodes that perform a series of mathematical operations on the input data. The input to the first set of nodes would be our features. These features can be direct pixel values or something else, like a filtered image or maybe the frequency of how often a particular color occurs. You will generally see all the input data to a neural network be normalized to values between 0 and 1 or between -1 and 1. This helps ensure that all the features are on the same scale. It can help make training faster and assist in finding the optimal parameters for each node during the training process. No math is performed on these input features in the first layer. Each of these input values are copied to every node in the next layer. Any layers that are not input or output layers are considered to be hidden layers. The outputs from one layer are fed as features into the next layer. If we are doing a simple binary classifier, the final node would output the probability that the input image belonged to that class. Following our previous cat versus dog example, it might give us the probability that it thought an image belonged to the cat class. If that probability was below 0.5, we would say that the image should have the label dog. If it's above 0.5, we'd assign the label cat. Now, let's extend that to the multi-class problem. For a neural network, the number of input nodes would be equal to the number of features we want to feed the network. We could have any number of layers or nodes in the middle depending on our application. The output nodes would be equal to the number of classes we want to identify. Each output node would essentially be in charge of performing a one versus rest classification to determine the likelihood that the input image belonged to that particular class. Unfortunately, the output of each of these nodes might be scaled in such a way that we can't get a good sense of the probability of membership. We can use the softmax function as the last layer in our network to combine the outputs of the last set of nodes in order to give us a set of probabilities. It scales and normalizes the outputs as necessary such that when you sum up all the probabilities, they will equal 1. So now we can interpret the output as being a set of probabilities. For example, let's say we have a trained neural network and we feed it a new unseen image. The output might look something like this. We can say that the neural network thinks the image is 63% likely to be a dog, 26% likely to be a human, and basically negligible probability for anything else. From there, we can select the label with the highest probability or set a threshold of something like 0.5 or 0.6. If the output probability of a particular class is over that threshold, we can say that the model thinks the input image belongs to that class. While neural networks are amazingly versatile and useful, they're far from perfect, as they can easily suffer from a variety of biases and other issues. One of the biggest challenges in computer vision is lighting. If you train your model using well-lit subjects like the one on the left, then the model will likely look for similar types of images. It will struggle with poorly lit images or ones where the subject is backlit. Our eyes and brains are incredibly capable of still picking out the cats in the right two images, but many computer vision models struggle with them if similar items weren't included in the training set. This means you either need to make sure your model is trained with images that contain a variety of lighting, or you need to find a way to ensure your subject is well lit during inference. Cats have an affinity for taking on a variety of shapes. Even most human children can still tell that these are photos of cats, but a machine learning model might struggle with them if it wasn't trained to look for cats in various poses. Additionally, the cat in the middle has its eyes closed. This is a variation that might prove problematic if the neural network was trained to look for certain shapes, position, and colors of the cat's eyes. What if the cat was looking away? Will the model still recognize it? As humans, we still instantly recognize that image as a cat. We want our model to be robust enough to figure out that all of these images are of cats. Another common problem is occlusion, where something is blocking or covering up part of the subject in the image. Once again, we can easily recognize the cats in these photos, but a model may struggle if part of the cat is hidden. Something else that I've run into is that models trained on photos do not perform very well with paintings or illustrations, like the cat on the far right. They have a hard time generalizing the shape of something. This is true for even many complex neural networks. Finally, is this a picture of a cat or a dog? Most humans can see that this picture contains multiple cats and multiple dogs, but a model trained to look for one or the other in an entire image would really struggle with something like this. One way to tackle this problem might be to only look at one section of the image at a time and determine if the animal in question is present. Then slide this window over to perform inference on another section. This is known as a sliding window, which we'll examine in more detail when we talk about object detection. Just because we don't have human-level comprehension of images yet doesn't mean that image classification isn't useful. One popular use case is determining if a human is present in the frame of a security camera. Person detection can be useful for businesses and homes. Rather than having someone watch security feeds all the time, you can just send a notification with a small video clip if a person was detected. We don't even need to know exactly where in the frame the human was, just that there was one present. We can do something similar for animals too if we're, say, trying to identify wildlife. Image classification is a powerful tool, and it's a great start for trying to automatically assign meaning to pictures. I'd like to take a moment and review neural networks. These are concepts that I covered in the Intro to Embedded Machine Learning course. So if you'd like to get more details about the things that I'm talking about in this lecture, I recommend going back to that course and reviewing those lectures. In supervised learning, we start with a set of training data. Each sample consists of a set of features and an associated label. The features are given by X and the label is given by Y. Features might be a collection of pixels that form an image. A label is what's in that image, like a cat or a dog. The goal is to find some kind of function where we plug in X and it gives us the correct label. In situations where there is no easily derived function to map X to Y, as in the case of many observed phenomena or things with lots of probabilities, we can rely on machine learning to help us get close. To do that, we train a model which will act as our function. Remember that a model is usually nothing more than a series of mathematical operations performed on the input data in order to produce an output. That output is known as a prediction, and it's often given as y hat. By using a training algorithm, we can automatically adjust the parameters inside the model so that for any given x, y hat will hopefully be close to the ground truth label for that feature set. From this, we want the model to generalize the features and patterns in the data well enough so that we can give the model new data that's not in the training set, and it will still be able to assign the correct label to that set. This is known as inference. We can set aside some of our data set to be used for validation and testing to make sure that the model has generalized well enough. There are other forms of learning, such as unsupervised learning and semi-supervised learning, but we're going to stick to supervised learning in this course. A feature is an individual measurable property or characteristic of a phenomenon. For example, the X, Y, and Z measurements from an accelerometer taken at a point in time might be used as features. These would make up the features for one sample. In this case, a single sample, X, would have 3 features, and we would say that X has 3 dimensions. If we were to plot this sample as a point, we would need X, Y, and Z axes to show how this sample differs from other samples. However, this feature does not capture how an accelerometer might be moving through time. So maybe we use 1 second's worth of accelerometer data that's been sampled at 100 Hertz. With X, Y, and Z data, that would give us 300 features for one sample. To plot a single sample to compare it to other samples, we'd need a 300-dimensional plot, which is a little difficult for humans to visualize. However, 300 features is still perfectly valid as an input to a machine learning model. Just remember that if we construct a model that expects a given number of features, we should always use that number of features in our dataset. Otherwise, the model will not be able to work with the data. We can also perform some math to transform or extract certain features from the raw data. For example, we could compute the Fourier transform of the accelerometer data to see what the frequency components of that data looks like. If we're mostly interested in certain frequencies of that accelerometer, this can help the model learn what to look for much more quickly and can help reduce the amount of data that needs to be fed to the model. We don't need to be limited to just one set of features, too. We could also, say, compute the power spectral density of our measurements and use that along with the frequency data as our set of features. Just remember that the more features you send to the model, the more computationally expensive it becomes. As a result, you often want to spend some time thinking about and experimenting with different features to figure out what works best for your particular model and application. For images, we might use raw pixel values as our features. I show them here as being normalized between 0 and 1. We might need to flatten the 2-dimensional image into a 1-dimensional vector in order to feed it to the model. We would obviously use more features if we wanted to include the red, green, and blue channels for a color image. Alternatively, we could filter the image to pick out things like color blobs or edges and feed that to the model. We can even have the model automatically figure out which features to pick out in an image, which we'll see when we talk about convolutional neural networks. As you can see, as the image gets larger, the number of features per sample also gets larger. We can easily have hundreds or thousands of dimensions for a single sample when we use images as the input to our model. To start, we usually want to collect a data set. This could be downloading a set made by someone else or creating your own. For supervised learning, you will need to assign a label to every sample in that set. This might be the name of the folder each group of samples is stored in, a list of files and labels in a text file, or simply a separate array in Python that stores the labels in the same order as the samples. Then you'll usually want to randomly divide the data set into test, validation, and training sets. The test set should be put aside and not touched until you are ready to report on the results of your model. Any tweaks made to the model based on things learned from the test set could result in the model overfitting to the data set, including the test set. The validation set is often used during training to test how well the model is performing and to adjust model hyperparameters. Hyperparameters are things like the size and shape of the model, number of training iterations, and so on. The training set is used during the training process to automatically update the parameters in the model using whichever training algorithm you choose. Depending on the size of the data set, setting aside 10 to 20% of the samples for a test set, another 10 to 20% for the validation set, and leaving the rest for training is usually a good start. Let's review what's going on inside a neural network. A node, or neuron, makes up the fundamental building block of a basic neural network. A weighted sum of the inputs is first calculated. The inputs could be our features if this is a node in the top layer of the network, or it might be outputs from other nodes. Note that there is no x0 as the weighted sum includes a bias term, which is often given by b or w0. This is added to the weighted sum of the inputs. The weights and bias terms make up the parameters that will automatically be adjusted during the training process. As a result, W0, W1, and so on are usually randomized when the network is first created and then take on new values throughout the training process. The output of the weighted sum is then transformed through an activation function. The activation function acts to add some level of nonlinearity in the network. Without it, the network would simply be a collection of linear equations and would struggle with anything beyond basic classification. Some activation functions, like the hyperbolic tangent or sigmoid functions, also act to squash or constrain the output. For example, the sigmoid function ensures that the output of the node is between 0 and 1. One of the most popular activation functions is the rectified linear unit, or ReLU for short. The ReLU function is very easy to implement in code, as all you do is just convert any negative values to 0 and leave positive values alone. This makes it very efficient while still providing a good amount of nonlinearity. When we connect these nodes together, we create a neural network. This is an example of a dense neural network, where the outputs of all the nodes in one layer are used as the inputs to every node in the next layer. The input values, or features, make up the input layer. For example, if we are using the 3 values from the accelerometer as our features, we would have 3 inputs to this network. Neural networks are fairly robust and can work with all sorts of data, so long as the values are numbers. Anything between negative infinity and positive infinity can theoretically be used as an input feature to a neural network. However, you start to run into issues with training times when you mix different scales. For example, let's say you're using one-axis accelerometer data as one feature and a light sensor output as another feature to a neural network. The accelerometer might have a scale of something like -20 to 20 meters per second squared, whereas the light sensor could go from 0 to 120,000 lux. Because the features are on different scales, the training time would potentially be much longer than necessary. You also might lose some floating point number accuracy with really large ranges on some processor architectures. To alleviate these issues, you will often see the input feature values be normalized between 0 and 1, or sometimes -1 and 1. For our purposes, this might mean taking our grayscale pixel values and mapping the 0 to 255 values to be between 0 and 1. Because the pixel values have similar ranges, you might see neural networks work with raw pixel values, either normalized or non-normalized. Each of these three values would be copied to every node in the next layer. Hidden layers are any layers that are not the input values or provide the final output of the network. This particular network only has one hidden layer. If we are creating a multi-class classifier, we can replace the final activation function in the output layer with the softmax function, which combines all of the weighted sums from the nodes in a way to give us a measure of probabilities of each class. This collection of probabilities would make up our prediction, which is often represented as y-hat. During training, we would compare this y-hat output with the ground truth label assigned to the input sample. To perform training, we first initialize all the weights in each node to a random value. We then take one of the training samples and feed the features as inputs to the network. Next, we do a forward pass where we calculate the outputs of each layer to feed to the next layer. The output of the whole network will be a prediction. We compare that prediction to the known good value from that sample and calculate how different they are. The value that gives that difference is known as the loss value, and we calculate this value with the loss function. We use this loss value in the backpropagation algorithm to go backwards through the network to update each of the weights. When we update the weights in this manner, we hope that the neural network will be more accurate next time. We continue doing that for all of the samples in our training set, which is known as one epoch or epoch. You'll come across both pronunciations. The auto-generated captions struggle with the spelling sometimes, so I'll do my best to stick to epoch. After each epoch, we can run the validation set through the network using just forward passes to see how well it performs. Note that the model's weights are not updated with backpropagation during validation. We repeat the forward passes and backpropagation with the training data over and over again until the accuracy of the model reaches an acceptable or desired level. I'd like to review some terminology around the training process in case you run into it later in the course or in some of the recommended readings. Gradient descent is the most popular algorithm used to adjust the parameters in most neural networks during the backpropagation training step. It computes the gradient of the loss function given after a forward pass with a training sample and uses that information to update the parameters in the model. An epoch is when all of the training samples have been passed through the model during training. You'll often see accuracy and loss plots use epochs as the time axis. Batch gradient descent is when you pass all the training samples through a model and compute the average gradient to use for gradient descent. Stochastic gradient descent is computing the gradient and updating the parameters once each time you do a forward pass with a new training sample. Mini-batch gradient descent is a mix of batch and stochastic gradient descent. You compute the loss and average gradient for a group of training samples and use that to update the parameters. You then move on to the next group in the training set and repeat the process. You'll often want to watch for when a model is underfitting or overfitting during training. Underfitting occurs when the model performs poorly on both the training and validation datasets. It means that the model was unable to generalize the features to accurately predict the classes. To fix it, you'll want to try getting more data, working with different features, training for longer, or trying a more complex model. With a good fit, the model should have good accuracy for both the training and validation sets. What level of accuracy is good enough is dependent on your particular needs for your project or product. Overfitting happens when the model is able to predict labels for the training data well, but fails to generalize what it's learned to unseen data, which includes the validation set. Here, we expect the training accuracy to be high, but the validation or test accuracy to be low. To fix overfitting, you can gather more data, try early stopping, reducing model complexity, adding regularization terms, or inserting dropout layers, assuming you're working with a neural network. Note that sometimes you may not have the right data or right features, and you need to go back to figuring out what's the right type of data to work with as input for your model. Instead of accuracy, you might also see the loss value given over time or epochs of the training process. You should expect it to basically be the opposite of accuracy. Over time, the loss should decrease. Training and validation sets will show little decrease in loss if the model is underfit, and there will be a big separation between the training and validation loss values if the model is overfit. Finally, let's review how we might evaluate the effectiveness of a classifier. One popular way to do this is the confusion matrix. Across the top, we list the labels that the model predicts for each sample. Down the side, we list the actual classes. We usually want to compute the confusion matrix for the validation or test set. For each sample from that set that we feed to the model, we record the output. If the predicted label was bird, but the actual label was cat, we add 1 to that cell. Once we've gone through the whole set, we'll end up with something like this. The true positives are the number of predictions that match the actual class. We can compute the total model accuracy, but an examination of each class can yield some other useful metrics. For example, we might start by focusing on the metrics for just the dog class, so the number of true positives would be 199. The true negatives are when the classifier correctly predicts something other than our intended class. A false positive occurs when the predicted label is our intended class, but the actual label was something else. Finally, a false negative is when the actual label is our intended class, like dog, but the model predicted something else. Using this information, we can compute a number of metrics. For example, the total system accuracy for this dataset is calculated by summing all correctly predicted classes and dividing that by the total number of samples in the set. Note that this has nothing to do with the intended class. We sum 205, 199, 223, and 186 to get the total number of correct predictions. We can calculate the per class accuracy by adding the true positives to the true negatives and then dividing that number by the total number of samples. For example, the dog class would have a 92.7% accuracy with this model and dataset. In some instances, you'll have an imbalance among your classes. As a result, it's often better to use the F1 score for a class rather than accuracy, as it takes the false positive and false negative rates into account. To compute the F1 score for a class, you divide 2 times the number of true positives by 2 times the number of true positives added to the number of false positives and false negatives. For our example, the dog class would have an F1 score of 0.845. The closer the F1 score is to 1, the better your classifier performed on that dataset for that class. So we can compute the accuracy and the F1 score for each class to compare them. As you can see, they differ slightly. To get the total F1 score for the whole classifier, we can compute the average of the F1 scores. Again, we can compare that to the total system accuracy for that dataset. Both of these numbers can give you some insights into how well the model performs with unseen data, assuming you are using the validation or test sets. I hope this helps give you an idea of how neural networks work and how we can evaluate them. Don't worry too much about the math, as we will be using tools to do most of the complex calculations for us. Previously, we went over how a basic neural network operates, how you train one, and how you can evaluate its performance. I'm going to show you one way you might implement this using Python and Keras. If you head to the GitHub repository for this course, you can go to the Training an Image Classifier with Keras folder and find a link to this collab. I recommend working through this exercise so you can get a feeling of how dataset curation and model training works in Keras. Even better, you might want to manually copy all of the code into your own collab and play with the values to see what's going on. I want you to see how you might traditionally use this machine learning framework, and you can compare this code to the advanced mode in Edge Impulse. Personally, I like to do data curation and evaluate various features in Python before uploading my datasets to Edge Impulse to do the model training. To run the script, just click on the first code cell and then press Shift and Enter. You might get a warning from Google saying it's not authored by Google, and that's fine. Just click Run anyway. This will run one cell at a time, and you will automatically be placed into the next cell. Press Shift Enter again to run it. Note here that we need to set the dataset path, and this whole thing is basically a Linux instance. On the left side, we can click on the little folder icon, and that gives us a view into the files and folders of this file system. We can go up and you see a lot of the folders. It looks just like a Linux instance, and our files will be kept in the content directory. So click on that, right-click, and click New Folder. We want to keep our dataset in something called Dataset, and then I'm going to create a new folder in that, and I'm going to name these folders after my labels for the things that I'm trying to identify. So I'm doing electronic components, so my first one will be capacitor, then I'm going to have a diode, and then an LED, and a resistor. This may be enough for your use cases. However, I always like to have a background or noise or something that's basically not any of the things that I'm looking for. You'll find that this does not exist in many pre-made data sets, so I like to add it when I'm collecting my own data sets, because a lot of times you'll take a picture or a video of something and the items you're trying to identify are just not in that photo. So one of your classes should be background or noise or whatever it is you're looking for just is not present. I'm going to call this one background. I'm going to right-click on the folders. I'm going to click Upload. I'm going to go into wherever I keep my data set that I've collected. So for me, I have it in Python data sets, and I have them in the electronic components. So this is background. I'm going to click Control-A to highlight all of them and click Open. This will upload all of the files to the Colab instance. And I'm going to repeat this process for each of my classes. So here's capacitor. Remember that this is a Linux instance that will only run once while you're logged in. So as soon as you log out or the runtime's disconnected, you have to re-upload all of your data. That's because Google does a refresh of all of the files on the system whenever you disconnect from the runtime environment of this Jupyter notebook. And if you click down, you can actually see all of the files that got uploaded. We've got to do LED next. And then last for me is resistor. So this can be your own data set. You can use my electronic components. Feel free to experiment with different types of photos, or maybe it's MNIST, fashion MNIST, some type of pre-made data set. This should more or less work for you, but you might have to make a few changes to the settings. So now that we have our data set under the dataset directory in content, we can point our dataset path to there. We are going to resize our images. All of my images are 96 by 96 color images. We're going to scale those down to 28 by 28 pixels, and we're going to actually use them as grayscale, or we're going to convert them to grayscale instead. That just makes the machine learning model smaller and easier to work with. If you don't need large resolution to classify objects, then don't use it, because it just wastes a lot of processing power and time. Sometimes you will find that dark images or dark backgrounds work better with lighter subjects on them. This can help improve your accuracy. I'm not going to do this for now, but feel free to experiment with this. All this does is just invert the image. So white pixels become black, and vice versa. As we saw earlier, we're going to set aside 20% of this data for validation and 20% for testing. And this random seed affects the random library in Python. This way, with a particular seed, you should be able to replicate what I've done here exactly, and random will follow the same sequence of numbers that it generates. So we're going to press Shift-Enter to run that cell. Everything's been set for our settings. The next thing we want to do is load our images as NumPy arrays. I'm not going to go through this code in a lot of detail, because you shouldn't be really working with this, as we're going to be moving to Edge Impulse fairly soon, but I wanted to show you what this code would look like if you were going to use Keras in order to train a machine learning model. That way you can see what Keras looks like and then compare it to what's in the advanced settings in Edge Impulse. So this just goes through each of the folders, it finds the files in those folders, it reads them using the PIL library, and then it converts that image file into a NumPy array. It then appends that array to our collection of samples, which I call X, in this case uppercase X because it's a three-dimensional array. Eventually that will get converted to a much larger array that's a NumPy array, but right now it's just a list of NumPy arrays. In addition to this, each time one of the images is added, it also adds the label, which we get from the name of the folder that the sample is located in. So I'm going to go ahead and run this. And one thing I like to do is to always print out something from each cell to tell me that it worked properly. So here I added 50 images from the LED class, background, capacitor, resistor, diode. That looks correct because I collected 50 images of each and then uploaded those. It also lists out the labels for me so I know what my labels are, and it gives me a total number of samples. And this should just be a total of these individual classes. Next, we're going to convert the labels to numbers. Right now they're stored as strings, so there will be 50 background strings in our Y array, and then 50 capacitor strings, and so on, because all I did was tacked on the name of the folder to the array. What we're going to do is change those to numbers. So here it is, you can see it's actually out of order a little bit, so resistor came first because I can't necessarily control how the labels are read if they're going to be alphabetical order. That's all right, which is actually here when I'm listing out the directory. So this may or may not be alphabetical order when it's listed out in this for loop. So you can see the labels, the ground truth answers, or my Ys, are just strings before, and then they become labels, and it's alphabetical order. So background will be 0, capacitor will be 1, diode is 2, 3, and 4. So I need to run this cell, and you can see LED came first this time, and that is label 3. And background is 0, and so on. So now, instead of strings, they are numbers. This makes it a little easier to work with, especially in a machine learning model when we are working with numbers rather than strings. Next up, we have our collection of samples and the associated labels. We want to shuffle them because right now they're in order. It's all the LEDs, including the samples, are in the same order. And then all of the background and the capacitors and the resistors and diodes are somewhere in there. They are in this exact order, and that is a terrible order to feed to our network for training. We want to shuffle it up a bit, and we also, more importantly, we want to extract the test and validation sets, and those should be a random sampling from this larger set. The best way I have found to do that is to zip the X and the Y's together. This associates the first element in the X list is associated with the first element in the Y list, and then the second is associated with the second, so that when we shuffle them, that ordering stays the same, or that pairing stays the same. And then we unzip them again so that the pairing stays the same, but everything's all shuffled. Then we figure out where we want to slice out from that array in order to get our test set, and we take 20% off the top. We take 20% from the beginning of the array, then we take the next 20% for our validation set, and then the rest, which should be 60%, goes to our training set. And this keeps the correct Ys with the correct X's, or the correct labels with the correct samples, but it shuffles them up and extracts the test and validation data. Finally, for later on, we're going to need to know the number of training samples. That's going to help us in some future calculations, and then we print out everything that's been done. So we pull out 50 samples for our test set, 50 samples for our validation set, and then 150 samples for our training set. When I'm working with new data, I always like to view what one of the samples looks like. It gives me an idea for what I'm working with and tells me kind of what the numbers are. So up here, I've got the index. You can index into the X training set and take a view of what that raw data looks like, as well as, well, print an image because we're working with images. So you can see here I've got my capacitor, and it looks like we are working with grayscale, which is good, and the value of the pixels should be between 0 and 255. And I set that as a min and max here so that it's plotted appropriately when I'm using matplotlib. You are welcome to try adjusting this index, so we'll pick something else. Let's say, I don't know, 142. So I can run this cell again. LED, sure enough, that's an LED. and 10, diode, yep, it looks like the ground truth labels match up, and these images are still in the 96 by 96 array format. I created a function here to help me resize a list of images because we're going to call that for each of the sets. All it's doing is just calling this resize, which comes from the skimage.transform library. That allows us to just resize the images using whatever resizing algorithm that they have by default, and we're going to keep anti-aliasing on by default, but you can turn that off if you want. It just helps get rid of some of these jagged edges in the image, which is more useful when you're sizing up, but I find it useful when you're sizing down too. So we're going to use this function. We're then going to resize all of the images in the training, validation, and test set. And then I like to view the images again. So you can see here it's a much smaller image. It's still the capacitor, but it's a lot more pixelated because we've scaled it down. We can see that it's a 28 by 28 image now. It's more pixelated, but it's a lot smaller, and it should still be identifiable for what this object is. You will notice that the resize command in the resize images function that we wrote takes the 0 to 255 grayscale values and converts them into floating point values between 0 and 1. So it does that normalization process for us, which means we don't have to do it manually. So keep that in mind, because these are the numbers that we're feeding to the neural network, not 0 through 255. Next, we want to convert a list of samples into our NumPy arrays. It's going to take a list as an input and output a NumPy array as opposed to that list, because when we go to train using Keras, it's expecting a larger NumPy array that contains all of the training samples rather than a list of NumPy arrays. So I'm going to run that cell. You will see that our training set now is one large array instead of a list of arrays. It is 3 dimensions. It is 150 in the first dimension. So instead of 150 samples in the list, we now have one larger array. And the images are now just arrays stacked on top of that. So you can imagine this is one large 3-dimensional array, and the width and height, for example, would be the width and height of each image, and then the depth would be 150, so that's each of the images. And then same thing with Y. Rather than being a list of values, it's now one long array. We do the same thing for the other sets. And I can't remember if I ran this cell or not. And I did. You can always look at the number above to see if it ran, because a cell that has not been run in a new notebook will not have a number in this spot with the play button. The next thing we need to do is flatten each image to a one-dimensional vector. For our simple dense neural network demonstration here, it cannot work with two-dimensional arrays like this. So what we do is we just take the first row, and then take the second row and tack that onto the end, and then take the third row, tack that onto the end of the second row, take the next row, tack that on, and it just continues like that to squish this down into one long array. When we run this cell, you'll see that it's no longer a 3-dimensional array, but rather a 2-dimensional array, because this width and height got squished to one array. So now it's just a collection of 784 pixel values that have been normalized. Remember, these are floating point values between 0 and 1. The same thing happens to all of our training, validation, and test sets. Finally, we need to do one-hot encoding. This should be the last step before we actually get to building our model. One-hot encoding takes our numbers for our labels, which would be 0, 1, 2, 3, 4, and converts them into a series of probabilities of each class, if that even remotely begins to make sense. So in the first index, we have something that aligns with label 0. The second index is label 1, label 2, label 3, and label 4. So the number of values in this one-hot encoding lines up with the number of classes that we have. So we have 0, 1, 2, 3, 4, that's 5 classes, so we should have 5 elements in this array. And this then becomes our actual answer, or our ground truth label. So rather than having a single value, we've got a collection of values, and these correspond to the probabilities of each class. So label 1, which was our capacitor because alphabetical order, rather than being the number 1 or number 2 as being the output to the array, becomes the index for the highest probability number. And because we know that this instance of a capacitor is label 1, the second or index 1 element of this array should be probability 1. It's guaranteed to be a capacitor. And then all the other probabilities should be set to 0. So it's 0 probability that it's the background, 100% probability that it's a capacitor, 0 probability that it's a diode, 0 that it's an LED, and 0 that it's a resistor. And you can see how this works for another example. So let's take 4, which we know should be the resistor. That will be 0 probability for everything else and 100% probability that it is the resistor. These are the answers that are used to train the network. We don't expect to get 0, 1, 0, 0, 0, for example, coming out of the network during inference, because it's going to give us a list of probabilities that come from the softmax layer when we are done with inference. And you will see that when we go to perform inference on an unseen validation or test set sample. Once again, let's see if I ran this cell. I did not, so we run this cell. And I left the answers in here so you can kind of get an expectation of what to look for, but you still need to run every cell, otherwise parts of it won't work. We then construct our Keras model. This is a fairly simple model. It consists of 64 nodes of a densely connected layer. We're using the ReLU activation. I did put dropout layers in here, which we looked at in the previous course, in the introduction course, followed by another layer of 64 nodes. Same thing, ReLU activation, 25% dropout. And then the final layer consists of the same number of nodes as we have classes. So for example, this is no longer 10 nodes. In fact, this is a typo in this. This would actually be 2, 3, 4, 5 nodes, because that's the number of classes we have. And the softmax activation, where each node should output a number after going through the softmax function here that corresponds to the probability that the model believes the sample belongs to that class. That's why we have 5 nodes, 1 for each class. We then set some training settings here. The categorical cross entropy is generally used when you have more than one class, so we're not doing a binary classifier. So this would change if you do have a binary classifier. The atom optimizer is fairly common, and then we're going to record the accuracy metrics as we're training the model. We then print out a model summary, which I always like to do, and you can get an idea of the number of parameters that are in this model, which is based on the number of nodes, how those are interconnected, the input shape of your sample, and so on. The higher the parameters, the more computations you have to do. Then we train the model. This is where a lot of your hyperparameter tuning can come in, outside of course, playing with the size and shape of the network. Batch sizes adjust how fast things change. I'm just going to say 32 to start. You can also play with the number of epochs for training. Start with like 100 to 200, see how that does, and you'll be able to judge when you plot the accuracy of the validation set. Let's run this, and we wait for it to train. We don't have many training samples to work with, so this will be fairly quick. If you have a lot of training samples in your data set, this might take a little longer. When it's done, I always like to plot the training and validation loss as well as the accuracy. This just plots those for us and makes it all nice with blue and orange markers so we can see and look for overfitting and underfitting. When we plot those, we see that the model looks like it fits fairly nicely. There's a little bit of overfitting because the accuracy of the training data is a little better than the accuracy of the validation data. But it looks like it's good enough. Sitting at around 90% is kind of where it maxes out. That's not bad considering this is a densely connected neural network and we don't have a lot of training samples to work with. Then we can use Keras to predict a single label from our validation set, or feel free to do it with the test set, but you should really be using the validation set if you're still trying to tune hyperparameters and figuring out what kind of model works for your data. To do this, I'm going to pick an index into the validation set, just like we did earlier when plotting the individual images. We need to convert it to a 2-dimensional array instead of a 1-dimensional vector, because this is what Keras expects. So we actually just add a 0th dimension to a 2D array. It's really kind of odd, but then we feed that array consisting of our image data to our model. It's a parameter to model.predict. That's all we need to do to perform inference. We then find the index of the highest score. Remember how I said it's going to be printed out in an array of 5 elements corresponding to the probabilities of each label. So we just find the highest one, and then we output that prediction and print that versus the actual label, because we should know what the actual label of the validation sample is. So we run that. If you look across, here's the actual output of the model. It is 5 values corresponding to the probabilities of each class. So class 0 has a very low probability. Same with classes 2, 3, and 4. The highest probability has about 99.8%. That's how much the model believes that this sample belongs to the capacitor class. And sure enough, it is correct. The actual label is capacitor. And you can continue to do this for many of the samples or all of the samples in your validation set. Feel free to do that with some of the test set as well. And I'm just gonna, looks like we have a bunch of capacitors in a row. Here we go, background. Yes, this changes. The first element now changes to be the highest, and so on. Here's an actual miss. This is a false classification. It thinks it's a diode, but really it's a capacitor. And you can look here. So diode is 0, 1, 2. It's about 40% sure it's a diode. And it looks like it's about 16% sure that it's a capacitor. And this makes it about 35% sure it's the background. So it's struggling with this image. It really doesn't know. So you can see how it's not going to be perfect. And to explore that, we can actually print out a confusion matrix. And this just helps us print that out. It goes through all of the validation set and computes the confusion matrix. We've got the predicted labels across the top, actual labels down the bottom. You should see the largest number for each of the predicted and actual labels be in this diagonal, because that means it's predicting correctly. But it does have a few where it's not, and you can see some of these misclassifications off to the side here that are not part of, oops, that's not one, this is one, that these are not classified correctly. So that means the model is not completely accurate, but it's actually doing a pretty good job. We can use model.evaluate in Keras to get a accuracy. And I did this on the validation set. So this is another typo that I will make sure is corrected in the code. So I can run that validation loss. And then here's the accuracy. It's about 90% accurate on the validation set. And then I'm going to run this on the test set, because I would only use this up to this point to update my hyperparameters, play with the network, try to find something that's getting me better than, say, 90% accuracy. When I'm happy with that, I would then run it on the test set. As you can see, I'm using the test set here as opposed to the validation set, which should give me a little bit different number. It actually looks like it's better on the test set, about 94%. A lot of that is because I have a very small data set to work with. With larger numbers, hopefully these would be closer, but that's not necessarily always the case. You can have a model that starts to overfit to the validation set as well, so be careful with that. And I hope this gives you an idea of how you might get started using Keras. Don't worry about trying to follow everything here. I do recommend either running this or manually typing it into your own Colab instance and working through each of the cells to see what's going on. This is going to give us an idea of what's happening under the hood in Edge Impulse, especially as we get into image classification and uploading our own data sets. You can upload images directly to Edge Impulse, which we will do later, but I want to show you how to use the ingestion service so that you can automate the curation process and upload extracted features separately if needed. You can find the code for this section by heading to the GitHub repository for the course and looking in the Using Colab to Curate and Upload a Dataset folder. Click the link there to open the Jupyter Notebook in Colab. This is going to be very similar to the example we saw in a previous lecture where we uploaded our images to specific folders in Colab and then used Colab to run a script that trained a Keras model in order to identify or classify those images. However, this time, instead of creating a Keras classifier, we're going to do the same curation process, the same feature extraction to resize those images, and then instead of training that model, we're going to send them to Edge Impulse using their ingestion service. To start, we are going to need to create a dataset folder just like we did in the previous lecture. So in our file system here, right-click, make sure you're in the content folder. So we're here. I'm going to right-click and say New Folder. I'm going to call it Dataset without the capital letters. Dataset, all lowercase. Right-click on the Dataset folder. We're going to create a folder for each of our labels. So for me, that's going to be background, diode, capacitor, LED, and resistor. Here we're going to upload all of our images. So I'm going to right-click, say Upload, go to the bitmap images that I have saved from our OpenMV camera capture, or however you decided to curate those images to start to get an initial data set. So I'm going to go to Background, Control A to select all of them, click Open, and I'm going to continue doing that for all of the folders in here, so capacitor, diode, LED, and resistor. With that done, I'm going to start running the cells. So notice instead of Keras, we're going to keep the SK image transform library because we need to resize each of the images. This will handle all of the interpolation for us to make sure it's resized appropriately. I am very thankful for being able to use Python because it has access to a number of these libraries that makes things like image transformation very easy and straightforward. I'm going to run this to import all of the libraries. Notice here that I need to copy in my API and HMAC keys from Edge Impulse. So let's head to Edge Impulse, create an account if you don't already have one, and here you'll be asked to make a project or select from your existing projects. If you have existing projects, scroll down, select Create New Project. I'm going to call mine Electronic Components -DNN for Dense Neural Network. Click OK. Click X on the pop-up to close it out, and we should be at the dashboard. So in this dashboard, you're going to want to head to Keys. You're going to want to double-click on the key. Notice that it is going to actually copy the whole key, even though it looks like it's not copying the key. So copy that, head back to our Colab script, and paste that in. Notice it does paste in the whole script, and we're going to do the same thing for the HMAC key. We're going to need both of these in order to upload our samples to Edge Impulse. Most of the rest of this should look very familiar. It should point to the dataset folder that we just created in order to find all of the images that have been divided up into our labels. We have the target width and height. We're going to resize the images from 96 by 96 to 28 by 28, as smaller seems to work fine, and it saves on computational cycles for both training and inference. And we're also going to set aside 20% for test. Notice that we don't have a validation set, as Edge Impulse will automatically extract a validation set, I believe it's 20%, from the training set that we will upload. So leave out the validation set for doing this ingestion service. The other thing I want to point out, the reason we're doing this, and you don't need to use the ingestion service, however, it is available for us to use if you have your own data, say, sitting on your computer or somewhere on the internet that you want to send to Edge Impulse. So this is showing you both how to use the ingestion service, which means that some of this code will be fairly complicated. Don't feel obligated to understand all of the code at this time. It's just really to demonstrate how we can, one option, to upload data to Edge Impulse. It's actually a lot easier to send regular images in PNG or JPEG formats, for example, to Edge Impulse, which we will do in a later lecture. However, Edge Impulse doesn't really work with images in that way and flatten them for us. So if we want to work with raw data instead of images, we can do this. We can use the ingestion service to upload our own raw data that's been manipulated, curated, or we do our own feature extraction outside of Edge Impulse, and I'm just going to demonstrate that to you here. There's no need to copy my code, but if you want to see what's going on, feel free to run it, play with it, try writing your own, as the ingestion service can be extremely useful when you're working with your own data. That being said, let's continue. We will run this to do our settings. It looks like I accidentally typed an extra character here. That ran, looks good. This is divided up into a few sections, so this next part, these few cells should look very familiar from the previous lecture, where we are first going through each of the images, loading them using the pill library, and then converting that image data into a NumPy array. We are extracting the label that comes from the name of the folder in Colab. Notice that we are not going to convert that label to a number, which we had to do in the Keras example, because we're not going to be training the model directly here. This label is actually best in string format when it's uploaded to Edge Impulse, because that's going to display the strings for us, and it will handle converting those to numbers during the training process. After running this, I should get 50 images from each of my classes, because that's the number of images that I took for each label. It also has the labels in string format, which is great, 250 total images. Next, we are going to zip the samples and the labels together. We're going to shuffle them, and we're going to extract the test set, which is the first 20% of that shuffled set. The rest are going to become our training set, or will become the training set in Edge Impulse. Edge Impulse will divide that into validation and training sets for us, so we don't need to worry about doing that here. We should see that the number of test samples is 20% of everything, and the rest belong to the training samples. Let's go down to the next cell. I always like to view one of the training samples or more to get an idea of what I'm working with. For these images, it should be 0 to 255 grayscale values for each pixel, and this should be in a 96 by 96 array, depending on how you took the images, whether it was with OpenMV, your cell phone, and crop them, and feel free to try out a different index to see what those images look like. I am just going to continue down here. This is a function that is essentially a wrapper for the resize function that will resize the image that is given to it, and we're just going to go through the list of everything in one of the data sets and resize them all to that desired width and height, which is going to be 28 by 28 for us. You can see I'm passing in these parameters here, that's 28 and 28. And we're going to do this for the training set and the test set. Then I'm going to view the same image, and it should look just like the same here, but it's been resized or scaled. Instead of 96 by 96, it is now 28 by 28. Also notice that this resize function that we saw earlier, that handles mapping the 0 to 255 grayscale values to the normalized 0 to 1 floating point value. So we don't need to worry about normalizing. That has already been done for us. Then we convert that list, which is a list of arrays, into one giant NumPy array. So instead of a list of 28 by 28 NumPy arrays, we now have one giant NumPy array where each of the image arrays has basically just been stacked on top of each other. And instead of a list of 200, we now have just one array that is 200 by 28 by 28, and the same thing for the test set, but with 50 samples instead. Next, we want to go through and flatten each of the images. So instead of 28 by 28, those arrays just get completely flattened into a single 784 element array by appending one row next to each other to create one long vector instead of a two-dimensional array. With that, we get into some helper functions. Edge Impulse, the ingestion service for Edge Impulse, expects things in particular formats when we upload it using that service. One of them is JSON, which we create a wrapper for here, and you can see all of the different fields that are needed. They get filled out in this function. We will create that function, and that just fills out the fields but leaves the values empty that we fill out with the image data or whatever sample data you want. Note that when you're using this ingestion service, it doesn't have to be image data. It can be any sensor. It can be from an accelerometer, a sound sensor, a temperature sensor. The ingestion service is really agnostic to what kind of data it's being sent. We can send it floating point data, we can send it integer data, it's just numbers. You want to make sure that your samples have the same size. So if you're working with, say, two-dimensional arrays, they need to always be 28 by 28 for every sample. Or if you're working with one-dimensional vectors, if you have, say, 3-axis accelerometer data, your samples should always have 3 values in them, because that's what the model is going to expect, especially when we train it from edge impulse. You want to make sure that all of your samples have the same size and shape. Next, we have the send sample function. This handles taking that JSON data and then actually uploading it to the endpoints, which are given here, ingestion.edgeimpulse.com, API testing data. If you're using HTTPS, then you will need to create a signature that is done here, and that just gets appended to the message before it's sent out. The response value is returned from this function, so you can compare it to, say, HTTP OK to make sure that everything was received correctly by Edge Impulse. If you'd like to learn more about the Edge Impulse ingestion service, head to docs.edgeimpulse.com/reference. At the top, you should see this whole section about data ingestion. And it's really just a bunch of HTTP or HTTPS post requests that you construct and send those along to that server endpoint that was listed. So these are your endpoints, and you can do API testing or API training to split between training and test sets. They give you some example usage if you want to create your own post requests, which is essentially what we're doing, just we're doing it in Python, and an idea of how to work with HTTPS. There are a number of formats that are supported. So you can upload files directly in Edge Impulse with CSV, so comma-separated values, JPEG or PNG for images, or WAV for audio files. If you're not using that, you can still use this ingestion service to upload any arbitrary numbers you want, so long as those samples are the same size and shape. You can encode the data in CBOR or JSON, and they give you examples of the fields you need to fill out. This should look very similar to our JSON wrapper. This creates those initial fields for us, and it leaves values empty, and we just put the data right in that values field. CBOR is something similar, so you're welcome to use CBOR instead. And I believe you can also use CSV, but CSV is great if you have actual files saved as .csv files that you collected. You can examine those in a spreadsheet, and a lot of machine learning likes to use CSV to store data because it's fairly simple. So here's an example of how you might store something in CSV format to upload. But for now, we're going to stick with JSON format because it's easy enough to work with in Python. We're going to define our send sample function, and then we have our upload sample. This is a little different because it's essentially just a wrapper for send sample. We could call send sample directly. However, I'm doing everything with threads. And the reason I'm doing everything with threads is because I found that using a single thread in order to upload data takes a long time, because as you upload each data, you have to wait for send sample to return this response value before checking it. But if we say spin up 20 threads, we can run them all in while loops concurrently, and others can be running while one is waiting for this response code. To do that, we're going to spin up the 20 threads down here. Each thread runs this while loop. Before doing that, we made sure to put our sample and associated label inside of a queue. So we create a queue, we put the sample and the label in that queue, and then each thread pulls from that queue, which is just a global variable. So all the threads know about this one queue, each one pulls from it, sends that off, and they keep doing this until the queue is empty. And then once the queue is empty, the threads exit, and then we finish with this whole cell. So let's create our function, which is our threads essentially. We're going to run this cell, which is going to put the training set and associated training labels in the queue, spin up the threads, and then wait for those threads to be done. If there's any failures uploading, it should be printed to the console below us. We can actually go to the data acquisition view in Edge Impulse to watch this happen. So when I shift enter to run this thread, we can see the labels and samples coming in at a rapid pace. Since I don't have many samples, that should actually be fairly quick. And we can see that we have the labels associated correctly. So we have LED, resistor, background, capacitor, and diode. Notice that edge impulse assumes, at least for now, that anything that isn't image or audio data that's been specially labeled as such, it assumes that it's some sort of time series, which is why you're seeing 33 seconds. It thinks that, I believe there's a millisecond between each of these samples, which we can change, but it's really not necessary since this is not time series data. Things will still work for us, it's just a minor labeling difference. So don't worry about seeing the 30 seconds up here. You can click on these samples and see all the different pixel values. Remember, it's been normalized between 0 and 1. Now that that's done, we need to do the exact same thing for the test data. This is the same exact sequence that we just did where we put the test data and labels into the queue, spin up a bunch of threads, and wait for those threads to be done. We're going to run that. We're going to head over to test data, and we can see that data has already come in. If you're not familiar with multi-threading or concurrent programming, don't worry about this too much. It's not completely necessary for this course. Please just use this uploader script as a template. If you want to use the ingestion service as a starting point, you can create your own curation and uploading script if you desire. This is really just a demonstration. You're not going to be tested on this. This is just so that you have something to work with if you want to use that service. In the future, we're going to be uploading images directly to Edge Impulse because Edge Impulse has a number of tools that work much better with image data than it does with this raw data that we have here. And we will see that it's got filters, it's got other things that help us create better models. But this is just a demonstration so that you can see how Edge Impulse compares to training a model from scratch in Keras and where the similarities are and how Edge Impulse makes that training process easier for us. Feel free to look through your data. If you notice that there's an imbalance among your classes, or you messed something up and you put your training set into your test bin and vice versa, you can head to your dashboard, click out of the pop-up, and you can scroll down to Rebalance Data Set. This will attempt to rebalance the training and test set so that you have about 20% in your test set. So remember that this button is here if you mess something up where one of the samples gets put into the wrong bin. But with that, we are ready to go into training, which we will do in a future lecture. In a previous lecture, I showed you how to create a simple dense neural network in Keras and then train it as an image classifier. Now that we have uploaded raw image data to Edge Impulse, we're going to use it to train a very similar dense neural network and see how that training process compares. In Edge Impulse, you want to make sure that you have your data uploaded to the data acquisition view. You can go through and make sure that the classes are correct. You've got samples in each of the classes for training data, and if you go to test data, you've got samples in there that you can test with as well. We uploaded all of this from a Colab script, and note that we've flattened all of these images. So rather than a two-dimensional image, we've got a one-dimensional vector where each value corresponds to one of the pixels. It's just been flattened out to one vector right now. These values should be between 0 and 1 since our Colab script normalized those values for us, and you should have a total of 784 values for this vector, assuming you're working with a 28 by 28 resolution photo for each of your samples. From here, we want to go to Impulse Design, and an Impulse in Edge Impulse is our pipeline. It's incoming data. We transform it in some way during processing. This is to extract the features, and then we create a learning block, which is the actual machine learning model that we will train. I pointed out earlier in a previous lecture that Edge Impulse considers any non-two-dimensional data or data that's been labeled as something other than raw. It considers it to be a time series data. Even though we're not really working with time series here, it thinks it's time series. So we want to change where it says 1,000 milliseconds to the size of the vector. In this case, it's 784. Even though it says 784 milliseconds, it doesn't really have units. It's unitless. It's just a number of pixels. So if you go to data acquisition, you can click on this and you can see that it's 784. It thinks each one of these is a millisecond, and that's okay. We can work with that. We're going to try to trick Edge Impulse here into believing this is time series, but it won't ultimately matter because it's going to train the same type of network that we did earlier in Colab. So click to add a processing block. The only thing we're going to do here is just keep the raw data. We've already flattened it. Even though we can have Edge Impulse flatten for us, I just wanted to show you what it's like to work with raw data in Edge Impulse. So click to add raw data that basically just passes everything that is the data right to the learning block. It's not going to do any sort of processing. We want to use a Keras neural network, save the impulse, and the first thing we want to do is extract features, even though there are no real features. The one thing that the raw feature extraction block can do is it can scale for us. We want to keep the scaling the same since it's already been normalized. So just click Save Parameters. It'll bring us to Generate Features. Click Generate Features and wait while it generates all those features, which is really nothing. It's just essentially copying those raw values into some other container that's the same values. When it's done, you'll get this nice feature explorer. Even though there are more than 3 dimensions, the feature extraction process performs some transform in order to plot these on 3 dimensions and gives us an idea of the separation of classes. And they're fairly separated. You can see them in individual groups here, which means we should be able to train a classifier on them. But we might run into some issues with diodes and resistors looking similar, which makes sense. They have long component bodies with 2 leads on either side. And it looks like we might have an issue with background and one of these resistor values. In fact, that may be a bad photo that we can possibly track down later, but let's work with this for now. It looks like there is enough separation to get us a decent model. We go to the neural network classifier window, and we're going to set these to be the same as the classifier we created earlier in Colab. So let's scroll up to look for our hyperparameters. We're doing 200 epochs. Number of epochs, so that is 200. The learning rate is not something we set here, but if you look at the Keras API, you can see that with the Atom optimizer, which is what we used, you can see it set here. It has a learning rate default of 0.001, so let's set that, 0.001. The minimum confidence rating is a threshold during testing, and things can get tagged as uncertain if they don't meet that minimum confidence rating. This has really nothing to do with Keras, but it is used by Edge Impulse during testing and validation. So we can just leave this alone for right now. Edge Impulse gives us a default neural network. We want to change it to match our dense neural network that we have set here. This consists of an input layer, 2 layers, 2 hidden layers that are 64 nodes each. After each of those layers, we have a 25% dropout layer, and then it goes right into our number of classes, our output layer with the softmax function. So we are going to edit this. We're going to say 64 neurons for the first hidden layer, 64 neurons for the second layer. It already has the output layer, which has the 5 nodes, 1 for each of our classes. And we want to add some dropout layers. So let's click on Add Layer. We're going to add a dropout layer. This needs to be 0.25. We're going to drag this up to be under the first dense layer. We're going to add another dropout layer. And this is going to help with overfitting. Not that there's much to be concerned with this particular model. In fact, this model is probably overly complicated for what we're trying to do. But once again, it's just a demonstration to show that we can create something in Edge Impulse that looks like what we created in Keras. In fact, if we go to the Keras Expert mode in Edge Impulse, you can see that the code, the underlying code, is the same, more or less, as the code that we created in Keras here. It's just creating a sequential model and adding the layers, and that's what's going on right here. So let's go back to visual mode. Yes, switch. And the network looks okay, so we're going to click Start Training, and we're going to wait for that to happen. Remember that the idea of this is really just to show you how Edge Impulse is accomplishing more or less the same thing that we can do in code with Keras. But there are a few benefits to using Edge Impulse. One is this ability to collect data and visualize it and have it automatically extract features for us without needing to write that code ourselves. Training is made simpler with this graphical interface. And when we go to deploy the model to a microcontroller, it wraps everything up for us in a very nice, easy to use library that can be very difficult to create using TensorFlow instead. When the training is done, it should spit out the model for us as well as give us a performance measurement of the validation set. It's got 95% accuracy and a 0.1 loss on that validation set, which I believe is actually a little better than what we saw in our Keras code. If we look here, wherever the validation set is the lowest, so it might have gotten lucky, gotten a model that does really well on the validation set, and that loss was very low at 0.1, Edge Impulse is going to pick that model. It does early stopping. In fact, it trains for those full 200 epochs, but figures out which of the model has the best validation loss and goes with that. That's the one it delivers for us. So it already has early stopping built in. This confusion matrix looks really good. There's only a few misses that we see here. And in fact, we can go to model testing and test it on our test set. These are the samples that we set aside during curation, and we did not test them until right now. It looks like the model does very, very well in the test set. In fact, I'm very happy with this performance. 94% is really good. Now, once again, we probably could use a lot more data. Remember that there are only 50 samples per class in our total data set, and even that got divided up into test and training sets. I'm happy with this performance, and we can go ahead and deploy this, which I'll show you in another lecture. Embedded systems also consist of some devices that run Linux, like the Raspberry Pi. So I'd like to show you how to run inference on the Pi before we move on to microcontrollers. Note that what I'm going to show you requires the Raspberry Pi camera. It's possible to convert this demo to another Linux-based device or using a webcam, but it will require some effort. To start, you'll want to head to docs.edgeimpulse.com. This will take you to the documentation and getting started guides on the Edge Impulse site. Scroll down and look for Raspberry Pi 4. In here, it'll walk you through how to set everything up. I'm going to be doing everything from a remote terminal. You can do it headless. You don't need a full graphical interface to do a lot of this, but I find it very helpful when we are previewing what the camera sees. It can be helpful to have some sort of interface, some sort of graphical interface to do that. I am VNC'd in right now, so this would be what you would see on your Pi's screen. And if you scroll down on that Edge Impulse docs page, you should see a section labeled Installing Dependencies. This is what we're going to run, and you want to run one of these at a time. So I'm going to grab the first one. I make sure I have a console open, just anywhere in the home directory. Paste that in. That's going to update your Aptitude Package Manager as well as install Node.js, which we're going to need to run some of the Edge Impulse tools. Grab the next line, which is a bunch of dependencies for running these tools. And then we're going to use npm to install the Edge Impulse Linux tools. When that's done, if you haven't already done so, you'll want to run sudo raspi-config. You probably would have run this when you were setting up your Raspberry Pi to begin, to do things like connecting to a network, changing your password, and unlocking any sort of interfacing options. If you have not done this, go into interfacing options, go to camera, and when asked if you'd like to enable the camera interface, say yes. Note that you will probably have to reboot your Pi when this is done and you say finish. And also note that this is for the Raspberry Pi camera only. If you are using something like a webcam, that's going to be a different process. The reason I'm not going to show webcams is because I can't control all of the drivers and things that go into making any webcam work on Linux. I could probably verify for one, whereas I know that the Pi cam is a known good thing that will actually work for these demos. So you might be able to get a webcam working, but I'm going to show everything through the Pi cam, and I probably won't be able to help you with webcam because webcams and Linux drivers can be iffy. So I'd recommend using the Pi camera if you're working with a Raspberry Pi. The next thing we want to do is install the Python SDK for Edge Impulse tools on Linux. So if you scroll down, you'll see a link to the Linux SDK. There's one for Python, so let's click on that. And there's some instructions on installing dependencies for the Raspberry Pi. The SDK allows us to write code using Edge Impulse libraries. What we just installed was a collection of Edge Impulse tools that allow us to do things like connect to our project across the internet and download the trained model. So we actually need both in order to work on the Raspberry Pi. To start, we're going to grab this group of dependencies. We're going to copy those, and we're going to run those in our console. Say yes if you're asked to install anything. When that's done, run the pip installer for the Edge Impulse Linux SDK. Note that if pip3 does not work on your particular installation, it might be pip. So you might have to replace pip with something like python-m pip install edge impulse linux-i, and then that address, that HTTPS address earlier. That's if pip3 doesn't work, but it looks like it is working for me. Finally, I believe OpenCV does come with one of these packages, but just to be sure, I'm going to install it. So I'm going to call python-m pip install OpenCV-Python. That's already been installed on my machine. It should be similar for you. If not, that way you guarantee you get OpenCV. OpenCV is a computer vision library that has a number of languages that support it, including Python. We're going to need it to do some basic image manipulation, but it can do a whole lot more than that. Now that we have all of our dependencies installed, we can go ahead and download our trained model file and create an inference program using Python and the Edge Impulse SDK for Python. When working on a Raspberry Pi, I like to keep everything inside of a projects folder in my home directory. So if you don't have one already, you can go ahead and make your projects. It already exists for me, so I'm just going to go in there. Inside of that, I'm going to make a directory called electronic components, DNN for dense neural network. That's where I'm going to keep this particular project, and I'm going to go into that directory. From there, we're going to run the Edge Impulse Linux runner tool. This is going to allow us to download our trained model file. I recommend for this step using -- clean argument, as that allows us to reconnect to Edge Impulse to our account and pick a new project every time. Without it, you're going to be connected always to a particular project, which is great if you're trying to make this as part of a pipeline for your machine learning project or end product. But since we're just working with these one-off projects at the moment, I recommend using -- clean. And -- clean is also a way to reconnect if you somehow drop connection or you're on a different account. We're going to use -- download to tell it to download the model file associated with a particular project, and we need to give it a name. In this case, I'm going to call it modelfile.eim, and that's going to download it in the current directory. From here, it's going to ask you to sign into your account, and then it's going to ask you to pick your project. As you can tell, I have a lot of projects that I've worked with. I'm looking for electronic components DNN. That's the one where we train the model on the electronic component images. And we're using a basic dense neural network for that. If you do an ls, you should see a .eim model file stored in that local directory. Note that this model file is not just your model. It also contains the DSP code, the feature extraction, and a number of optimizations, but it should work on most Linux distributions, which makes it really good for single board computers. I'm going to show you code in another editor, so hopefully it's a little bit cleaner on your screen or monitor so that you can see what I'm entering. But don't worry, this is being saved to my Raspberry Pi. You can see it's going to projects, electronic components, DNN static features, test.py. One of the things I like to do before just throwing raw images from a camera into the model to perform inference, I like to test from known good features and compare it to how the model performed in wherever we trained it. In this case, it would be Edge Impulse. So I'm going to go into Edge Impulse. I'm going to log in. Once logged in, I'm going to go to my Electronic Components DNN project, the one that we created earlier. And I'm going to go to Model Testing. This is my test set and all the components or images of components in the test set. And I'm going to pick one, say capacitor. And this successfully classified it as a capacitor. And I can say show classification. It will perform classification on the server and give me the output. In this case, it's showing me that 0% background, 98% capacitor, and so on. This is the output of the model that I'm looking for. The probability is that it belongs to each of the classes, not just that it thinks it's a capacitor. What I care about are these numbers. And Edge Impulse gives us raw features. These are the things that are going into the model, which is what we want to copy. This should look very much like our pixel values, just normalized to be between 0 and 1. I'm going to click copy to get all of them. And we can start creating our code. At the top, I'm going to import OS time. I'm also going to import the Edge Impulse Linux runner. The Impulse runner module is what we need from the SDK. And we're going to point it to the location of our model file. Feel free to make these parameters or whatever for your own program, but to keep things simple, I'm going to do it just as global variables in this script. This name should line up with the model file that we just downloaded. And here we are going to copy in our features. So I'm just going to paste in our features. Yes, it looks really nasty. You could put this in a different file and read in the file if you want to. But once again, to keep this simple, I'm just going to make it one long variable here. Next, I like to print something to the console just to let me know that it's working. We're only going to be performing inference once, just to make sure that this input of features outputs those exact probabilities or something close to what we saw in Edge Impulse. You'll notice that the Impulse Runner module will attempt to load files from wherever this module is stored on the file system. We want it to load the modelfile.eim that is relative to this particular program. So we have to call these os.path functions in order to make that happen so that the module knows where to look when trying to find that model file. Then we want to load the model file, and to do that we just call Edge Impulse and the path to the model file, and that's going to load it in, load all the DSP code, the feature extraction, the model itself, and get that ready for inference. When working with that model, I like to put everything in a try catch or try except block. In case something fails, we can see what's going on. And to begin, we're going to print out the model information. The model, that .eim file, has information about the model, including the name and who created it, which is based on what you entered in Edge Impulse. The next thing we're going to do is time how long inference takes. And the magical inference function is right here, runner.classify, and we're going to send it features. And you notice that features is a list of numbers. It's these normalized pixel values. It should be 784 values in a flat one-dimensional list, and we're just going to take that list and send it to runner.classify. The result is what we're going to care about, but in addition to doing that, I'm also going to time how long this particular function takes. Next up, we're going to display the predictions. To do that, the result is returned as an object, and it's got a number of fields in it because it works as a dictionary. So we want the result from that object, and we want the classification from that particular entry. Those are going to become our predictions, and all I'm going to do is just loop through those. The labels are stored in the predictions themselves, so we don't need to worry about keeping a list somewhere. It's going to first print the key, and then the value of that key for each of the predictions, which should be the label and then the probability. Next up, I'm going to print out how long it took to perform that inference. And remember, it's not any of the manipulations of the data before then, it's just this function. and then we're going to print out how long the timing took according to the edge impulse model itself, because that's keeping track of time, and we can find that in the timing entry of the result object. Whether or not this try except block works, I'm not going to have an except block. In case something fails, it's just going to exit anyway. But either way, it's going to call runner.stop in order to stop that tool from running in the background. Go ahead and save this. And let me return to my Raspberry Pi. And I'm going to do an ls, and you can see there is a static features Python script that has been created, and I'm going to run that. And you can see it successfully ran. It's going to give me the probabilities of each label, including the background, capacitor, diode, LED, and resistor. You can see that capacitor is the highest at 98%. And then the next one after that is, it maybe kind of thinks it could be an LED, but at a very, very low percentage. So this is 98% and about 2%. And if we go back to our Edge Impulse project, this is the sample that we used. And sure enough, it lines up with background, capacitor, diode, LED, with LED being the one that it possibly could be. So those predictions lined up, which means that hopefully our model is working as intended as we trained it, and it's capable of taking in a known good test sample and giving us known good predictions that match up with what we saw in Edge Impulse. Now we are ready for live inference. So I'm going to clear my console so you can see that from scratch. To do live capture, we're going to need some Python libraries. And to make sure you can see the code, I'm going to change the coloring to Python. We're going to need OS, sys, and time like we've done before. We need OpenCV, which is CV2 in Python. That's the Python wrapper for OpenCV. We'll also need NumPy to help us with some of the resizing and flattening the data. We're going to need PyCamera, just as we've done for the PyCamera capture. And we're going to need the Edge Impulse Linux runner, like we did for the static inference, in order to perform inference on live images. Next, I'm going to define some settings like we did before. We've got the model file that we will import. We can choose to draw the frame rate on the screen. I'm going to set the resolution of the captured image to 96 by 96, but this is going to be rescaled to 28 by 28. Next, as we've done before, we're going to point our impulse runner to the model path. In this case, we're using the basic runner. There is an image impulse runner that you can use, but since we're going to be manipulating and resizing our images to a one-dimensional feature array, we're going to use the basic dense neural network impulse runner in this case, as it's not going to be performing any image manipulation for us. We just want to use the Edge Impulse library here to perform inference, not feature extraction. We will look at using the image impulse runner later when we have Edge Impulse perform that feature extraction for us. Keep in mind that this is still all being done locally on the Pi. We're not sending any data to the Edge Impulse servers. Next, we're going to initialize the model and print out any error codes in case something happens where it can't initialize it. I'm going to continually print the frame rate to our preview so you get an idea of how fast this is running. Then I'm going to start the camera and configure the camera with our resolution, width, and height, which should be 96 by 96. This is a pretty small preview, but it should be good enough for what we need. This will be displayed in the preview, but keep in mind that we're going to be resizing this to 28 by 28. Next up, in order to provide a continuous frame capture from the PyCamera, we're going to just create this stream. Basically, anytime we see a frame from the capture continuous function, the code in this for loop gets run. This basically turns into a while true loop, and frame is just a new frame from the camera. Next up, we're going to get a timestamp so we can compute the frame rate. That's if you choose to display it. Then we're going to get the image NumPy array from our frame. So our image at this point is a collection of numbers. In fact, we can print this to the screen to get an idea of what's contained in that NumPy array. I'm going to print the very first value, which should be an RGB value, and I'm going to print everything in there. So this should be 3 numbers that we see. To get this to work with a preview, we need to call cv2.imshow, which displays the image in a preview. We need to clear the stream after each time we display it. The preview will not work without this line. I'm going to calculate the frame rate here, which we're not going to be printing to the screen right now. These lines are just something that's needed in order to get everything else to work. And then I also need to call cv2.waitKey, and this allows me to press some key. In this case, I'm going to allow the user to press Q if they have the preview window highlighted in order to exit out of the preview. If they do press Q, then all of the windows will be destroyed and the program will exit. You can also push Control-C on the command line that's running this script in order to exit. So you have both options. Note that if you just try to click close on the preview window, it will close the preview window and a new one will open as we've not exited this for loop. Let's save this on our Pi. I have my Pi mapped to a network location. I'm going to go into Projects, My Components, Dense Neural Network, and I'm going to save it as DNN Live Inference Pi Camera. Since that was the first one I was working with, I'm going to overwrite that. Say yes, and let's look on our Pi. On my Pi, I'm going to go into my projects directory, and then I'm going to go into my electronic components DNN for the Dense Neural Network project. From there, I'm going to run the script that I just made, which is DNN Live Inference for the Pi camera. When I run that, you should see a preview window pop up, and this is the very first pixel, should be the upper left corner here, and that is showing me the values. In this case, coming directly from the Pi camera library, this pixel value is an RGB value that is 8 bits. So each of these values is red, green, blue, although in this case it might be blue, green, red, depending on the order. But if I move the camera around, you can see that it goes from 0 to 255 depending on the white value. And there is a little bit of auto gain or auto balancing that goes on here. So if I make it something completely black, it should be all zeros. Completely white is 255. And let's go to something red in that upper right corner. I've got my LED here. So it does look like it's BGR. So it's going to be blue, green, red. So if I put in something blue in this upper corner here, yeah, you can see how that first value goes up. So this is blue, green, red in that order. To get out of this, you can push Control-C on the script that's running in the console, or you can just push the Q key if you have the frame preview highlighted. And from there, let's go back to our script to add the inference part. We no longer want to print out the raw RGB or BGR values, so let's get rid of that line. And these next few lines are going to resize, reshape, recolor that image into a feature vector that the model expects. In this case, we're going to start by resizing the image to 28 by 28, which is given by these parameters that we set up top here. And by the way, feel free to change all of this to arguments if you want to turn this script into something like a tool. I'm just putting them as constants in our settings here just to save some code space, but you are welcome to turn them into arguments. I just wanted to make the script a little easier to read. In this next line, we're going to convert the image to grayscale. To do that, we call the OpenCV color RGB to gray, but we actually don't want RGB here. As we just found out, those values are BGR, and because it weights the individual colors a little differently, in order to create the grayscale image, we want to use BGR. Next, we're going to take that two-dimensional array that represents our image and convert it to a 1D vector. So those 28 rows just get stacked next to each other to create one long vector. And then we also want to divide each value by 255 to create a floating point number between 0 and 1. This becomes our feature vector that gets fed into the model. Note that edge impulse doesn't work exactly with a NumPy array. It wants to use the numbers in list format, so we have to convert them to a list in order to feed them to the edge impulse model. From there, we're going to perform inference. All we need to do is call our runner.classify and then send it the features, which is just a list containing our grayscale values in floating point format between 0 and 1. If this fails for some reason, I'm going to print out an exception so that we can see what's going on. And then I'm going to display the raw result. This will help you see what's going on so that we can extract the correct values. Let's save this and go back to our Pi. We'll run it again, and we should see a direct output from our inference. I'm going to stop this so we can read it. Let's scroll up, and you can see one of the outputs here. This is very much like a JSON format or a Python dictionary that allows us to index into it using these keys. For example, we can just call result in order to get this key, and then classification to get the set of keys here, and then we can call our label to get the value of that label. In this case, since our camera was looking at the background, I expect to see the background confidence score or the probability be close to 1, which is what we saw here. This is all you would need to get started if you just want these numbers to make whatever you need to do with your embedded system. However, for the purposes of testing, let's print these results. Let's find the highest label and print that along with its confidence score to the preview, much like we do for the frame rate. So from here, I'm going to head back to our code. You'll notice up top that I set the results to none in case this inference fails, and results will still be none when it comes down here. So to deal with that, I need to make sure that the results are not none in order to continue. Ideally, nothing should be printed here. You should just see a blank output. But if inference fails, you should also see an error printed to the screen. Next, I'm going to go through all of the predictions found in the results. And remember that we can index into these. So I need to index into result, and then from that value, index into classification. That should give me a list of the predictions, which includes all of my labels and their predicted probability values. I'm going to loop through all of those and then find the max label and max value. Next, I'm going to draw the predicted label on the bottom of the preview. I need to pass it in the image that I'm going to draw. The max label that we just found here. 0 is x of 0. And then the resolution height -20, which means I'm going to leave space for the probability value to be printed. And in this case, for put text, the y value here is the bottom left point on the text. But you can probably just play around with these numbers to figure out where the text gets drawn on the screen or in that window. Then I'm going to draw the predicted class's confidence score. In this case, it's the probability since we put it through a softmax function. I'm going to round it to 2 decimal places. In this case, instead of -20, I'm going to use -2 pixels from the bottom of that preview window, which should give me enough space for this Hershey plain text that we're using from OpenCV. Note that in both of these cases, I'm drawing the text in white, which is given by this 255, 255, 255 value. And that should be good enough to give me my predicted classes and its confidence score. In addition to doing this, I always want to draw the frame rate on the screen, assuming we have draw FPS set to true, which we do up in my settings here. And this should put the frames per second or frame rate at the top of the screen. So we should see both the frame rate, how fast inference is being performed, along with how fast we can capture the images and convert them to a feature set. Let's save this and run it on the Pi. Note that what I'm going to show you requires the Raspberry Pi camera. It's possible to convert this demo to another Linux-based device or using a webcam, but it will require some effort. To do this next test, I'm going to hold the Pi camera above my electronic components on a white sheet of paper, which should match how I captured the training set. Note that lighting can matter, so I have a desk lamp shining light onto the components. When we run this again, you should see the preview window show up. In addition to the frames per second, you should see the highest predicted label shown at the bottom, along with its prediction score. And this is ideally the probability of that class versus the others. So now I'm going to move the camera around. And the white background should auto gain balance to something more grayish, so you can hopefully continue to read those values. And if you notice here, I've got a diode. I'm going to bring it close to my diode, and it should predict it. However, it does confuse it with a resistor, but if I hold it in the exact right spot, it thinks it's a diode. And if I move it around, it confuses it with the background or another resistor, which means the dense neural network is giving a lot of weight to certain pixel values. Probably something in the center, as you see when I move the diode off-center. It thinks it's background, and at certain distances or certain positions, it confuses it with a resistor or even a capacitor. The other thing to note here is if you have bad lighting, sometimes that can affect things. I have a lamp shining on my components here, so you can see I turn the lamp on and off. However, the auto gain of the Pi camera does adjust, and it still allows it to mostly work. I'm going to leave this light on. I'm going to move it to my next component, which is my LED. You can see here it does a good job of seeing that it's an LED. However, if I turn it off axis, it confuses it with a capacitor. Or if I move too far away. So your components need to have a particular lighting, they need to be a certain distance from the camera, and a certain orientation in the frame. This is very hard to control for with the data set and the neural network that we're using in this example. Here is a resistor. I need to move my page around a little bit. And in fact, my network struggles a bit with the resistor. It thinks it's a capacitor in a lot of cases, and it really confuses it for a diode, depending on how I have it positioned. It really struggles with this. I can't even find a good position for it to detect it. And then if we move to capacitor, it has no problem detecting the capacitor. I think it's because it's such a unique shape that the pixel values in certain areas mean certain things that the neural network picks up on. But it struggles with this resistor. It confuses resistors and diodes just because the leads are coming out on either side. There we go. It thinks the diode is a resistor when it's over to the left side. And when this is over to the left side, it struggles. It still really struggles. And this might be an issue with I need to focus my camera a little better. But I can probably find a very particular position where the resistor is in the frame and it thinks it's a resistor. As I mentioned, it's looking for very particular pixel values in certain spots, so it's not really good at detecting overall shapes. It's really bad at generalizing beyond our training set, even if we use something like data augmentation, which makes dense neural networks not a great fit for doing image classification on live data, as you can see by this example I'm showing here. In the next section, we'll get into creating better models for image recognition. Before we jump into more complex computer vision topics and neural networks, I'd like to take a moment and review what we covered in this module. We first looked at how digital images were made using an array of picture elements, or pixels. Most grayscale images are made up of an array of 8-bit values, where each value is a number between 0 and 255, denoting the amount of white or brightness in that pixel. We can normalize these values to be between 0 and 1 in order to express the brightness as a percentage of the amount of white. These pixels are combined to create a grayscale image like the one shown here. We express the resolution of the image as width by height in number of pixels. We also introduced the concept of bit depth, which gives the number of bits used to describe each pixel. We can use a collection of 3 arrays to create a color image, where each array is a color channel, one for red, one for green, and one for blue. When combined, we can create nearly every visible color. You will often find these color channels as having a bit depth of 8 bits each, which means a color image would have a bit depth of 24 bits. We then introduced the concept of image classification and how a machine learning model can be trained to recognize what an image is showing on the whole. This can be a binary classifier where it tries to identify between 2 different images or determine one class versus everything else. We also have multi-class classification, where a model attempts to pick the correct label for an image from more than 2 options. While there are many machine learning algorithms and models out there, we will focus on using neural networks to perform image classification and object detection in this course. We can do basic image classification with a neural network by flattening an image to a one-dimensional vector and feeding those values as inputs to the first set of nodes in the network. We then talked briefly about how a neural network works and how we can train one. A single node in a neural network consists of a weighted sum of inputs followed by some nonlinear activation function that transforms the single numerical output. Training consists of feeding a sample from the training set through the network to get a predicted value. We then compare the predicted output to the known good output value of the training sample and use the backpropagation algorithm to automatically update the weights in each of the nodes. We continue this process with all of the training samples until the network is correctly predicting labels to an acceptable level. We can look at the accuracy of the model as it trains over time to see how well it's performing and if there's underfitting or overfitting. If there's underfitting, it means the model is not generalizing well, and we often need to get more training data, try different features, or adjust the complexity of the model. If it's overfitting, we can try early stopping, gathering more data, reduce the model complexity, or try some techniques like regularization or dropout layers to reduce overfitting. In addition to accuracy, we can look at the loss of the training and validation sets as the model trains. These plots should look something like the inverse of the accuracy. Where accuracy should increase over time as the model learns, we expect the loss to fall, as loss is a measure of how different the predicted values were from the ground truth values. A confusion matrix can help us visualize how well a model performs by comparing the predicted labels to the actual labels. We can compute per-class accuracies to help give us an idea of where a model might be struggling and where to focus our efforts. Additionally, we can use the measurements of true positives, true negatives, false positives, and false negatives to calculate a number of metrics like the F1 score, which can give us greater insights into how the model is performing. We saw what a code-based training effort might look like using Keras in Google Colab. Here, we resized a group of images and flattened them to a one-dimensional vector. We trained a simple, dense neural network which gave us about 90% accuracy at predicting images of our electronic components. We then uploaded the same feature set, a collection of one-dimensional vectors, to Edge Impulse to see how to use that tool to accomplish the same task. Finally, we deployed the trained model to two systems. The first was a Raspberry Pi where we could perform live inference on images captured with the Pi camera. The next system was the OpenMV camera where we used MicroPython running on a microcontroller to capture images and perform the same inference. Output was a set of probabilities and a predicted class. We saw how a dense neural network was limited in its ability to predict classes from live data, as the objects had to have similar lighting, framing, distance, and focus as the training set. The network is looking for combinations of pixels to be certain values in order to make its predictions. In the next module, we're going to introduce the concepts of convolution and filters in order to have a model look for things like patterns, edges, and shapes. The idea is that this will allow us to create a more robust model for image classification. One of the frustrating things about a convolutional neural network is that it can be difficult to figure out what's going on when the model classifies a given image. I'm going to show you a couple of techniques that you can use to get a sense of why a model made a particular decision. We'll start with our simple convolutional neural network that's been trained to recognize images of electronic components. For both of these methods, we need to remove the softmax layer at the very end. That's because the methods require the raw output values from the final layer of the dense neural network to compute the necessary heat maps. The first method is known as a saliency map. Here we compute the loss between the raw output of the network and the ground truth label values of a particular input image. The saliency map algorithm works its way backward through the network to figure out which pixels in the original image were the most important or salient in helping the model make the classification. These maps can look a little noisy, but it can be very instructive to see where the network was looking in the image. The second method is a class activation map. Here, we figure out which features from the final convolution layer were the most important in helping the network make its classification. Specifically, we'll use the grad-cam algorithm, which is short for Gradient Weighted Class Activation Map. Note that the resolution of the heat map will likely be different than that of the input image. That's because it's a feature map that results from one or more convolution or pooling steps. In fact, its resolution should match the output resolution of a single filter from the final convolution layer. In this case, we would expect a 14 by 14 pixel heat map from our particular model. I'm not going to go into the math behind either of these algorithms, as it includes a good amount of calculus to compute gradients. In fact, I don't even have a great understanding of how each of these algorithms work, but they can still be useful tools for debugging a convolutional neural network. What you can do is start looking at the saliency maps and cam images for your test or validation sets. Here, I've created overlays for both maps that appear on top of the original image. This will help you get a sense of where the model is looking to make its classification. This resistor worked fairly well, although the spots in the corners of the saliency maps tell me that it's looking at the background sum to make a prediction. Next is a known good LED image whose label was predicted correctly. The saliency map shows that it was looking mostly at the corner and some of the edges of the LED. The cam image is really interesting. The feature map around the edges seemed to be the most important. Finally, here's an example of a misclassified LED. As you can see, the leads of the component are cropped out of the shot. Both maps again show the model focusing on the edges of the component. However, the cam heat map is closer to that of the resistor, where there are some curved edges near the center of the frame with a light bar at the bottom indicating some level of importance. What I also found interesting is that the model does not seem to care about the leads of either part at all. It focuses mostly on the component body to make its decision. Let's say you're trying to make a classifier that identifies dogs in an open field. Your training set looks like a collection of dogs on the left and a bunch of open fields like the ones on the right. Let's say you have a ton of training data and your model performs wonderfully on the validation and test sets. However, when you go to deploy the model, you find it performs terribly in the field. Why is that? In reality, your model is probably not detecting dogs, but rather it's looking for light backgrounds versus dark backgrounds. A saliency map or cam can help you spot that. If the heat maps mostly focus on the background rather than your subject, you can determine that your model is looking for something else that differentiates your images rather than what you were intending. Let's take a look at how we can use our model from Edge Impulse to view saliency and class activation maps. We'll start with the trained model in Edge Impulse. From here, we'll need to download the trained model in order to use it in our demo code. So head to your dashboard, click out of the pop-up. You'll want the TensorFlow saved model file, as that includes a save point that we can load into Keras to use for classification and computing the gradients necessary for each of the maps. So let's download that file. It's going to be a .zip file. If you go into the GitHub repo for the course, there should be a section for the convolutional neural network visualizations. And if you go in there, there will be a Colab Jupyter notebook. If you click on Open in Colab, the page might freeze. So what I like to do is click on it and say Open Link in New Tab. This will bring you to Colab with the notebook. This will give you some information about the notebook, and let's run it one cell at a time. If you get the warning about the notebook not being authored by Google, click Run Anyway. After that first cell runs with our imports, we're going to want to point to our saved model.zip file. To do that, we'll want to click on the File Explorer, right-click in the area and click Upload. In Downloads, go to wherever you downloaded the .zip file, click it and say Open. Click OK, and that will appear in the Files area. You'll want to right-click on it and click Copy Path, and this is what you want to paste for your zip path. This will unzip the file, and if we refresh the File Explorer, you should see the saved model folder appear here. And this is a collection of files that make up your model, including a save point and some other files that are used by Keras to create your model. From here, we want to specify an input image. Go to your Edge Impulse project, and there are a couple of places that we can get image data from. First of all, if you click on the Image tab, you will see the screen. We don't want the raw features, as this is the information for the 96 by 96 color image. What we want is the processed features, as this has been scaled down to 28 by 28, which we specified in the Impulse design, and converted to grayscale, as well as normalized to being between 0 and 1. This is what we want. So we can copy this to the clipboard, and we can go back into our Colab. I've got an example image here. I just want to delete this, paste in my features, and then I want to change the true index to whichever index match my labels here. Note that you're going to probably need to update these labels in order to match whatever labels you have for your project. Remember that Edge Impulse keeps these in alphabetical order. If we look at this, this is a resistor, which means the true label should be resistor. For me, that is 0, 1, 2, 3, 4. I'm going to change that to 4. And I have a note here to say that this is a resistor. And saved model should point to whatever got unzipped here. You probably don't need to change that. Note that if you go to model testing, click classify all if they have not been classified, and you can see what the model predicted for each of the test set samples. In fact, instead of using this known good resistor here that was part of the training set, let's use one of the test samples. And this is up to you on what you want to look at. You can look at validation, you can look at test, you can look at training. I'm going to take a peek at this resistor that the model thought was a capacitor. So I click on the little options menu here, say show classification, give it a moment, and it will pop up with the image and the output of the classification, which it was very sure that this was a capacitor. We don't want raw features, we want the processed features. So let's click those, and we're going to paste them into the image data here. Make sure we close off the list. Make sure we close off the list with a bracket. This is still a resistor. So 4 corresponds to the index of resistor here. We're going to run that cell. The next cell will load the model and give you some information about the model. So feel free to look at it here. It should match the model in your Edge Impulse project, which is noted here. Then we need to reshape the image, as what was given was just a list of features. Note that you will probably need to change the width and the height variables here to match whatever was set in the Impulse design page here. So 28 by 28 is your width and your height. You want to set them here, 28 by 28, and that's what determines how the image gets resized. So instead of being one long list, it's now a 28 by 28 array. We ran this. This is what our image looks like. The Keras model that we're going to be using in our algorithms expects a bunch of these together and color channels. So we need to actually put this in a 4-dimensional array, but if you notice, it's still just a 28 by 28 image that has a dimension of 1 for the color channels and then a dimension of 1 for the number of samples, since it's only one sample. That's all we're working with right now. We'll run that. We also want to do a forward pass of the model with this input image. That should give us the predictions, which should match our test sample. If we go here, we go to our resistor that looks like a capacitor. We show classification. And it should look something like this. TensorFlow takes a moment to start up the first time you run it, so be patient with it. And sure enough, we round that up to 1, and that looks about right. It really thinks that this is a capacitor. As I mentioned earlier in the slides, we need to remove that softmax activation function that's in the last layer of the densely connected neural network. That's part of our convolutional neural network. And to do that, we just call model, go to the very last layer, which is given by this -1 index, and we change the activation to none. That removes that softmax for us. First up, we're going to show the saliency map. This relies on the back-end TensorFlow library to compute gradients for us. And we're going to use the gradients of the loss with respect to the input image in order to generate that heat map. This becomes our function, which we can just call here, where we give it images, which is really just our one image given here. Our model file, the only thing that's changed about that is changing the activation layer, and then the actual class of the image, which we got from the test set. This should be 4, which corresponds to resistor. That's used to compute the loss between the predicted value and the actual value during this gradient function up here. We'll run that. We then show the saliency map, which gives you an idea of where the network was looking at the individual pixel level on the input image. And then we can overlay that image with our original image. So we have this on top of the resistor, and you can see it's looking at the top edges here. It's not looking at the component body. In fact, it's completely ignoring the bottom side and ignoring the leads, it seems, except for maybe this area over here. And it's also looking a little bit at the background, which is interesting. My thought process here is that the network is actually looking for values to be not background somewhere in the center. Because this resistor is high up, it thinks this is a capacitor because that's where it's expecting the capacitor component body to be, since it takes up more space on this image. Once again, that's a hypothesis that I would need to test and maybe get additional training data in order to feed the network more images like this, where the resistor is not centered all of the time, to teach the network that, hey, a resistor can be up here. You need to look at other features in order to determine that this is a resistor and not a capacitor. Let's look at GradCam. Once again, we're using the back-end TensorFlow library to compute the gradients. This time, the gradient is the output neuron, or the output node, with respect to the output feature map of the last convolution layer, which is what we saw in the slides. We're looking at the feature map of that final convolution layer before it goes to that final max pooling layer and before it gets flattened to go to the densely connected neural network. We use that to produce our heat map. And in order to call this function, we need to tell it where that final convolution layer is. So what I'm going to do is print out all of the layers in my network, and I'm going to go backwards through them to find where the final convolution layer is. The name of that should be conv2d_1. It prints that out, and sure enough, that's the name of the final convolution layer. If you have 3 or 4, it should still point to that last convolution layer that's in the network. We then call the function with the name of our last convolution layer. That creates our heat map, and then we can draw that. As you can see, it's focusing once again on the resistor in the upper part of the image, and let's overlay that with our original image. This gives you a slightly different look at how the model is operating and where it's focusing its attention. With both the saliency and class activation maps, you can see that the model is focusing on the upper part where the component body is. However, you would want to compare this with something like a capacitor to see if the model is indeed focusing on that upper part for capacitors. This gives you some insights to how the model is working and can help you debug potential errors, especially for your test set images or your validation set images where the model failed to predict the correct class. In a future lecture, I'm going to go over data augmentation, where we can use this relatively small training, validation, and test sets to create or automatically generate new samples that can be fed into the model to hopefully correct some of these issues. Hopefully these heat maps generated by the saliency and GradCam functions can give you an idea of what you need to do during that data augmentation. So for example, if I wanted to be able to classify resistors in the upper part of the image, perhaps some of that augmentation would be, let's create more images out of the ones that already exist where the resistor is in the upper part or lower part. So we can start to move things around in data augmentation based on information we've learned from these mappings. One way to deal with an inaccurate model or one that's overfitting is to give it more training data. If you can't or don't want to collect more data manually, then you can use something known as data augmentation, where you automatically generate slightly modified versions of your original images to create a new data set. I'm going to show you some very simple image transformations you can do in order to augment your data, and this is running a collab that you can find in the course GitHub repository. To begin, make sure you've connected to the runtime, and then I'm going to upload a single sample, and I'm going to continue to use this first resistor sample that we collected. Once that's uploaded, what we can do is set the path to the image, so 0.bmp, and you're welcome to keep the seed as the same or change the seed. That's so you can get the same exact results that I get, assuming you're using the same input. And hopefully that works for most of the random calls that you'll find in this collab. So we'll run this. Then we're going to load our image as a NumPy array, which you saw way back when we were doing data collection. Now that our image is a collection of numbers in an array format, we can use that to get the height and the width of the image. Then we're going to view the image. I always like to do this just to make sure I know what kind of data I'm working with. As you can see, it's a 96 by 96 and there's 3 color channels. And I'm going to keep these images as color images. And then when we upload them again to Edge Impulse, I'll use Edge Impulse to convert it to a grayscale image. This is in case you want to work with this data set as color images instead of just grayscale. You can see that the individual color channels are still 8-bit values going from 0 to 255. And here's an output of that image. It should be exactly the same as our bitmap image. And you can double click these and sometimes it'll show you an image preview over here, but it looks like in this case it doesn't work with bitmap, so it just tries to download it. One of the simplest transforms you can do is a simple flip. And here we're going to flip the image horizontally, we're going to flip the image vertically, and then we're going to flip the image horizontally and vertically. What this does is not only does it move your subject around a little bit, but it also accounts for any variations in light that the classifier might be picking up on. For example, resistors might be shinier than some of the other components, so that the neural network is looking for this little reflection in the resistor at this particular point in the image. Or it's looking for a highlight or a shadow. And by flipping it, especially vertically, all those things are now in different spots. So it tells the classifier that, hey, you need to learn different things about this object than maybe where a reflection point is. Hopefully this will help kick it into gear in order to pick up on the shape of our subject rather than other features that we don't care about, like background or reflection points. Flipping horizontally can have this effect too, especially if it's looking for things like, oh, the gold band is always on the right because I forgot to flip the resistor when I was taking images myself. And instead it goes ahead and flips it so now the gold band is on the left, telling the classifier that it shouldn't always look for one of these bands and that it should try to pick up on something else. And same thing with some of the other color bands. I really should be using resistors with varying degree of color bands because there's a good chance that these color bands are being picked up by the classifier. But moving on from there, the next thing we can do is rotation. This takes the image and rotates it. Here I'm doing a 45, 90, and 135 degree rotation, but you can really work with anything. You could do, I don't know, 15 degrees, and that affects it in a different way. Note here that I'm using mode edge. This tells the transformation function, in this case rotate, whenever it rotates the image to fill in any blank spots with whatever pixel values it finds along the edge. So another way to look at this is if we change that to constant, it's going to fill it in with a constant value, in this case black or 0. And as you can see, the image is rotated, but these black bars may not be useful. In fact, they may be detrimental if you're not working with a dark background, like I am here where I've got this white background. It's going to tell the classifier to look at these dark backgrounds, or it might tell the classifier to look at these dark backgrounds. So if you've got a dark background, great. If you've got edges that can be extrapolated out and create something that looks like a decent image, then going with edge here is something that I completely recommend. As you can see, it tries to fill it in with either the background or the leads of this resistor, which is totally fine. I'm okay with it doing that. And then same thing here. The image actually ends about here, but it goes ahead and copies the pixel values from that edge outwards. And it ends up looking like leads on a resistor, which is exactly what I want. So this may or may not work for you, but it works great for these electronic components. Then we have scaling and randomly cropping. You might also see this referred to as random zooms. What we're going to do is actually increase the size of this picture. So instead of 96 by 96, it becomes 120 by 120 or 240 by 240, however big you want to make it. So this image is now bigger, and we're going to crop a section of that resized image to create something like a window that might look at this part of the resistor or this part. And it has the effect of moving your camera around or maybe a little closer to the resistor. In fact, you can see it even looks blurry here, which replicates the idea of moving my camera around so that the resistor is not always completely centered. This is a great way to make it look like the subject's not always in the center of your frame without having to take a bunch of extra pictures doing that. You can zoom out, there are transforms for that, but because you don't know what pixel values are outside the edges here, you're gonna have to guess. So you can either make them all one color, like black or a dark color, or you can use that edge extrapolation where it just kind of copies the pixels out. And for something like this, the leads look like they would just extend out, which is fine, and the resistor gets a little bit smaller. That's another way to do it, but the scaling and cropping works pretty well. Next, we have translation. This is where your object is just moved to a different part. We're not zooming in, we're not changing the size, it just moves it around. And this helps the classifier figure out the shape of the object rather than looking for it in a particular position. This is another great way to train a more robust classifier where your subjects are not necessarily dead center. And I actually do a random translation with this code where this resistor might be up here or it might be over here, up to about 1/4 of the way over. That way I'm not cropping too much of my subject out of the frame. And I'm actually doing this using the random.random function, not necessarily setting, I'm going to put the subject in this corner, this corner, this corner, this corner. That is another way to do it, but rather just kind of take a random smattering, because if you have more than one original images, you should end up with a good amount of random translations throughout your entire data set. Finally, the last one I want to talk about is adding noise. There are a number of different types of noise you will find in images. If you're working in darker environments, or if you've got your ISO or gain setting cranked very high on your camera, you're going to have something that looks like this center image, where it's very noisy. Noise is amplified in order to capture it, which is something that you'll run into often, especially with low light photography. But you can also run into it in any instances if you've got, say, a bad camera or a cheap camera. Introducing some noise is a fantastic way to emulate that, especially if you're trying to train a data set that was captured from a different camera that may not have that noise. This is part of the reason I always recommend capturing your training, validation, and test data sets from the same sensor that you're planning to use in deployment. This type of noise shown in the center here is known as Gaussian noise. It's what you'll commonly find added to images when you increase the gain. So this is a good one to use. Another type of noise you might come across is known as salt and pepper noise. This is evidenced by this image on the right here. Salt and pepper noise is different from Gaussian noise. It sometimes results from bad or poor analog to digital conversion when you're capturing an image. It shows up more often in black and white photos from what I've seen, but it's still something that you can have, and because it's different than Gaussian noise, it might be worthwhile adding into your training set just to give your model something else to look at where it tries to learn the shapes of things rather than trying to pick out individual pixel values, which who knows exactly what value they will be with a bunch of noise like this, and the noise will be different from image to image. Even with just the simple demo I showed you, that is 12 new images from just that one original image. If we include the original image, that means we can increase our data set by 13-fold. However, this is only a brief sampling of some possible augmentations. I didn't even include stacking the transformations, like flipping, cropping, and adding noise to create one image. You could exponentially increase the size of your data set if you start creating 4 rotated images for every flipped image. There is a whole field of study around data augmentation, and it gets into more advanced transforms that we didn't cover here, such as zooming along one dimension and playing with the color balance and contrast. I recommend starting with some simple transforms at first to see what works and what doesn't. This might mean training multiple models and comparing their validation or test results with one another. I uploaded my augmented data set to a new project in Edge Impulse. If we go into data acquisition, you can see that here I've got over 2,500 items in the training set and 655 items in the test set. And you can see the number of items in each of these. This is a lot more than my original set, which was just 50 of each class. Now I've got over 500 in each class, and most of that is being used to train my new classifier. If we take a look at the impulse, I'll first go into the feature extraction area. You can see that this is the augmented data. Here's one with noise. And I've converted them all to grayscale, 28 by 28 resolution, just like the original training that I did. So the model should be the same. It's expecting the exact same input data, and it's actually going to be the same architecture. I left it as the default edge impulse convolutional neural network with 2 convolutional layers, then a flattened dropout, and then our 5 nodes for the classifier. I trained this using 100 training cycles, and you can see that it's actually a lot more accurate than before, and that's because I'm working with a lot more data and more variability in the data so that the model can learn the features that I'm trying to teach it, and not things like looking at the background or if there's just 2 leads, things that were in the original photos but might not be fully represented in different camera angles, lighting conditions, or even if you're moving the object around in the frame. As you can see here, the model still struggles a little bit with the diode and the resistor and the LED and the capacitor, but it's a lot better than what it used to be. If I go to model testing, I've classified all of my test data, and you can see there are some misses here and there, but it's still maintaining about 97% accuracy, which gives me much more confidence that this model is going to work better when I go to deploy it. Something else you can do is look back at our saliency and class activation maps to see what the model's looking at this time. It struggled with capacitors and LEDs before, or trying to determine the difference between resistors and diodes. It looked like it was trying to examine the backgrounds for some LEDs. In fact, let's take a look at this LED that was misclassified, and we can probably determine what was going on. First of all, you see that it got shifted, so it's missing this round cap, which makes me believe that this image might be shifted a little too much during data augmentation, which is okay. I'm happy to have some things that aren't classified properly because it helps us figure out what the model is looking at. I'm going to copy these features, and we know that this is an LED. I'm going to go into my Colab script here and start running it. The other thing I need to do is download my saved model, which I'll do here. I'm going to upload the model. And since I've already downloaded this before, I need to rename it because these parentheses do not work well in Colab from what I've determined. So there's the name of my model. I'm going to copy the path, paste it here. That should unzip the model for me. And then I need to get the processed features because I accidentally removed everything on my clipboard. I'm going to put them here. And this was an LED, 0, 1, 2, 3. LED is correct. And I'm going to run through these so we can take a look at what the saliency map looks like as well as the class activation map. If we look at the saliency map, we can see that it's focusing on the pixels in this bottom part here, which might be LED, might be resistor. We're not quite sure, but it is missing this round part of the LED. Interestingly enough, the classifier is looking in the center here, and I can see why it might think that's a resistor because it kind of creates this oblong shape right in the center, and it's missing that cap or any other edges. So that would make sense why this got misclassified. That being said, it's a lot better than trying to look up top and down below for the background, which it still might do, but this is a good start and you get an idea of what's going on with the model. Data augmentation does not always work, but it can be useful if your images are fairly similar, and especially if you're working in a controlled environment where the background doesn't change much, like what we've got here with the different components on the white background. Your best bet is to always collect more data that represents your target use case, but failing that, data augmentation can be quite powerful to help you train more robust models. When it comes to training complex machine learning models, there is a slick trick we can use called transfer learning. With this, we reuse a part of a model that's been previously trained on a different but similar data set. Let's look at our very simple convolutional neural network as an example. Let's say we fully train this model to identify electronic components. The feature extraction portion of this model, which consists of all the convolution and pooling layers, has been trained to recognize certain shapes and patterns that make up those electronic components. This includes basic shapes that are large in the frame based on the training data. Now, let's say we wanted to train this same model to recognize something else, like nuts, bolts, and screws. We could retrain all of the filters and weights. For a small model like this, retraining everything would not take a long time. However, when we start to look at much larger and more complex models, fully training all of the weights might take hours or even days. So it makes sense to reuse parts of the model where we can. To reuse a model, known as transfer learning, we would freeze whichever layers we want to keep. For things like image classification, we often want to freeze the convolution and pooling layers, as we assume that they have been trained well enough on images that are somewhat close in structure to our new dataset. Freezing means that when we run the training process next time, the parameters in the frozen layers are not allowed to change. Next, we remove the layers that were not frozen and replace them with whatever we want. This might be a totally new flattened layer with different fully connected nodes. You can even add more than one fully connected layer or other layers if you desire. Note that our outputs change too, as we might want to recognize a different number of classes. We then run the training process again on this model using our new dataset, which consists of nuts, bolts, and screws. This time, the convolution and pooling layer parameters are not updated. Only the new layers are updated. We are essentially saying that we're happy with the features that the first part of the model has extracted for a given problem, and we're going to use that for our new, but similar problem. The dense neural network classifier is the only thing that gets updated at this point. When training is done, you might see a second training process occur called fine-tuning. Here, we first unfreeze any layers. We then run the training process again with a very low training rate, which means parameters are not allowed to change very much. This causes all the parameters to adjust slightly as necessary to pick up any minor variations in the features from the original training set. At this point, we hope that the model is capable of correctly identifying screws, nuts, and bolts instead of electronic components, and we'd want to test its accuracy on a validation or test set. Note that we have to use a dataset that has similar features to our original dataset. I would not expect this model to work well identifying cats versus dogs, as the feature extraction portion has been trained to look for very simple shapes in electronic components rather than complex features like eyes, ears, nose, and so on. There are two main reasons why you'd want to do transfer learning. The first is that it saves you a lot of time. Some of the more complex models out there can take hours or days to train from scratch. Using transfer learning can get this time down to a few minutes. Next is that we can work with smaller training data sets. Because we assume that the feature extraction portion of the model has been trained on a similar data set that's close enough to our problem, we only need to train the classifier portion. As a result, we can often get away with a few dozen training samples rather than a few thousand per class. Before we move on to discussing MobileNet, I'd like to make a quick note about model diagrams. I will try to draw my model layers going from top to bottom, with the input at the top and the outputs at the bottom. This is to mimic how you might see the model described in Keras or in the Netron app. However, in many machine learning articles and papers, you might come across the reverse, with the input at the bottom and the output at the top. An article might refer to replacing the top layers during transfer learning, for example. In this case, they're referring to the dense layers that make up the classifier portion of the network, which happen to appear at the top of this particular diagram. You'd have to look at any provided diagrams or infer from context whether the author is thinking about the network model being top to bottom or bottom to top. You might also see left to right sometimes, which just adds to the confusion. The models all work the same mathematically though. I generally try to stick to top to bottom for any content that I create. Over the years, researchers have put together collections of pre-made datasets for people to use with machine learning. These are popular with competitions or for using as the basis for purpose-built models. Classifying images is such a big problem in the machine learning world that there are many such datasets for images. One of the most popular datasets is CIFAR, and there are two versions, one with 10 classes of objects and another with 100 classes of objects. The images are all the same size and have all been labeled, which makes it perfect for training a model. Another large collection is the ImageNet dataset, which contains over 14 million images, and these images have all been labeled with one of 1,000 classes. An interesting feature of ImageNet is that the labels are part of a hierarchy. This can help you train a model that recognizes just a dog as a label or a specific breed of dog. COCO, which stands for Common Objects in Context, is another image dataset with over 300,000 images and 1.5 million objects that have been labeled in those images. Which pixels make up the objects are also noted in the ground truth information. This is useful for training a segmentation model. We'll talk about object detection and image segmentation in the next module. Along with collections of datasets, researchers in industry and academia have created families of machine learning models designed to tackle specific problems. As image classification is one particular problem that's in very high demand, there are a number of models that have been developed specifically for image classification. Because ImageNet has such a large number of classes and a huge number of samples, it provides a great benchmark to test the accuracy and efficiency of these models. This particular paper compares the accuracy and computational requirements for many of the top neural networks. ResNet and VGG are two very popular models. You can see that they have decent accuracy. Some of the more accurate models also require many more operations. Since we are working with embedded systems with limited resources, we want to use a model that is closer to the left side of the graph, as these should be less computationally expensive. We will be looking at MobileNet v2 as it was specifically developed for embedded and smartphone applications. While it might not be the most accurate model for image classification out there, it is very efficient while still performing decently well on such classification tasks. Here is what a version of MobileNet v2 trained on the ImageNet dataset looks like. As you can see, it's quite a bit more complicated than the basic convolutional neural network we were looking at earlier. It's designed to work with larger images, color as well as grayscale, with many more complex features and many more classes. There are some layers in here that we did not specifically cover, but this is still essentially a collection of convolution and pooling operations. This depth-wise convolution operation performs convolution on the 32-dimensional feature maps that come from the previous convolution operation, but then it leaves the third dimension alone, creating a new stack of 32 convolved feature maps. The output from some of the layers are added to the output of future layers in what's known as a residual block. These skips resemble how the pyramidal cells in our brains work. They also help fight a problem in training known as vanishing gradient, where the parameters stop updating due to a very small gradient being calculated during backpropagation. MobileNet v2 also contains a number of bottlenecks, where the number of neurons or convolution filters in a layer is fewer than the layer above it. For example, the output of one layer might be fewer two-dimensional feature maps than the layer before it. Then you'll see the number of maps get larger again. These advanced techniques help the model learn complex features of images. At the end of the feature extraction section, you'll see that we're left with a bunch of 7x7 feature maps. A global average pooling operation is applied to each of these feature maps to create our flattened array, where each element is an average of the feature map values. From here, we can perform our classification using a densely connected neural network to make a prediction of the label of the input image. When working with transfer learning, we often want to start with a pre-trained network like this one. All of the weights for the convolution filters have already been set by training this model on a known good dataset like ImageNet. Here is a version of MobileNet v2 that I used for transfer learning in Edge Impulse. What's interesting is that we can change the input to MobileNet somewhat. Instead of a 224 by 224 color image as input, I modified this one to accept 48 by 48 grayscale images. the convolution layers still work the same, as they're not really dependent on having a particular size and shape for their input. The only thing we have to be concerned with is that at the end of the feature extraction chain, after the convolution layers reduce the dimensions of the feature maps, individual output feature maps are not smaller than 1 by 1 pixels. This means that for most applications of MobileNet v2, the smallest input shape is 32 by 32 pixels from a grayscale image. Edge Impulse removed the average pooling layer for this particular model and added 2 fully connected or dense layers for classification. This is the section that gets trained during transfer learning. However, all of the parameters get tweaked a little bit during the fine-tuning stage. I used this model to identify when my dog was present in the frame or if it was just an image of my empty office. That's why there's only 2 outputs. However, you can use MobileNet and transfer learning to create a model that can predict any number of classes, of course within reason and the capabilities of MobileNet and your processor. Keras, as well as Edge Impulse, comes with a collection of pre-trained MobileNet v1 and v2 models. Note that common pre-trained MobileNet v2 models were trained on ImageNet or Cocoa images with specific resolutions, like 96 by 96 or 224 by 224 pixels. That means if you don't use one of those resolutions for your input, you might lose some accuracy, as that's what the parameters were trained on. Something else that you can adjust is this alpha hyperparameter. This controls the number of filters in each layer. A larger alpha value means more computations and a more complex model. This could mean more accuracy, or it might mean more overfitting, so you should try a few values of alpha to see what works best, or start off with the lowest alpha to see if that works well enough for your problem. Here is the original paper that proposed MobileNet v2. In it, you can find a chart that gives you an idea of its accuracy on the ImageNet dataset compared to other models. As you can see, version 2 generally works better than version 1. You can increase the resolution of the input image, which can help with accuracy. However, it often means more computations are required. Once again, for embedded work, you'll want to find the most efficient model capable of performing your task with your desired accuracy. Transfer learning, which reuses parts of a previously trained neural network, is an incredibly powerful technique. It allows us to quickly create models that meet our needs and with less training data. Now that we've seen how transfer learning works in theory, let's put it into practice using Edge Impulse. We'll be using MobileNet v2 that's been pre-trained on the Cocoa image dataset and then tweak it for our project. To start, you'll want to collect a new dataset. You're welcome to use the old dataset that we were using in the first part of the course, but I recommend trying something new here. One of the advantages of transfer learning with a complicated model like MobileNet is that we can do things like have complex backgrounds and have our shape or object or objects that we want to detect within those complex backgrounds. And by that I mean a variety of background shots. Here is a bunch of shots from my office, just at different angles, different positions, places where I would predict I might find my dog. And you should do something similar. I'm going to be creating a dog detector. Specifically, whenever my dog is spotted in the frame, I'm going to get notified from my OpenMV, my Arduino, whatever it is, my embedded system that I'm training this model for. And I have a bunch of different photos of my office from a various number of angles, zoom levels, and whatnot. It's all around this backpack, as you can see, because that's where I'm going to hopefully see my dog, and it's kind of gray. I also got a number of photos of my dog in various positions, and I'm using the OpenMV to capture these, but feel free to use whichever device you'd like. These are all done with a 96 by 96 resolution and color, but we're going to ultimately convert these to probably something like 48 by 48 and grayscale. And as you can see, I just have my dog in a variety of positions here. Hopefully I can create something that spots the dog, and you need about 50 samples per class. And I only have 2 classes here, background and dog, but you're welcome to do a multi-class classifier. I know that in the Edge Impulse documentation, they show you how to do something similar that is background, plant, and lamp, and you can identify one of those 3. So it can be binary, it can be multi-class. Just make sure you have about 50 samples of each, and as you can see, I don't need a perfectly white background as we're using a fairly complex model here. Once I'm done with that, you'll notice that these are in bitmap format. To work with Edge Impulse, whatever format you were using, I recommend converting them to PNG, and I've got them here. They're all nicely labeled. Here's the ones with my dog, once again, 96 by 96 resolution, and here are the ones with the background in just a variety of positions here. As you can see, I got a few more here than just my backpack. It's all around my office. And from here, we can go to Edge Impulse. Once in Edge Impulse, sign into your account and create a new project just like we've done before. I'm going to call mine Dog Detector. Once at your dashboard, click out of the pop-up. We don't need anything from here. We can go right to data acquisition and upload your samples that you collected. Remember that you need PNG files. I'm going to go to wherever I keep my data set, PNG version of my dog detection data set. I'm going to start with background. I'm going to select all of them, click open. I'll let it automatically split between training and testing, and I'm going to enter the label of background. I'm going to do the same thing again for my next class, which is dog. Change the label to dog and upload again. And you'll want to do this for all of the classes that you have, and it could be 2, it could be 1, whatever it is. Once it's done, I recommend clicking on data acquisition and making sure you have your 2 classes with 50 items between the training data and the test data. Once you're happy with that, go to Impulse Design. You can stick with 96 by 96, but I found that for some of the lower end embedded systems, 96 by 96 is a little big. So this didn't even work well with my OpenMV H7, the non-plus version, but it would probably work with the plus version. So to make things work, I recommend going 48 by 48. And remember, 96 by 96 is a common format that MobileNet was trained for, so I might lose a little bit of accuracy by downscaling or resizing the image to something that's smaller, but hopefully it will still work for our purposes. Just, I recommend working with something that is the lowest resolution possible that gives you the accuracy that is good enough for what you need, because then it means you can work with lower resources on your embedded system. Next, we're going to add a processing block. We're going to stick with image, and then we're going to add a learning block. Instead of using a regular neural network this time, we're going to use transfer learning, and this allows us to use or start with a pre-trained network. Click Save Impulse, and then go to Image, where we're going to do more or less feature extraction for our images. In this case, we're going to start with the color images. We're going to go to grayscale, and they're going to be converted to 48 by 48. They're going to be resized from 96 by 96 to 48 by 48, and that will be the input images for our training. So click Save Parameters, and then click Generate Features. Once that's done, you should see the Feature Explorer appear, and you can take a look at where your classes are. Remember that this is just a very simplified visualization of your images because there are more than 3 dimensions in your image. There are hundreds or thousands of dimensions, and these just get reduced to something that you can kind of get an idea of certain aspects of the image. And it looks like it's going to be fairly separable here, which means that we should be able to train a decent model. Also, don't forget, because we're working with 48 by 48 images, you will need to supply the model a 48 by 48 grayscale image during inference, whenever you go to deploy that to your embedded system. Let's go to transfer learning. I'm going to bump this up to 50 cycles. I find that 20 is a little low sometimes because I like to just train things for longer and see what we get. The learning rate is fine. I'm going to choose to not do basic data augmentation at this time. And it looks like it starts us with MobileNet v2.35, and 0.35 here is that alpha parameter, which just determines the number of parameters or the number of filters in that feature extraction portion of MobileNet, which means that we can potentially get a better model that can identify more complex features with more of those filters, but it means more resources and we run the risk of overfitting. You can click on the first button to edit the number of neurons in that final dense layer to help with your classifier once it's done with the feature extraction that gets added on and trained separately as part of the transfer learning process. There's also a dropout layer that you can affect. 0.1 seems to be fine, or you could delete the whole model. I'm going to choose to use a different model here. In fact, I'm going to look for MobileNet v2, which generally works better than MobileNet v1, and I'm going to pick one, honestly, with the lowest alpha rate here, simply because I'm working with such a simple data set and I want to use as few resources as possible for RAM and ROM, which are shown here for each of the potential models. As you can see, as you start going up in image resolution, this is the resolution that the input expects, but it can be changed. The minimum is 32 by 32 pixels. We're going to use 48 by 48 because the parameters that resulted from training this model on ImageNet were set for this resolution, so expect a slight drop in accuracy. As you go up in the resolution as well as the alpha, you're going to start using more resources. In fact, here's one that uses over a megabyte of RAM, so keep that in mind when choosing a model and what kind of embedded system you're working with. Even the smallest model that we have uses a good amount of RAM and flash memory, so pay attention because MobileNet still requires a fairly beefy processor with lots of resources and usually a fast clock speed in order to work. So I'm going to choose this one with 0.05 alpha. I'm going to click Add, that appears here, and I'm going to click Start Training. This is going to show the training output on the top right, and we just wait for a while until this is done. You'll see that it queues up on their server, and it's going to train the model. Whenever it says training model, that means it's training the classifier portion that's after the feature extraction that we saw when we were looking at MobileNet v2. So those parameters are going to stay the same because they were trained on ImageNet, which is that large database of images, and we're just training that classifier portion to work with our project here, dog versus background. Next, it's going to fine-tune, which means that it unlocks or unfreezes all of the parameters, sets a very low learning rate, and just tweaks them a little bit. It's not going to take very many epochs in order to do this. When it's done, you should take a look at the accuracy and validation accuracy. Hopefully these are over something like 90%, which is really, really good for something like this. And as you can see, this trained very quickly in comparison to our fully training model, even though this is a much more complicated neural network. When it's done, it's going to show you the validation set performance. 88.9% is not bad. It looks like it struggles some with a few background and dog images on the validation set. You can see those in red dots here where it misclassified those. But this is not a bad starting spot. In fact, I would be happy to deploy this knowing that some frames may be misclassified, and I can go back and look to see which images might do that. In order to do that, we can go to testing and use the model to perform inference with our test set that we set aside at the beginning. Let's classify all of those and see what happens. When it's done, you can see that we have an accuracy of 92.3, and the only thing that it missed is that one of the dog images, it considered it to be uncertain. It didn't even misclassify it, just didn't meet the threshold. So we can look at that to see where it was misclassified, or try to figure out what was going on here. When you load it, it looks like my dog was looking away. There's no identifying features of eyes or mouth that are clearly in the frame. So I can see why this might have struggled. In fact, it still thought it was a dog, but it just didn't meet that threshold and it counted it as uncertain. I believe it needs to have a 0.6 threshold in order to count it as I know that this is a dog. So it struggled a bit. This makes total sense. So I believe the model needs to have the dog looking at the camera, or at least a solid profile picture of the eyes, ears, snout, in order for the feature extraction portion to pick up on those features, because that's what it was trained for when it was trained with ImageNet. And I'm okay with this being misclassified for my particular deployment. The other thing you can do is try playing with some of the hyperparameters that you can find in the learning section. So some of the options here where you can pick the number of neurons and you can adjust the dropout rate, that may help, or you might have to try a different model, maybe a different resolution for your particular project to get an accuracy that you are happy with. When you are done, head to deployment, and you have a number of options to work with. You can do a strict C++ library to work on any number of systems, assuming you have some way to compile C++ files. The other thing you can try is an Arduino library. There are a few Arduino boards powerful enough to support MobileNet. The Portenta is one of those, but if you're working with the Portenta or the OpenMV camera, I recommend using the OpenMV because it's much easier to work in MicroPython. But if you need C, C++, you want that absolute efficiency and execution speed, then try the Arduino or the C, C++ library. Finally, there's also a way to deploy it to Linux boards if you want to get this working on a single board computer. Once you've selected the library or output that you'd like, click Build. It's going to create the library, and it will download it for you. From there, you can deploy it to your system of choice and give it a shot. I copied the trained.tf lite and labels.txt file to the SD card of my OpenMV camera so that those would load into this program. I also changed the frame from 96 by 96 to 48 by 48 because I have no good way to easily resize images captured in the frame over here, and that's just something that is with OpenMV. There are Python libraries, or you can write your own way to resize images as you capture them, but capturing a pure 48 by 48 image seems to work well enough. I'm also capturing in grayscale this time so that the image is ready to be fed directly to my model. Much of this should look very similar to the original densely connected neural network that we did earlier if you were using the OpenMV cam. Once we have the image, we can feed it and the model file to this tf.classify function that classifies the image for us and gives us the prediction back as a collection of objects. We look at the first one since we're only doing a single classification. We're not trying to do several classifications or object detection yet. With those predictions, we can print out the probabilities in our serial terminal. I'm only doing that once every few inferences, so you're missing a few when things are being printed to the console, and that's okay. However, I am drawing the label and the probability of that label to the background image in OpenMV so we can take a look at what's going on. When I point this around the room, you can kind of see that it works pretty well. It's looking at my crazy rug here. There is dog, and it identifies my dog as dog. And it looks like it identifies dog even without the face, but it struggles a little bit. My guess is if it has a face, if it has the face in the frame, it definitely knows that it's my dog. However, if it's just the body or part of the coat, then it struggles a bit, probably because it's looking at various patterns like the black stripes on the light background. If I move around my office some more, you can see some boxes and back to dog. And if we come back to this area where there are some cables hanging down, you can see it actually misclassifies those as dog, which is part of what makes me believe that it can identify the backside of my dog. Because those stripes on the back are dark against a lighter background, I did not have these cables hanging down as part of the training set, so it doesn't know that these should not be classified as dogs. That's something I can learn by testing in a live environment. I should capture these, put those in my training set so that it does not misclassify them as my dog. But I could set up my dog recognition machine here to automatically open a door or give Pippin here some water or food or whatnot. Pippin. Pippin. Who's my good boy? That is dog. So in addition to dog, you can also make a person classification machine to identify if people are at your door, say if they're ringing your doorbell or about to, maybe set up something to prevent somebody stealing a package, or if somebody's in your home and you need to know, or you want to turn on lights or turn on a fan or the air conditioner. This is another way to do a detection to see if somebody is in an area. I hope this helps you see how you can use transfer learning to train a model that's been trained on other objects in order to very quickly produce something for an embedded system. I know that we covered a lot in this module. Let's take a moment to review what we've learned. First, we talked about how image convolution works. This is accomplished by sliding a window across the image with a given stride and performing an element-wise weighted sum of all the values underneath the window. This produces a single output in a new array that constitutes a feature map. Here is the general form of convolution, assuming we're using a stride of 1. Without any sort of padding of the input array and using a kernel larger than 1 by 1, we'll end up with an output array that's smaller than the input array. We could also pad the input array or image with zeros or copy the values at the edges to make the input bigger. Usually, we would want to add enough padding so that the output array is the same size as the input array. This is known as same padding. No padding is known as valid padding. Convolution is an incredibly important method that allows us to filter an image in a variety of manners as shown. We can blur, sharpen, or create interesting effects like this embossed image. We can also use convolution to detect edges in the image, which forms the basis for how many computer vision techniques detect objects, including convolutional neural networks. Another important function you will see is pooling, and there are two common types, average and max. In average pooling, a window slides over the whole image, and the pixel values under that window are averaged together. This helps to reduce the dimensions of an image or feature map. The stride in a pooling operation is almost always the same as the width and height of the window. In this example, the window is 2 by 2 and the stride is also 2. Max pooling is similar, but instead of averaging the values under the window, the maximum value is chosen instead. This helps to reduce the dimensions of an image while highlighting the most salient features. While both pooling methods have their uses, max pooling is more common after convolution as it helps to pick out the most important features. We then saw how these operations fit together to create a convolutional neural network. A series of convolution and pooling operations can be stacked together to create a feature extraction section. The weights in the convolution filters become the parameters in this stage, which get automatically updated during training. This helps the model learn the most important features in images in the training set, which are fed to the classifier section. Note that each convolution layer may have more than one filter. For example, if that first two-dimensional convolution layer has 16 filters, then 16 feature maps will be generated that are passed on to the next max pooling layer. Once the image has been filtered and pooled one or more times, the feature maps are rolled out or flattened to create a one-dimensional array or vector that is sent to a simple, fully connected or dense neural network. This network acts as the classifier in order to predict the label of the input feature set. When trained, this model will ideally figure out which features are the most important in any given image and use those features as calculated by convolution and pooling to classify the original input image. Next, we saw how we could modify a trained convolutional neural network to produce a series of visualizations to help us see what's going on. In both cases, we need to remove the softmax activation of the last layer as the math requires the raw output of the neural network. We first looked at saliency maps. In these, the pixels that are determined to have the biggest effect on the decision-making process are highlighted. The second was a gradient-weighted class activation map, where the features from the final convolution step are shown and the elements that had the biggest effect on the decision-making process in the neural network are highlighted. We can use the information in these maps to help us figure out how a convolutional neural network is making decisions. Specifically, it tells us where the network was looking in each input image or feature map to make its decision. Knowing that the model is looking at a particular area is a great way to identify potential biases or problem areas worth exploring. One way to fight model biases is to use data augmentation. Here, we can perform a number of image transforms on a single training image to produce dozens or hundreds of copies of that one image. For example, with 12 simple transformations, we can multiply our training set by 13, going from 250 images to 3,250 images. If a model was looking at a certain area of the image for a particular background or glint of light, this process can help tremendously by moving or flipping the object in question. In other words, it keeps the model on its toes when training. Finally, we looked at transfer learning, where we can take a pre-trained model, freeze some of the parameters, and train a new classifier. This can help us reuse a model that's been trained on a similar set of data. For example, we looked at MobileNet v2 that was trained on the popular ImageNet dataset that contains millions of images categorized into 1,000 classes. We freeze the feature extraction set of parameters, remove the classifier section, and add our own that corresponds to the specific problem we want to solve, such as making a dog or person detector. We then train using the whole model, but only allowing the parameters in the final few layers to update. A final fine-tuning step can be performed where we unfreeze all of the layers and run a few training epochs to allow all of the parameters to update a tiny amount. This allows any parameters to shift a small amount as needed to better work with our data. Transfer learning allows us to train complicated models much more quickly, assuming we are working in a similar problem space. For example, using a model pre-trained on ImageNet to identify common objects like people, cars, animals, and so on. You would not want to perform transfer learning on such a model to identify things like frequency spectrograms, as the images are vastly different in their composition than the original training set. Additionally, since most of the parameters are already set, you can get away with far fewer training epochs. Training MobileNet from scratch might take 10,000 epochs or more, but you can do transfer learning in just a few dozen epochs. Transfer learning can save you a lot of time and energy. Now that we've seen how to classify images using both simple and complex neural networks, we're going to look at object detection in the next module. That's where we start to be able to locate an object in an image. Now that we have a trained object detection model, let's download it onto our Raspberry Pi and then use it for live inference. To start, we'll want to make a new project folder. I'm going to call mine ball dog toy detection, and I'm going to go into that directory. Once again, I'm going to run the Edge Impulse Linux runner with the clean parameter that allows me to select a new project and then tell it to download the model file from my object detection project. Sign in with your username and your password. You'll want to select your object detection project, and then the tool should automatically download your model file. From there, you can check that the file does appear in your Linux file system. To start, we're going to import some Python packages and modules. As we've done before, we're going to need OS, System Time, OpenCV, the two PyCamera libraries, as well as the Edge Impulse runner. Notice here that we're using specifically the image runner, which is different from what we saw in the dense neural network, as this one allows us to extract features from images. From there, we're going to need to load in our model file that we just downloaded, and we're going to need to set the resolution, width, and height, which I will keep to 320 by 320, which is what the model expects. As we've done before, we're going to load the model file, and then we're going to initialize it. If this initialization process causes any problems, we'll throw an exception, print it out to the console, and exit the program. Because object detection is normally very computationally expensive, I'm going to keep track of the frames per second and print it to the preview window so we can see how quickly this whole thing is running. Next, I'm going to start the PyCamera, and as I've mentioned before, you're welcome to try this with a webcam, but this code is going to be a little different since we're not using the PyCamera library. Webcams and Linux have traditionally had a somewhat difficult history where there weren't a lot of drivers that supported webcams. I think that's different in this day and age. However, because there are so many webcams out there, I won't be able to help you debug whatever particular version of USB web camera that you're using, so I recommend using the PyCamera if you're taking this course. I should be able to help you debug any problems you might have with it. From there, we'll configure the camera with 320 by 320 resolution. We're going to set up a for loop that essentially runs forever that gives us a new frame in this frame variable each time it runs, and that's coming directly from the PyCamera. From there, we need to get a timestamp of the current time so that we can print out the frames per second onto the preview. We're then going to get a NumPy array from this frame variable. With that, we can convert it into the features that the Edge Impulse model expects. And to do that, we're going to call the runner object, which comes from our model file that we imported with the image impulse runner. And we're going to call this getFeaturesFromImage function and pass it our NumPy array that represents our image. Remember that this should be an array of pixel values where each pixel is represented by a blue, green, red value between 0 and 255. We should not need to perform any other feature extraction or image manipulation, since the image should be in the correct resolution with the correct color and BGR values, which means after we call the getFeaturesFromImage, they should be converted to whatever the edge impulse model expects in this features variable, and we're going to pass that to the runner.classify in order to perform classification using our object detection model. I always like to print out the raw output from this model in order to see how I can look into it or index into it to get the values that I need. If you were to print those to the console, you should see that we get a list of bounding boxes. If there are no bounding boxes, it should just be an empty list, and so this for bbox in bboxes just shouldn't run. Using the information from this bounding box list, we can extract the x and y coordinates as well as the width and height in order to be able to draw our own bounding box on top of the detected object. You can also use this information for whatever embedded system project you are trying to do, like point a laser pointer in front of a cat, throw a ball for a dog, figure out where cars are in an image in order to avoid them, and so on. For testing, I'm just going to draw a bounding box over the detected object. To do that, I'm going to use the OpenCV rectangle function, give it the image where I want to draw that rectangle, and then give it the coordinates of the x and y that were from the original bounding box, that should be the top left corner, and then the bottom right corner given by x1 and y1, which should just be the x value plus the width and the y value plus the height. I'm going to draw these bounding boxes as pure white, so I'm going to use 255, 255, 255, but feel free to, say, assign a new color for each unique label or each unique class, so that you can have, say, all dog objects be highlighted in red and all ball objects be highlighted in green. But I will leave that up to you to try. I'm just going to paint everything in white just to make it simple for this script right now. The next thing I'm going to do is draw the object label. I'm going to change this to label, and I'm going to draw the score at the top of the bounding box, so you should be able to see the class that each bounding box should represent, along with the confidence score or probability. To get those, all we do is just call the bounding box that we get from the list of bounding boxes, index in using the label key, and we do the same thing but using the value key. That should give us the class label along with that class's or label's particular confidence score. And we can just print those inside of the bounding box given by the x and y of the bounding box. Finally, even if I don't have any bounding boxes that resulted from inference, I am going to draw the frame rate in frames per second on the frame. This gives me an idea of how quickly this whole thing is running, which includes capturing an image, converting it to the correct features, and then running inference in order to find those bounding boxes. As we've done before, we need to call the imshow or imshow from the OpenCV library, give it the image, and this makes it appear as a preview window with the name frame. To get it to work, we also need to truncate the raw capture from the frame that we saw earlier. This prepares it for the next frame and allows the frame to continually update, giving us something like a video stream. Next, we calculate the frame rate that gets updated on the preview in the next iteration of this for loop, and then give it some way to quit out of the program by pressing the Q key if we have that preview window highlighted. If we do press the Q key on that preview window, we'll want OpenCV to destroy all of the open windows just to create a nice way to clean everything up. Next, I'm going to save this on my Raspberry Pi in my ball dog toy detection folder, as that should have my .eim model file. And I'm going to call it live detection PyCam. Let's save that and now go over to the Raspberry Pi to see if it works. The script that we just wrote should be saved on the Pi, and you can see it here as live detection pycam.py. Now we're going to run it, and I'm going to move my PyCam around to see if it will detect things. As my dog walks around, you can see it is detecting dog correctly for the most part. If he lies down, it's about 0.7. It's picking up the ball every now and then, and it's grabbing the toy, although it looks like it's getting two bounding boxes sometimes for the toy and the dog. When I move the ball toy and, well, dog to a farther location, you can see that it still detects the dog decently well. It detects the toy okay, but I'm starting to get about a 0.5 confidence, which means it's starting to lose it, and it's not detecting the ball at all. This just goes to show that smaller objects do not perform very well with this model, even though we had a lot of training data showing the ball farther away. As a result, I recommend using a model like this with such a small resolution for objects that are closer up, or larger in the frame that just take up more of the frame where the model can pick out individual features on that object. However, it is still detecting my dog pretty well. Additionally, you can see that the frame rate is about 1.7, 1.8 frames per second, which is pretty slow, and that's about as good as we're going to get on the Raspberry Pi. If you introduce things like a hardware accelerator, or you switch to something like an NVIDIA Jetson Nano, where you have hardware architectures that accelerate or are designed to run things like neural network, you can expect a better frame rate. However, this is going to be the best we can do for now, but about 2 frames per second is pretty good. I hope this helps you get started training and deploying your own object detection model on something like a single board computer. Let's take a quick look at image segmentation. It's an advanced concept that we won't spend much time on in this course, but I want you to know that it's out there as an active area of research in computer vision. The idea behind image segmentation is to separate each object in an image by examining its individual pixels. As such, each pixel in the image is given a label as belonging to one of the objects. For example, in this photo, we might want to separate the different objects. You'll often see image segmentation outputs as another image with the same dimensions as the input image, but the pixels classified to their respective objects. For example, the laptop is black, the wall is white, the table is yellow, the power cable is red, and the glass is blue. We would want to have a good idea of the individual classes we're looking for when constructing such a model or filter to produce a segmented image. If we were trying to identify keys on a keyboard as opposed to anything else in the image, the output might look a lot different. Object detection gives us bounding boxes with X and Y coordinates. Image segmentation gives us more information about the shapes of the different objects. A bounding box might be good enough, but sometimes you need more information. For example, image segmentation might help medical researchers look for cancerous cells and isolate them from normal cells. In that case, the shape of the cell could be very important in determining its type and exact location. This is an image of cancer cells that have been colorized by the National Institute of Health. Image segmentation could help us identify such cells and give us similar coloration automatically to help identify cancer in patients. This paper combines segmentation with the faster RCNN model to help identify pedestrians more accurately. This is potentially useful in security cameras and self-driving cars. One of the easiest forms of image segmentation you can do is a simple threshold. Convert an image to grayscale and set a threshold value. Any pixel over that value is one color and everything else is another. Assuming my grayscale capacitor image here is stored as a NumPy array in the img variable, this code snippet will convert anything less than a value of 145 to white. Everything else will be black. This produces a very basic segmented image of my capacitor. Note that this only works on objects that have a high contrast with their background. You could set up multiple bands of color or grayscale values, but this doesn't work well with objects that have lots of complex shapes and colors against similarly complex backgrounds. Another popular technique is to use k-means clustering to group pixels with similar color values or other features together. However, this only works well when the features are guaranteed to be similar within each class or object. Imagine a person wearing different colors for their shirt and pants. While k-means might pick out the different articles of clothing, it might struggle to see the whole person. In 2015, UC Berkeley researchers proposed something called a fully convolutional network. Here, they used the feature extraction portion of a convolutional network to create a feature map. Note that this section could be something like VGG or MobileNet without the classifier network usually found at the end of the model. This feature extractor is also known as an encoder. The feature map is then sent to another convolution layer that produces an output the same resolution as the original input image. This step is known as a decoder, and it's in charge of assigning a label to each pixel in the output segmented array. What we've been looking at so far is known as semantic segmentation. This is where objects of the same class are given a single value. As we see in Figure 6 of this paper, objects of the same type are highlighted in one color. For example, person, horse, and car are different objects that get the colors pink, magenta, and gray respectively. This type of classification isn't great for determining the number of instances of each object present in an image, but it can tell us where some objects are located. Note that training this model is like training other convolutional neural networks that we've been looking at in this course. The difference is that the ground truth output is a segmented image map where the pixels have been given values that correspond to the object they represent. The idea is that the model's convolutional filters would automatically update their weights during the training process so that an input image like the one on the right would produce an output like the one on the left. Other similar models have been proposed. For example, researchers created this UNet model for doing biomedical image segmentation. Similar to the fully convolutional network, UNet contains an encoder that is much like the convolution layers we've been looking at in the course. An input image goes through a series of convolutional filters and pooling layers to produce a smaller feature map. This feature map then goes through a decoder, which upsamples the feature map to create a segmented image the same size as the original input image. The trick with UNet is that it concatenates feature maps from various stages of the encoder side to same-sized feature maps on the decoder side. Once again, the model outputs a segmented image with the same resolution as the input image. As you can see in the results section, UNet has been successfully used to identify different parts of cells. While there are plenty of models out there that improve on each other when it comes to image segmentation, the last one I want to show you is a model called MaskRCNN, which was proposed in 2018 by the Facebook AI Research Group. MaskRCNN does something a little different than the semantic image segmentation models we were just looking at. It's attempting to do what's called instance segmentation. The output images in Figure 5 do a great job at explaining what this means. As you can see, it's not only doing image segmentation to identify the types of objects and which pixels make up those objects, but it's also doing object detection. This means that it can uniquely identify each object of a class in the image. Instead of just highlighting all the pixels that make up the person class, it can identify the individual instances of the person class. It does this by building on the faster RCNN model. It adds a new MaskRCNN system to the faster RCNN model that uses a full convolutional network to create a mask of pixels from each proposed region of interest. From this, the model outputs a class prediction, bounding box, and pixel segmentation for each object found in the image. Don't worry if you didn't fully follow this lecture. Right now, image segmentation is mostly being used in large computers to assist with complex computer vision problems. As a result, it's a little out of scope for our course. However, I fully expect to see image segmentation making its way to embedded systems in the near future. Multi-stage inference requires training and using multiple machine learning models such that the output of one model becomes the input to the next model. Dmitry Maslov from Seed Studio is going to talk about multi-stage inference and give a demonstration using a Raspberry Pi based platform known as the RE-terminal.
Hello everyone, my name is Dmitry Maslov from Seed Studio and Hardware AI. Let's talk about multi-stage inference. You have already familiarized yourself with object detection and image classification tasks. Multi-stage inference in computer vision most of the time involves a combination of these two. What is the main benefit of using multi-stage inference? Object detection networks in general, and the ones used on embedded devices in particular, are not very good at distinguishing between multiple similar classes of objects. So what we very often do is use object detection network to detect a large class of objects, for example, a face or a car or a dog, and then crop out the image and rescale it, the result of detection, to be fed to image classification network, which gives a much more nuanced output. For example, the emotion on the face, car model, or dog breed. Another popular use case for multi-stage inference is OCR, or optical character recognition. Instead of performing detection of every character in the whole image, which is resource intensive and prone to errors, most often we first detect the text, and then recognition is performed on pieces of text cropped out of large image. For this exercise, let's take car model recognition as an example. In Edge Impulse, train a car detector. This should be fairly easy since we are using transfer learning and the base model already was trained to detect cars. So it contains the necessary feature maps. For image recognition model training, we are going to use a subset of Stanford cars dataset with 6 car model classes. I picked 6 classes of cars that I think I will be able to encounter while walking outside here in Shenzhen, China. After training the model and optionally checking the detection and recognition accuracy on pictures that you can take with web camera or find on the internet, let's deploy these 2 models on an embedded device. I have used ReTerminal, a Raspberry Pi 4 compute module-based development board with a touchscreen in a sturdy plastic case. It comes in handy while on field trips like the one I'm going to take. Raspberry Pi 4 compute module has the same CPU as Raspberry Pi 4 development board, but has an option to include onboard eMMC memory. The module in ReTerminal has 4 GB of RAM and 32 GB of eMMC. First of all, you'll need to download the models for car detector and car classifier, which you can do by using Edge Impulse Linux Runner, logging first to the project for car detection, and then run the following commands, which is Edge Impulse Linux Runner, download car detector .in, and then logging into your car classifier project, and then you'll need to run clear command, and then you'll need to log into car classifier project and download the model for car classification. Then if you look at the multi-stage inference script, you'll see that it's actually very similar to the scripts for object detection and image classification. Basically it combines these two. You'll see that the main function of this script is very similar, with the exception that we obviously have 2 models now. So we're getting the path for detection model, for the classification model, and then creating the context for both of the models at the same time. Then we get the information about the models and print it out. Then we find the suitable web camera here, and then here is for loop that is going to acquire the images from web camera and then return the detection results and the processed image. Then what we do is for each bounding box of the object that we found, we are cropping that bounding box out of the image and then resize it to the classification model input size. And then we performing the inference on that small image with the classification model. And then finally we do some printing here And also I added the draw result function, which obviously does what it says exactly here. It draws the both detection bounding box and the classification result. And you already saw how it works in the previous video. In conclusion, do we really need multi-stage inference? And could object detection model do both detection and fine-grained classification? There are some models that can perform detection and large class size classification pretty well, such as YOLO 9000. Not suitable for running on embedded devices with constrained resources. So for now, multi-stage inference is best technique we have in our computer vision arsenal for this type of application.
Matt Kelsey is a machine learning researcher at Edge Impulse, and he's going to talk to us about his active area of research. By breaking a neural network down into components or layers, we can reuse intermediate outputs from those layers to create a self-supervised learning system.
Hi, my name's Matt. I'm going to do a short talk on reusing representations. So what do I mean by representations? Well, let's go through a quick sort of high-level view of what we often think about machine learning, which is this idea of our goal is to learn these functions f. And the function we're trying to learn takes some sort of input, I'm going to call this x on the left, and tries to map to some sort of output of interest to us. And when I say representation, I'm sort of thinking about any of the internal sort of features that a network like this or a function like this f may learn along the way. So one particular thing of interest here with these functions is that they're often around compression. So I can think about this function f as going from some high dimensional x, like an image, to some very low dimensional y. Say, for example, I'm trying to do classification where I'm saying, is this one of 10 classes? Now, neural networks have another logical breakdown. We often go by the name of, say for example, layers, where this f is actually composed of many little f's that sort of talk to each other. And the first f is responsible for taking the input x and sort of changing it in some fundamental way that then becomes input to the next this subfunction f. And when I think about representations, I'm thinking about what are these internal sort of structures, the internal views of the data as it gets passed along from this x on the left to the y. Now, a modern neural network with these f's may have many of these layers, 100 plus or more. But for this talk, I want to really talk about one of the ones that's more to the right-hand side. It's one that's getting closer to the output. And as I said, because there may be many of these f's, you can think about the sort of the functions on the left-hand side being maybe 99+% of the entire model as a whole. And this last little bit at the end is just like you can think of maybe as the last few transformations from whatever this sort of internal encoding that the network has learnt to the final sort of thing of output. So I'm gonna think about it in that way, that when we're training these functions, we're actually training two functions. One, like an encoder, so there's learning this internal representation, and that's this first piece. And that's the bulk of the network. The bulk of the network sort of goes from X down to E. And E has been co-trained, like this, jointly trained with this other part to then output this final prediction of what Y might be. And why have I sort of split it like that? Well, there's a lot of ways that are using one part or the other of this sort of decomposition in interesting ways. Probably the most successful and very well-known way is an idea called transfer learning. If I think about starting with a very large data set, B here denotes a very big data set, and I jointly train these two functions, the encoder and then sort of a part on the end, maybe it's a classifier, a small classifier at the end. Then if I'm a large internet company, I might have trained this very large encoder on a lot of data. And why do I care about that as a user, maybe that only has a small amount of data? Well, there's this general adage in machine learning that says the larger the network we need, the more sort of examples of data we need to train it. So if my x here, my small x, is similar to my large x, I can take a bit of a shortcut and I can say, well, let's just reuse the existing encoder that maybe someone has made available to me, and then only train the second piece. And under that general idea, which is true that the less parameters we need to train, the less data we need, I can sort of, get a good result with only a small amount of data, under the assumption that my input was the same. So if this is a large vision model that's been trained on something like ImageNet, which has a large diversity of sort of natural images, then I should be able to get away with training with a small amount of data. That's a really great thing for me. And this is the common fundamental setup in transfer learning. What this talk is going to be a little bit more about, which I think is really interesting, is the next wave of this type of work, which is around this idea of contrastive learning. And in particular, it's talking about this function that we're learning here, E, in the context of other data sets. And I'm going to go through one fundamental thing that allows us to do a lot of what we'll follow. Let's assume we've got a data set, and this is the ith instance of this data set. So I don't know what it could be. Let's say we're doing classification of images into 1 of 10 classes, and this is an image of a tree. So I've got some particular image of a tree, X, and I've got some label that is currently tree. This represents one instance in my data set. What if I had another instance in my data set? I'll call this the jth instance. Again, it would be an image of something and a class. There's a particular interesting thing. Say that for the selection of these I and jth instance, that the Ys were the same. So say they were both trees, for example. Then under this idea that this network is about trying to compress things and smoothly doing it towards the sort of output, then it seems intuitive to say that if these two Ys are the same, say tree, then I would expect at this point of the encoding for the encodings to be like each other. Because if I'm sort of thinking about this second part as being a classifier that needs to sort of operate on this encoding, then if they were both trees, then the encodings need to be the same. So fundamentally, that idea that the encodings need to be the same when the class is the same can hold no matter what the class is. So it's a reasonably strong assumption to make, but an interesting one to say that I can start to use this as a learning objective. I can say, given that two instances are the same class, I want their encodings to be the same without even knowing what the class is. And that's very powerful, and we can use that in a lot of different ways. One of the fundamental ways this is being used now in a lot of the state-of-art models is this idea that focuses around how augmentation works in images. So let's have a quick review of what that means. There's a really common thing you probably would have seen in image classification or a lot of image networks, where I can take an image like this picture on the left-hand side, and I can, if I'm doing classification, I can take that image and I can do lots of transformations of that image that don't break the idea that the class is still the same. So we might rotate the image, I might do a little bit of a crop, I've changed the color, in this case, saturation, contrast. But the fundamental idea of image augmentation is that I can do all these transformations that put me in a different part of pixel space without fundamentally changing what the salient object class is. So in this case, it would be dog, but by doing all these mutations, I keep it as dog. We can use this idea that I can do image augmentation to make instances of the data where, without even knowing what the class is, the class has not changed. Let's concretely talk about that. If I then say, I'm going to take a picture of my dog here, and I'm going to apply two random augmentations. And it's a really good thing about this augmentation approach is that it's stochastic. So maybe I've rotated one way, I've rotated the other way, I've changed different amounts of lighting. If I think about these as instances of training that I want to feed into a network, if I'm only interested in learning the encoder part, as a pre-step to doing some transfer learning maybe later on, what I can say is these two images through the encoder, I want them to be the same. So without even knowing what the original class was, I'm going to say this is going to be part of my learning objective. I want the network, when it's learning this encoding, to when it takes this image and when it takes this image, return the same encoding. Now, I don't actually care where, if I think about this in a spatial sense, and I think about encoding as being a point in space, which is common in say, the embedding view. I don't care where they are, I just want them to be close to each other. Now, we have a bit of dangerous position here. Neural networks are good at optimization, and the optimizer will, nicely degenerate everything to zero. So what I'll actually do commonly in these contrasting cases is to pick another example where I don't want things to be the same. So, for example, a picture of this cat. So when I take the cat and I sort of change it, I want this to be an encoding that as an objective, is different to the other ones. So I can treat this as, I want these two, the red and the green, to be the same encoding. I'll treat that as part of a loss function, and at the same time add components to that loss to say that the red and the blue one should be different. Now I can do this with instances where I don't know the label. just by saying, take any image from a large data set and do 2 augmentations, take any other image from a data set and do the augmentation. And more often than not, they will not be the same class. So in general, in expectation, this idea holds that even without knowing labels, I can make these self-label type approaches where I say these are the same. It's very, very powerful. And this idea of using this as a pre-training step, like a learning representation step, before basically training a classifier is common in state-of-the-art image classification models at the moment, pre-training step on a very, very large unlabeled data set. Now, this is contrasting using an idea of augmentation, saying that I've got cases where 2 things should be the same, and I've got cases where things should be different. But where contrastive learning gets really interesting around representations is when you use much more novel ideas about what is similar and what isn't similar. My favorite example came from robotics. This is the first example I saw of this idea of contrastive learning. Say, for example, I have a robot arm that is reaching into a tray and it's picking objects up. And I want to learn some sort of network, or some sort of, pre-train a network that is sort of understands something about the pose of this arm. And by the pose of the arm, I mean sort of the description in joint space of where this arm is. So, if, for example, our arms, we can think about a rotation and a bend. And, my arm is located in space according to some series of numbers. So I want to learn an encoding of the arm. What I can do, which is, I think, is a fascinating idea. So I'm going to actually take a scene with a robot arm, sort of, in this case, simulated, reaching into a tray and coming back up. And I'm going to actually have 2 cameras viewing this robot arm. And the reason I do that is because I have an idea about time. Things being at the same point in time should be the same, whereas things under the idea that the arm is always moving, 2 things that are different in time should be different. So if I'm interested in using a data set like this to learn a network, pre-training a network that's good to sort of learn a representation around the arm pose, I can do the following. I can take these 2 cameras that are sort of recording at the same time, and I can take 2 of the images from different cameras at the same time. Now, and there's an invariant that holds here that I know, even though in pixel space, these look very different, the arm is in the same position because the camera images were taken at the same time. So I can use these 2 images as examples that go to the network to say, I don't care where you put the encoding, I just need these 2 to be next to each other. And you can see this is actually potentially quite difficult because in pixel space, these look fundamentally different. It's like the augmentation we're talking about, where we're making a change that's invariant to the class, but it's a lot more difficult here because the pixels are quite different. And in the same way we had the example before of things that are the same, under the assumption the arm is always moving, we can also say that if the arm is moving, then 2 images from the same camera at different times should have a different arm pose. And I want the encodings for these to be different. Now you can really see here, this is difficult because it's only the arm that is moving in this case. So for these 2 to have different encodings, the network really needs to focus on the thing that's changing, which is the arm, even though in general pixel space, these are quite similar. This example of contrasting over time comes from a paper called Time Contrasted Networks by an ex-colleague, Pierre. And this is the one that really got me into contrastive learning that I thought was such a great result, because we've got an effectively endless amount of data here. All we need to do is move this arm around, have 2 cameras that we know are taken at the same time, and use that contrastive invariant to say 2 images at the same time should have the same encoding, 2 images at different times need different encodings. And because more often than not that is generally holds true, we can use that as a learning objective to pre-train a very, very large network. That's fascinating. Now, there's so many cases where you might want to use this. This may work on other cases in vision, for example. This is a quick image I took from a screenshot from an NVIDIA Drive Labs video, and it shows these object tracking they're doing, and I didn't really pick it because of that. I just picked it because this is a good example of the different frames and videos you might have on a self-driving car. So that idea of contrastive learning could hold here as well, because we know the time is the same. So for example, any 2 pairs of these videos should in some way, if we were pre-training, act as things that represent the world as a whole at the same time and should be the same. And you can think about the ones on the top row here, the forward-facing cameras. Any 2 pairs of those should be a similar enough encoding that we could use this as a pre-training step for a network, which is very, very, very powerful concept indeed. But really the contrastive learning idea is that what can you imagine? What can you put around your data to say that there are 2 things that are the same? For example, 2 microphones in the same room that are recording audio. even though they'll fundamentally have different signals, because again, it's at the same time, you should expect things to be the same. And so an encoding should be the same. It's a fundamentally really super powerful idea. So that was fundamentally it, my idea of talking about reusing representations that have come from pre-training, particularly in contrastive learning, and how this is basically one of the next waves of what we see for transfer learning. So thanks so much for listening.
In this module, we covered some advanced computer vision concepts for you to consider. We spent most of the time talking about object detection, which is an important concept in embedded vision. In most cases of object detection, we are trying to uniquely identify each instance of an object type in an image and then figure out its location. We do that by generating what's known as a bounding box that consists of x, y coordinates of the object and the width and height of that object in pixels. Note that some bounding boxes give you center coordinates and some give you the top left of the box. Either way, you can use that information to figure out where the approximate center of the object is for your project. This can be very useful for something like having a camera automatically track a person or animal, or having a self-driving vehicle automatically avoid pedestrians and other cars. One obvious way to accomplish object detection is to slide a window over the whole image and perform inference on whatever sub-image is under that window. If the object is found, you can highlight wherever that window was to create a series of bounding boxes. However, this has a number of problems. A single object might generate more than one hit. Without additional steps, the system might see my dog as 3 different dog objects. Also, it will generally only find objects that fit completely inside the window. If an object is too large or too small in the frame, it will be missed. You could slide windows of different sizes over the image to look for large, small, near, and far objects. However, this illustrates the third problem with this approach. It's very computationally expensive. You have to perform inference on every single window, which could take a long time. This might be okay if you only need to look for objects in a still image once every minute or so, but you likely won't get a usable frame rate on live video streams. That's where we introduced this concept of region proposal. Modern object detection algorithms focus on only a few areas of the input image that might contain objects. Image classification is performed on these regions, which cuts down on the number of times inference needs to be performed. That gives us a more complex model that can be trained and used to perform object detection. We feed the model our input image and it outputs a list of objects that it detected. Each object contains the predicted class, a probability or confidence score of that class, and a bounding box coordinates and size. We can use that information to draw the bounding box on top of our image to give us an idea of what the model found. To train such a model, we need to provide the training process with ground truth bounding boxes and labels for each object of interest in a set of training and test images. From here, information about the regions can be combined, or the window with the highest confidence can be selected to determine where the objects appear in the image. From there, we looked at how we can evaluate object detection models. To begin, we would graph the recall versus precision for each label as we moved the classification threshold from 0 to 1. At each threshold value, we can calculate a precision and recall score from the validation or test set. We then estimate the area under the precision recall curve by averaging 11 different points. To determine if a bounding box is considered good enough, we would compare it to the ground truth bounding box and calculate the intersection over union. This is where we first find the area of overlap between the two boxes and then divide that value by the area encompassed by both boxes. If this IOU value is above some threshold, normally 0.5, we would say that the bounding box is a true positive for that particular object. This is, of course, assuming that the predicted bounding box and ground truth box are of the same class. The mean average precision is a common metric used for measuring the performance of an object detection model. One way to compute the MAP score is to calculate the average precision for each class at a given IOU threshold, like 0.5, and then find the mean of those scores. Some newer papers and competitions rely on finding the mean of the average precision scores for all classes across a range of IOU thresholds. This helps to give higher scores to models that are more precise with their bounding box placement. We then looked at a number of popular object detection models. The first was a region-based convolutional neural network. Here, a region proposal algorithm identified areas of interest that were sent to a convolutional neural network and classifier. This information was also sent to a regression model that updated the location and shape of the regions to create better bounding boxes. Next, we examined fast RCNN that built upon the ideas from RCNN. Here, the region proposal happens in parallel with the convolutional stages of the model so that feature extraction only needed to be performed once, thus saving some time during training and inference. Faster RCNN takes this a step further and performs region proposal on the feature map instead of the raw input image. To do this, the authors use a neural network for region proposal instead of some other algorithm like selective search. They called this approach a region proposal network. Finally, we looked at the single-shot multi-box detector that performs feature extraction, region proposal, and determines object location in one pass through the network instead of needing to do classification on each region of interest. By performing classification and bounding box regression on the output feature map of each convolution stage, the image is essentially divided up into a series of different sized grids, where each cell has a variety of potential default bounding boxes. The classification heads determine if the proposed bounding boxes belong to one of the classes or the background. Redundant overlapping bounding boxes are removed in the non-maximum suppression stage so that we end up with, ideally, one box per object. The output should give us unique bounding box and classification information for each object in the input image. Note that at this time, the SSD model we use in the course only works with color images, so we can't save on processing time by converting everything to grayscale. I showed you how to use transfer learning in Edge Impulse to train your own object detection model and then deploy it to a Raspberry Pi. Finally, we touched on some advanced concepts that, while outside the scope of the course for now, are important to keep in mind if you are working on an embedded computer vision project. These are just a taste of what's actively being researched in computer vision. I briefly talked about the idea of image segmentation and how it can be used to discern object shape. I also went over a few papers that showcased some popular image segmentation models. We also heard from Dmitry Maslov, who gave us a multi-stage machine learning demonstration. This helps us see how we can use multiple machine learning models in tandem to meet our needs rather than trying to come up with a single model for our project. Finally, we got to hear from Matt Kelsey, who showed us how we can reuse representations or encodings from the middle of a machine learning model. We can use these representations to create a self-supervised learning system. Object detection is exciting, and we're just now starting to see it work on embedded systems thanks to a bunch of research that went into optimizing both hardware and software. Computer vision is a very large field with lots of potential applications. I hope that this course has helped you get started using machine learning techniques for computer vision on embedded systems, and I hope you had some fun along the way. I know that I enjoyed making the projects as well as learning about the current state of research in the field. If you'd like to dive more into computer vision with machine learning, I highly recommend this advanced computer vision course by Lawrence Moroney and Eddie Hsu. They go through many of the topics covered here, but they also cover image segmentation in greater detail. The focus is on creating systems for larger computers, so many of the applications won't be designed for embedded systems. Adrian Rosebrock runs the Pi Image Search website, which is a fantastic resource that covers classic computer vision and deep learning concepts. He has free articles and books that you can buy to help you on your journey. If you run into issues with the Edge Impulse site or various tools, I highly recommend posting to the Edge Impulse forum. I find the people there are very helpful and responsive. TinyML.org is a great place to keep up to date with various research and development in the embedded machine learning community. They host weekly talks by researchers and industry leaders, as well as host conferences a few times each year. You can also check out their community forum where people discuss the talks and various embedded machine learning topics. There is a lot of research still being done in machine learning and computer vision right now, as they are very popular fields. Because new models and techniques are being proposed every year, you might want to keep an eye out for new papers on Cornell's archive.org page. For example, here is a relatively recent paper that provides a history and overview of popular deep learning techniques used for image segmentation. We only barely scratched the surface by looking at mask RCNN. Don't worry if some of these papers are confusing. It often takes a lot of time, effort, and background knowledge to understand the content. You can often find well-written articles on sites like Towards Data Science that break down these complex research papers into simpler terms. The last thing I want to mention is the idea of automating your machine learning process, which is something we only barely touched on in the course. I wanted you to collect your image data manually so that you could examine the files on your computer or play with them in Colab. However, Edge Impulse has a number of tools that help you automate the upload process so that you can collect data and send it right to your project. From there, they also offer a full API so you can script the training and deployment process. I always recommend doing a few machine learning projects by hand first so you get an idea of how to look for over and underfitting as well as how to tune the hyperparameters. Once you get the hang of that, you can start to automate the process if you want to. For example, you could create a unique model for each system that you deploy. I also recommend checking out Edge Impulse's blog and their Twitter page for fun and interesting projects that involve embedded machine learning. You can also find me on Twitter in addition to being able to contact me using the Coursera tools. The pairing of computer vision and machine learning is a powerful combination, and I hope that this course has given you a start to using them in your own projects. I want to thank you for being a student in this course, sticking with it till the end, and I wish you luck in your embedded machine learning journey. In addition to convolution, we can use other operations like pooling to downsample the image. This has the effect of reducing the size of the data as well as creating a consistent feature map that stays the same regardless of small variations in position of the subject. There are a few popular techniques for pooling. The first is average pooling. To perform average pooling, a window is applied over the top left section of pixels on the input image. You'll often find windows in 2x2 or 3x3, but they can be any shape. The pixel values under that window are averaged to produce a single output value, which is stored in the output image. The window slides over to the next set of pixels. In most cases, the horizontal stride is the same as the window width, and the vertical stride is the same as the window height. You'll usually want to avoid overlapping the window in pooling, as the idea is to downsample the image. Notice that I'm skipping the last column, as I'm unable to fit a window without overlap. This assumes a valid padding scheme, which we talked about in the convolution lecture. With valid padding, we do not add any padding to the input image. You could also perform same padding. This would add additional rows and columns of zeros or other values so that you're not losing information on the edges. Also, notice that I'm rounding the output values when storing them to my output array. For pooling with arbitrary data, you would likely not need to round or truncate the data. However, since I want my output to act like an image, I need the values to be 8-bit integers, so I round the values and make sure they're between 0 and 255. Another popular form of pooling you'll see is max pooling. It works similarly to average pooling in that we use a sliding window to compress the features in an image. This time, instead of computing the mean of each group of pixels, we simply pick the element with the highest value and keep that. We slide the window to the next group of pixels and repeat the process. We keep doing this until we have found the maximum values for all of the window positions. There's less math involved in max pooling, which potentially makes it more efficient. It also allows us to pick out the most salient or important features in an image. You could also have min pooling, where the minimum value is kept, but max pooling is much more popular. Something else that you might come across is global pooling. This is where the window is the size of the entire image. You can have global average pooling, where the average of all the pixel values is calculated. Once again, I'm rounding to store the output as an 8-bit integer. You could also do global max pooling, where only the maximum pixel value of the whole image is kept. Global pooling is used to aggressively downsample an image or to simply denote the existence of a feature. When it comes to convolutional neural networks, you'll often find pooling operations done after convolution, which means that pooling is done on a filtered image that does something like edge detection. Pooling allows us to compress the image in a way that keeps those highlighted features from the convolution step. Let's take a look at a filtered image of the same elephant we saw in the convolution lecture. Here, we did a simple outline or edge detection filter. If we perform a max pooling operation on this image using a 2x2 window, we get something that looks like this. First, notice that the output image is much smaller as we've reduced the number of pixels by 1/4. If we then decide to feed this filtered and pooled image to a neural network, that's a lot fewer dimensions and parameters to work with. Average pooling makes the image look like it's simply been downsampled. Some of the edges might get lost, especially, it seems, on diagonal or curved lines. Now, let's compare this to the max pooling operation. As you can see, the edges are much more pronounced. This is because edges are higher valued numbers in the matrix, much closer to 255 than, say, 0. As a result, the max pooling operation keeps those in the output image rather than trying to average them. When it comes to picking out features after a filter like an edge detector, the max pooling operation does a better job of highlighting those sharp features than average pooling. However, max pooling can lose some of the finer details, as it simply drops the non-highest values in each window. If those details or smooth transitions between areas in the image are important to your application or model, then you may need to use average pooling. That being said, I see max pooling used much more often with convolutional neural networks for image classification. Another important feature of pooling is that it provides some translation invariance for feature sets. This means that different images can have the main subject in slightly different locations, and the output feature set generated by convolution and pooling can produce the same or similar feature maps. For example, let's say that we're looking at a zoomed-in portion of an edge that's on the elephant we saw earlier. A max pooling operation would produce an output like this. Now, let's say we have another image of an elephant, but the edge is shifted by a few pixels. The max pooling operation would give us something like this. Not exactly the same as before, but it's similar. Both outputs let us know that there is an edge in that general area. This helps generalize the location of features in similar images. When it comes to machine learning, it can help train a more robust model that looks for features in general areas rather than have the model look for exact pixel values in certain locations. I hope this demonstrates how convolution and pooling can work together to extract features from images. This combination forms the basis for the first half of a convolutional neural network. In computer vision and image processing, convolution is a way to mathematically filter images to do things like blur, sharpen, or edge detection. I'll show you examples of those later, but first, let's see how convolution is performed. Convolution is the process of adding each element or pixel in an image to its neighbors, weighted by a kernel. A kernel is a small matrix that does not change throughout the convolution operation and holds the weights for this summation process. I usually see kernels as 3x3 or 5x5 matrices, although other sizes do exist. The numbers in the kernel determine the type of filtering that we do. I'll pick these for this example. Next, we take a section of pixels the same size as the kernel, starting with the top left of the image. Each pixel is multiplied with the corresponding kernel element. All the values in this element-wise multiplication are then added up to give us the first value in our output image, or feature map. The window then slides over by 1 pixel and the operation is performed again. We use the same kernel but a different subsection of the image this time. This gives us our second value. The window slides again to give us the third value. When it reaches the end of the row, the window slides down 1 pixel and starts again on a new row. This process continues until we have used all of the pixels in the original image to create a new output image. All of this assumes a stride of 1, which means the window moves over or down only 1 pixel at a time. With a stride of 2, we would start by computing the weighted sum of the window set in the upper left just like we did before. Then we would slide the window over by 2 pixels and repeat the calculation. We would move the window down by 2 pixels as well to repeat, but since we cannot do that, the convolution is done, and we end up with a 2x1 array for the output image instead. You'll also notice that the output image in any of these cases is smaller than the input image. There are a few ways we can account for this, which I'll talk about in a minute. But first, here is the general formula for image convolution. Capital I is the input image matrix and capital K is the kernel. We index into each of these arrays and sum the element-wise multiplication to get a value for one of the pixels of the output image O. Often in the math world, you'll see that matrices and vectors start with 1 for the first element. However, I've shown the equation for starting with 0 as the first index, as this should be easier to implement in code. S is the stride. H, which I'll show in a second, is the height of the image, and W is the width. Capital M is the number of rows in the kernel, and capital N is the number of columns. Lowercase I is the row index of the output image, and it goes from 0 to the floor of the image height minus the kernel height divided by the stride plus 1. Lowercase j is the column index of the output image, and it counts from 0 to the floor of the image width minus the kernel width divided by the stride plus 1. Here is an example of our previous convolution example with the zero-based indices marked for each matrix. The output image would be a 2x3 matrix if we set the stride to 1. Let's say that we're working with a really odd kernel like this, which causes the output value to be really large. If we're working with 8-bit grayscale values for our input image, then we would usually want to work with 8-bit grayscale values for the output image. These values must be between 0 and 255, so we usually set anything above 255 to 255 and anything below 0 to 0. You'll sometimes hear this referred to as clamping a value. In this case, we'd be clamping the value between 0 and 255. If you're curious, the output image would look something like this, as all values would just be clipped to 255. If you're working with floating point values for your pixels, which can sometimes happen in machine learning, you'll also want to clip or clamp those. 0 to 1 is the normal range, but you might sometimes see -1 to 1 as well. Now, let's talk about padding. Vincent Dumoulin made these great animations and shared them on GitHub. I'll use them to demonstrate how padding works. There are a few types of padding that you can use on the input matrix. We've been looking at what's known as valid padding, which essentially means there's no padding of the input image. Only the valid elements of the input array are used. In this instance, the input image is a 4x4 matrix and the kernel is 3x3. The kernel isn't shown, but we can assume that the element-wise multiplication and summation are occurring to give us the element in the output array shown at the top. With a stride of 1, the output array is a 2x2 matrix. We saw this example earlier, where we convolve a 4x5 input matrix with a 3x3 kernel and use a stride of 2. Notice that while the top 3 rows are used, the bottom row is skipped because we would not be able to move our window down by 2. We only use the elements in the input matrix that are valid with the given window size and stride setting. In same padding, we pad the input matrix with elements in order to give us an output matrix that is the same size as the input. The padded elements are shown by the dotted lines. For example, here we show a 5x5 input matrix with a 3x3 kernel and a stride of 1. With these elements added around the input matrix, the output matrix will be 5x5. Note that even with padding, if you set the stride to more than 1, you still may end up with an output matrix that is smaller than the input matrix. In some libraries, like Keras, if you specify same padding, it will attempt to add as many padded rows and columns as necessary to give you an output matrix that is the same size as the input matrix. There are a few ways to fill the padded elements. One common approach is to just set all of the padded elements to 0. This technique is probably the most common, and it's what Keras does when you specify same padding. Another option is to copy the values on the edges of the matrix out to the padding. This has the effect of making the image look a little bigger than it is and preventing some skewing of the data at the borders that might occur if we use 0 padding. In some applications, you don't need to maintain the information at the borders, so you can get away with no padding. In fact, it's more computationally efficient to work without padding. Not only does it save you convolution steps, it also gives you a smaller output matrix, which might be beneficial for future steps. For example, if you're using this filtered output image as an input to a neural network, having a smaller matrix means fewer input dimensions and therefore fewer computations in each node. However, there are times when you want to use padding. For example, if you're just looking to filter an image to blur or sharpen it, then you will likely want to maintain the same size and shape. Keeping the same shape also means you can perform more convolution steps without continually losing information at the borders. And sometimes you might determine that the information at the edges of the image really is important to whatever vision project you're doing, so you need to use padding to keep that relevant data. If you're working with color images, you would first break the image apart into its separate red, green, and blue color channels. Each channel would then act like the grayscale images we were looking at earlier. A separate kernel would be convolved with each channel to produce 3 separate output images. These output images represent the new RGB channels and could be combined to create the new filtered color image. Note that the kernel can be the same for each channel, but it doesn't have to be. You could use different kernel values for each channel if you wanted to. This would create some interesting effects, as you might blur one color, sharpen another, and do edge detection on the third. When working with color images, you no longer have a simple two-dimensional kernel. Since you have one kernel for each channel, you can stack the kernels together to create a 3-dimensional array. In this example, the first 3x3 matrix would be for the red channel, the second 3x3 matrix would be for green, and the third 3x3 matrix would be for blue. When working with something like NumPy, SciPy, or Keras, it's often easy to store these kernels together, so you would likely store them as a single 3x3x3 array. Using convolution, we can create a variety of filters for our image. Let's look at a few filters that have been applied to this elephant photo. Note that I'm using a small image, 200 by 130 pixels, so that our 3x3 kernels will have a noticeable effect. First up is the Gaussian blur. This simply mixes the pixels in the window in such a way to soften transitions and edges. We can also use the kernel we saw earlier to create a sharpened image. Note that sharpening an image using this method will also amplify any noise present in the image. We can also do this funky emboss effect to make it look like the elephant is carved out of the page. In addition to forming the basis for fun effects for things like Instagram filters, we can use convolution to do edge detection. The first is a basic outline that picks out any areas of harsh transition between light and dark. The next is a Sobel filter, which is a combination of 2 filters that pick out edges in the X direction and Y direction. Edge detection is extremely useful in computer vision as it helps us determine the boundaries between objects in the image and the background. It can also help reduce noise. This is the kind of information that a machine learning model can use to pick out objects in an image or extract features like patterns and shapes to use for classification. We can set the kernel parameters manually if we know what kind of filter or filters we want to use. Alternatively, we can use learning algorithms to set them automatically during the training process if we are using something like a convolutional neural network. In this case, the algorithm essentially tries a bunch of different filters and picks the ones that give it the best features to meet its goal, like classification or object detection. I hope this helps you get a sense of how image convolution works, how we can use it to create fun filtering effects, and how it forms the basis for feature extraction for many computer vision applications. At this point, we've seen all of the basic building blocks that make up a simple convolutional neural network, or CNN for short. Let's see how those pieces fit together to create a robust image classifier. Here is a very simple example of a convolutional neural network, and one that you might see doing basic image classification in an embedded system. We'll assume that our input is a grayscale image. Remember that a grayscale image is just a two-dimensional array of numbers. These numbers might be floats normalized between 0 and 1. They could also be unsigned 8-bit integers between 0 and 255. In some fully optimized models, which we'll see from Edge Impulse, the model might expect a quantized input where the input values are normalized and cast to a signed 8-bit integer value. In this case, the values will be from -128 to +127. The library we download from Edge Impulse should handle this quantization and normalization process for us, but it's a good idea to pay attention to what the model is looking for as an input. Note that the input should always be the same shape. If you trained a model to accept 28 by 28 grayscale images, you should always feed it 28 by 28 grayscale images. Next is one or more convolution layers, where each is followed by a max pooling layer. Note that a layer shown here is not a single convolution or pooling operation. Each layer may contain dozens or hundreds of simultaneous convolution or pooling operations to generate a number of feature maps that are passed onto the next layer. Using multiple stacked convolution and pooling layers like this allows the model to extract more complex features from the image before sending those features to the classifier. After going through convolution and pooling, the features are then stacked and flattened to create a one-dimensional vector. This vector is then fed to a dense neural network to perform the actual classification. The neural network can be more than one layer, but sometimes one layer is good enough, as I've shown in this diagram. The output goes through a softmax operation to give us our output predictions. This flattening and dense neural network step might look similar to the simple classifier we trained at the beginning. However, instead of feeding it raw pixel values, we're now giving it features that have been computed from the convolution and pooling layers. These features ideally include things like edges, blobs, patterns, and so on, which is closer to how we humans interpret images. Let's break down these layers. First, let's look at the convolution layer. Each layer will have some settings associated with it, and these settings can be treated as hyperparameters. This means you can adjust them before training, but they are not automatically updated during the training process. Two popular settings are the number of filters in the layer and the shape of the kernel. A 3x3 kernel is fairly common. Let's say we have 4 filters in this layer. Each filter has a stride of 1, and we would use same padding so that the output features are the same shape as the input image. Our image would be filtered in parallel 4 different times with 4 different kernels. Each of these kernels would extract a different set of features. For example, a few of the filters might perform edge detection, while another blurs the image to get an overall placement of the object. However, these kernel values are not set manually. They are randomized initially, and they are updated incrementally as part of the model training process. In effect, the model is learning which features it should look for to achieve the desired classification outcome. Another important difference between a convolution layer in a machine learning model and basic convolution is that the convolution layer also has a bias term. This is a simple constant value that is added to every element in the output array. The constant is the same within a filter, but each filter can have a different constant value for the bias term. Like the kernel values, the bias term is also a parameter that gets updated during model training. These output images are very contrived for this example, as they're using manually set kernel values to create a particular filtered output. So while we might think that the model is looking for edges or blobs or shapes, in reality the features end up looking something like this. The kernel values are learned and can often look random and weird. Sometimes it can be difficult to figure out exactly what features a particular filter has been trained to pick out. These images were created by using kernel values from a real CNN that was trained to classify these electronic components. The filtered images are then sent through an activation function just like you would find in a neural network node. Without activation, the filtered images are just created through a series of multiplication and addition steps. Activation adds nonlinearity into the process to assist with training and potentially help normalize the output to be between two values like 0 and 1. One popular activation function is the sigmoid function. This converts any number into a value between 0 and 1. In recent years, the rectified linear unit, or ReLU, has become more popular as it can make training faster and is often more computationally efficient than other activation functions like sigmoid. Each pixel value in the filtered image is sent to the activation function, and the result is the output of that convolution step in the layer. While we can depict these output arrays as images, it's usually more helpful to think of them as arrays of features rather than images. When working with floating point values for this convolution step, the values for the pixels and weights can be almost anything. As a result, the ReLU function will operate as intended. You just need to convert any value that's less than 0 to 0. If you try to imagine these feature maps as images, then you'll probably wonder how ReLU works on 8-bit pixels with values between 0 and positive 255. In a fully quantized network, weights and bias terms are often stored as signed 8-bit integers. In each layer, the input image or feature map gets quantized to 8-bit signed integers as well in order to make the filtering and activation functions faster on processors without special hardware floating point units. Rather than 0 to 255, the pixel values might be mapped to negative 128 to positive 127 and stored as 8-bit signed integers as well. This way, negative values are possible during the convolution step and they can be sent through the activation function. For ReLU, any values less than 0 are converted to 0. For the purposes of visualizing this step, it simply means that any shade darker than 50% gray becomes 50% gray, assuming this is how the quantization process set the midpoint of our pixel values. The quantization process can get fairly complicated in TensorFlow Lite, as a different 0 point could be set for an activation function. This might help give more precision for activations of filtered images with more light colors, like the one on the far right. While the filtered images and activation feature maps look similar, if you look closely, you can see that any of the dark shades have been converted to a middle gray to demonstrate how this ReLU function might work. What's left is a collection of prominent features for that particular convolution filter and activation. Note that you may often see one of these filter and activation functions referred to as a neuron or node. This can help you think of the individual units in a convolution layer in terms of a neural network. I'll shorten each of these nodes to a circle, which contains the convolution filter, adding the bias terms to each value, and the ReLU activation step. This gives us a feature map as an output for each node. While we could send these feature maps to another convolution layer or write to a fully connected neural network for classification, you'll sometimes find a pooling step after convolution. Max pooling is one of the most popular pooling operations, and it's what we'll use in our examples. Here, the pooling operation is performed on each of the filtered images to produce a new output feature map that has been downsampled and has the most salient features picked out. Each of these new feature maps is now 14 by 14 pixels. Rather than thinking of them as a separate collection of feature maps, you can also stack them together to create a three-dimensional array of feature maps. This array would have the dimensions of 14 by 14 by 4. This collection of feature maps is used as the input to the next convolution layer. Here, we'll use 2 filters instead of 4, but the other hyperparameters stay the same. Each filter or node works the same way as before. The collection of images are convolved with a kernel, and a bias term is added to all pixel values to produce a new feature map. There's one big difference here between this layer and the first convolution layer. The input is now several images, or a three-dimensional array, depending on how you look at it. Instead of a single 3x3 kernel to filter the image, each node now has a collection of kernels equal to the number of input feature maps. Each of these 4 kernels has its own set of parameters that are determined during model training. So even though a single filter might say it has a single 3x3 kernel, it really has more than that depending on the number of input images. Let's see what's happening in the node on the left. Here, 4 separate kernels are being used to filter each of the input images. Rather than output 4 separate new images, the values under the windows, after being multiplied by the weights in the kernel, are being summed together, plus a bias term to give us a single new value in the new image, or feature map in this case. In other words, this is how groups of pixels are being filtered and combined across several images to give us a new pixel value in the output image. The same thing happens in the other filter. Next, a nonlinear function like ReLU is applied to these arrays to give us the outputs of this layer. Each of these feature maps is a combination of the feature maps that were supplied to this layer. After that, we perform another max pooling operation on each of the 2 feature maps. This gives us downsampled features that are each 7 by 7, assuming we use a pooling window of 2 by 2 with a stride of 2. These are distilled features of the original image. Ideally, as the network trains, it settles on weights in the various kernels that help pick out the best set of features. The final step in this section of the network is to flatten the feature maps. Here, each pixel or array value is stacked end to end to create one long vector. When the end of one feature map is reached, it simply moves on to the next. Instead of a 7 by 7 by 2 feature map, we now have a 1 by 98 vector of features. This is very much like how we flattened our image when we tried the dense neural network for classification. The difference is that instead of using the raw pixel values as input, we're using these features, which should represent salient points in the input image that a neural network will care about. Part of the appeal in using convolution is that the input image can ideally be compressed into a set of important features. If you were to use the raw, flattened image, you would have 784 values going into the next section as opposed to 98. You have to do some computation in this convolution section, but it potentially saves you some calculations down the road. This is especially true if you're working with large images. A 200 by 200 pixel image would be 40,000 input values, and doing some convolution and pooling steps could potentially reduce that down to a few hundred. Convolution layers allow you to condense an image to important features, possibly by using a lot of convolution and pooling layers to create a deep network. These layers take into account the relative position and neighbors of each pixel value, rather than just assume that the raw values are the features. At this point, the features are then fed to a dense neural network, which we covered in a previous lecture. It works the exact same way. One or more layers of fully connected nodes sum weighted values of their inputs and apply a nonlinear activation function to the output. This classifier section can be as deep or shallow as you'd like. In simple, tiny machine learning applications, you may only need one layer as shown here. My electronic components images would probably have 5 classes, but I've shown 3 here as an example. The output layer of your dense neural network would likely pass through a softmax operation in order to give you the output probability of each class. I've listed the dimensions at the input and flatten stage to give you an idea of how the feature extraction section can reduce the dimensions. Note that this assumes 4 filters in the first convolution layer and 2 filters in the second convolution layer. If you use more filters in the last layer, there will obviously be more features at the flatten operation going into the classifier section. I encourage you to play with the architecture and various hyperparameters like the size and number of filters, number of layers, depth of classifier network, and so on. I hope this helps give you an understanding of what's going on inside a convolutional neural network. You may or may not see an improved accuracy over just a dense neural network, but the convolutional layers can help reduce the total number of operations inside the network, which makes the model more efficient. Now that you've seen the inner workings of a convolutional neural network, let's see how we can use Edge Impulse to train one. For this demonstration, I'm going to be using the bitmap images that I collected from my OpenMV camera. If you'll notice, go into your dataset and pay attention to the format of the images. Mine were all taken in BMP or bitmap format, Edge Impulse requires PNG or JPEG images, at least at the time that I recorded this. In the future, that may change, but since I have BMP only from my OpenMV I need to convert these to PNG or JPEG. I'm going to go with PNG because it's a lossless format. You can convert them individually manually, but that takes up a bunch of time, or you can find some program. On Windows, there's this program called Bulk Image Converter. I'm going to use that. So I'm going to go where I stored my data set, which is in Python, datasets, electronic components, BMP, select that. I'm going to include the subdirectories. I'm going to convert BMP to PNG. I'm not going to delete them, and I'm going to click Start. That should be pretty quick as the files are pretty small. You'll notice what happens is if you go into the folder, it puts it in the same folder. So all the PNG files are now in here. Next, I'm going to go to Edge Impulse. I'm going to log into my account, and I'm going to create a new project. I'm going to call this one Electronic Components-CNN. When it's done, it should drop me into the dashboard. I'll click out of this pop-up, and I'm going to go to Data Acquisition. I'm going to click Upload Data since I already have it stored on my computer. I'm going to choose Files. By the way, you can see the supported files here. You can do what we did earlier in Colab and convert it to raw CBOR, JSON, or CSV format, where it's just the raw pixel values, whether that's 0 to 1 in floating format or 0 to 255 in grayscale, or even color if you don't mind having some extra dimensions in there. WAV is for sound files, PNG or JPEG is for our image files. That's what's supported at this time. I'm going to go to my data set, which I keep in Python right now. I'm going to go into the BMP folder, and I'm going to go into my first class, which is background. I'm going to select all of them, which should be all of the PNG images. Click Open. I'm going to automatically have it split between testing and training sets, and I'm going to enter a label. You can name the files with something like background dot and then the number of the file, and then that will allow it to infer the class. As you can see here, anything before the dot to determine that label. But since I don't have the files named like that, I'm going to enter the label manually. I'm going to repeat this process for each of my classes. So here are the capacitors. Change the name or change the class name. And then we're going to do this again for the diode. Once more for the LED. And you'll notice that the images are color images right now. I don't mind storing them as color images in Edge Impulse. We're going to use Edge Impulse to convert them to grayscale before training our model. And then the last one is the resistor. When that's done, I can click Data Acquisition again, and I can see all of the different images that have been stored in my Edge Impulse project, and I should see the 5 different labels: LED, resistor, background, capacitor, and diode. If I go to test data, you should see where some of the data set was split apart. About 20% should appear in test data. That may not always be exactly the case, but this is a good mixture here. This is a fairly small data set. I highly recommend getting more samples than what I have here. But this is a good place to start just to see if we can train something. I don't expect it to be very accurate, kind of like what we saw with the dense neural network. From there, I go to Impulse Design. It's going to ask me to input the image width and height because it's going to resize the image. So for these, I want to resize them to 28 by 28. And then you can pick how the resizing is done, where it scales versus where it crops. You can squash it, you can fit. I'm just going to leave it fit because it should keep the 1-to-1 ratio when it scales from the square 96 by 96 to the 28 by 28. I'm going to add a processing block. That's going to be an image. It's going to do some very, very basic processing. And then I'm going to add a learning block. It recommends doing transfer learning, but we're not going to do that. We're going to come back to transfer learning in a later lecture because for right now, I want to show you how to use a basic neural network to accomplish this task. So for neural network, click Add, save your impulse, go to Image so that we can extract features from these images, or rather than extracting exactly features, we're going to convert them to grayscale and resize them. So rather than RGB color depth, click grayscale, and that's the only thing we have to work with right here. So save parameters, and then click generate features. This will then create our grayscale images that are now 28 by 28 each and store them in our project. That's what we're going to use to train our classifier. And remember, that's what our classifier, our model, when it's done being trained, will expect 28 by 28 pixel grayscale values as input. So keep that in mind when we go to deploy the model to our embedded device. When it's done, you should be able to look around the Feature Explorer. Keep in mind that this is not all of the dimensions. There's some special math going on the back end to kind of squish those 28 by 28 dimensions down to 3 dimensions so we get an idea of how different the images are. From this, there appears to be very good separation among the classes with the exception of diodes and resistors. These are mingled together a good bit because many of the resistors end up looking like diodes and vice versa. So I would expect the model is going to have a hard time distinguishing these unless we get more data in here and we could get better separation among the classes. But for now, this should be good enough to try a few things. Let's go to the neural network classifier. The number of training cycles, I find that for a basic two-dimensional convolutional neural network, 10 cycles is not enough. This is the number of epochs that are required to train the model. I usually go with something like 100. Learning rate is fine to leave at the default. The minimum confidence rating is something that Edge Impulse does when it's trying to test and evaluate the network, so we can leave that alone. And I'm going to go ahead and show the default network architecture. Note that you can add extra layers here. You can add more convolution and pooling layers. You can also adjust some of the hyperparameters. So I can click on this to adjust the number of filters. In the concept lecture, we showed this as having 4 filters and this as having 2 filters. And there was no dropout layer here. But a lot of these convolutional neural networks need a lot more filters than what I showed in that concept video. Because of that, we're going to leave the default of 32 filters for the first layer and 16 filters for the next layer. You can also adjust the kernel size. Kernels can be rectangular. It could be a 4 by 6 array. However, Edge Impulse only supports square kernels, so 3 means a 3 by 3 kernel for each filter. And then there's also the number of convolutional layers. You could stack convolutional layers prior to a pooling layer. And it comes with a pooling layer, which I believe is a max pooling layer. We can check that in just a second. After those 4 layers, which is convolutional pooling, there's a flatten. There's also a dropout layer, which helps with overfitting. This is where some of the connections are dropped or disconnected prior to going to the dense neural network, and this only happens during training. This has the effect of helping with overfitting, so I'm going to leave this in, but you can feel free to play with this rate. This is the percentage of connections that are dropped going to this dense neural network. There is only one layer in this dense neural network, and that is a 5-node neural network, 1 node for each of the features, and that's going to be our actual classifier. Everything up until that is our feature extraction that is trained automatically. If we go into Keras Expert mode, you can see exactly what's going on with the different layers. I was correct, it is a max pooling layer, as you can see here, and this is how you would use Keras to construct your neural network if you wanted to do this in Python. You would add a 2-dimensional convolutional layer, the number of filters, the kernel size, and the activation. You can see that they are using ReLU just like we showed, and the padding is same as opposed to valid, which means that the output array size and shape from this convolutional step should be the same as the input. After that, there's a max pooling, another 2-dimensional convolutional layer with 16 filters this time, one more max pooling, then a flatten layer, a dropout layer, and then a dense layer which has a number of nodes equal to the number of classes, which should be 5, followed by the softmax operation, which gives us the probability of each class as the output. There are some hyperparameters here if you wanted to play with those. This is the Atom Optimizer, which is a specific algorithm used to update the parameters in the model based on the difference between the expected outcome of each individual sample being fed through and its actual ground truth labels. We can control the batch size, which is the number of samples being fed to the model at a time prior to updating the parameters. And this is where the training and validation data sets are being set up so that they can be used for training and testing down in this .fit function. Let's go back to our basic view. And from there, all we have to do is click Start Training. I like to watch the training output in this window over here. As it's going, what I'm looking for is accuracy, and that is accuracy of the model on the training set, and comparing that to the validation or val accuracy. Both of these numbers should be going up. You can also look at the loss, which should be going down, but I like watching the accuracy for now. As you can see, accuracy is about 90 or over 90%, and the validation accuracy hovers around 90%. Because there is a difference between the accuracy and the validation accuracy, I can assume that there is some overfitting going on where the model is better at predicting samples in the training set than it is at predicting samples in the validation set. There are a number of ways you can address overfitting. Some of that might be playing with your network hyperparameters, which includes maybe adding layers or even removing layers, changing the number of filters, changing the number of neurons, putting in dropout layers, adding densely connected layers. You can try different architectures and configurations to see if you can reduce some of that overfitting. As you can see, our accuracy on the training set came out to be about 95%, but the accuracy on the validation set was a good bit lower. The other big thing that we can do is get more data. As I mentioned earlier, there's only 50 samples per class in this, and we should really be looking at having more than that. A few hundred samples per class at least to give us a better idea of what's going on and hopefully reduce overfitting in our model. When we looked at the Feature Explorer earlier, I noted that diodes and resistors looked very similar, and they both are actually kind of similar if you think about it from an object perspective. They're both cylindrical bodies with two leads or a lead coming out of each end, and I could see how a machine might confuse them, which means we have to figure out ways to train the machine better to look at the difference between those. And some of that might be better features where maybe we're using smaller kernel sizes to get those. These are just things to play with, but I did determine that we can use a convolutional neural network to mostly correctly identify the differences between or among these electronic components. We saw this a little bit in the concept video where I talked about quantization, where the actual weights and input features were quantized to 8-bit or 32-bit values, and then it was using integer math to compute everything inside of the network, which means you don't have to rely on floating point emulation or floating point units, which is specialized hardware in some microcontrollers and microprocessors. So that allows us to more efficiently run these networks on hardware like microcontrollers that may not have access to floating point units. This could save us some energy, this could save us some cost, a variety of reasons why you would want to do integer math instead of floating point math. But if you wanted to run the original network, you could click the float 32 unoptimized network or the unquantized version, and you can see it's about the same. So quantization doesn't lose us a whole lot of accuracy, so there's no reason not to go with the quantized version here, especially if we're going to run this on a microcontroller. Once you're happy with the results here, I'm going to call this good enough. For your purposes, I recommend playing with these. Try different numbers, try smaller kernel sizes, and see if you can get your accuracy up. I also recommend getting more data if you can, but I'm pretty happy with 90%. It's very similar to what we saw with the densely connected neural network. However, ideally, the convolutional neural network should have fewer parameters. It may have similar math or computational requirements, but it should have fewer parameters, which means it will take up less memory when we go to store this model. That may not always be the case. It depends on the number of nodes. It depends on the number of layers. There are a lot of factors that go into it, but ideally, convolutional neural networks should give a similar accuracy with fewer parameters and fewer steps to be performed. Once I'm happy with this, I can go to model testing. And I'm just going to click Classify All. This is my test set that was held out and never used for training or validation. I'm going to wait a moment while that tests all of them. And when I'm done, hopefully I get something similar to my validation set. Yes, about 90% accuracy. Once again, it's having trouble with both resistors, actual label is resistor, as well as falsely predicting other things as resistors. Now that we have a fully trained classifier, and hopefully you're happy with the accuracy and results of it, you can go to deployment and deploy it to your particular microcontroller or embedded system. There's a raw C, C++ library you could use, an Arduino library, as well as a MicroPython version for OpenMV, and even one for Linux. We'll be exploring these in a future lecture. Up until now, we've only been talking about image classification, where we want to assign a single label to the main content of an image. But what happens if we have multiple objects of interest in one image? For example, let's say we trained a classifier to identify an image as either a cat or a dog. Then I feed this to the model. Is this a picture of a cat or a dog? The model is incapable of handling two objects, so it will focus on the most salient features based on how it's been trained to make a decision. And it will classify this image, which contains both a cat and a dog, as either cat or dog, but not both. Remember the model we trained earlier to identify electronic components? I gave it these two images as test data to see what it would do. Both images contain a resistor and a capacitor. In the first image, it still successfully classified the resistor, but it was not very sure of that choice, even though the resistor was in the position it might expect to find resistors, right in the center of the frame with the leads going out to either side. When I moved the camera down slightly, the resistor was no longer in that spot. In this case, the model focused on the capacitor this time and classified the image as such. Note that it won't always be what's in the center of the image. What the model focuses on has to do with how you train the model. If the resistors were always in the top left of the frame for the training data, then it might focus there when trying to classify something as a resistor. But for this model, it happens to focus on what's near the center, as that's how all the images in the training set were structured. What we've been doing up until now is known as image classification. Image classification is where we train a model to predict the class of an entire image. This works best when there is a single lone subject of one of our classes. When you introduce multiple objects in the image, the classification methods start to break down. Image classification also can't tell you exactly where in the image the object is located, so it's best if all the objects are framed in a similar manner for all the images you're working with. However, we can use other methods to find the location of objects. This is known as object localization. Note that with localization, we don't care about the type of object that's being detected. We just want to know where some kind of object of interest is located. That's where we introduce object detection. With object detection, we want to both locate something in the frame as well as classify it. Object detection can tell us where multiple instances of an object are in an image, as well as discern among several classes of objects. Most object detection methods will attempt to both classify objects in an image and give us an idea of their location and relative size in the frame. They will do this by using what's known as a bounding box. A bounding box is a set of coordinates in the image that could be an x, y, width and height, or the location of two opposite corners. The idea is that you could use this information to draw an overlay on the original image to get an idea where those objects are located in the frame. Along with the bounding box, you should also get a predicted class and confidence level of that class. For example, a well-trained object detection model might give us a bounding box for the cat with a predicted confidence of 98%, as well as a bounding box for the dog with a predicted confidence of the dog class of 83%. With a little bit of math, you can find the center of these bounding boxes, which should give you an idea where the middle of the object is. This is great if you, say, want to have a self-driving car avoid these objects, or maybe want to have a pan-tilt camera automatically follow them by moving so that the center of the frame lines up with the center of one of the objects. One easy way to do object detection is to do a simple sliding window with inference performed for each window. Let's say I'm trying to determine the location of my dog in this frame. This works best if the window is the same size as your training set resolution. We then feed whatever is under this window to our image classification model, and it performs inference to give us a prediction. Here, it might predict background as the class. Then we slide the window over and send the new set of pixels under the window to the model. Note that I have a little bit of overlap between the two windows. You can adjust the amount of overlap by setting a stride value, usually measured in number of pixels. If your stride is larger than your window width, you won't have any overlap. If it's less, you'll have some overlap. Note that more overlap means a better chance of detecting your object, but it means that you'll need to perform more inferences per still image, which could really slow down your frame rate. We continue this process until the window highlights my dog. Here, the model should predict dog as the class. From here, we could draw a bounding box the size of the window to denote that a dog was detected. However, let's say that we keep sliding the window and marking the locations of dog detections. We might end up with something like this. There were 3 true positives that detected areas of my dog, 1 false positive as the model thought my hanging cables were a dog, and 1 false negative where my dog's back legs were missed. This might be good enough for your project, as you can still successfully see that a dog was present in the image. Knowing that the cables caused a false positive hit, we might go back with extra training data to get a better model. Let's say we do that and end up with something like this. We still see 3 instances of the dog class. However, with some math, we can determine that bounding boxes of the same class are overlapping and assume that it must be one large object. We can then find the extents of these bounding boxes to create a larger, more inclusive bounding box. You could average the individual classifications together to get some kind of total confidence score for the detected object. However, this might not work if you had multiple instances of dog next to each other. Note that this method might think overlapping objects are a single object. As you can see, this is a basic approach to doing object detection, but it has a lot of problems. We'll examine more advanced techniques for handling overlapping objects later. Something else you can do is resize the image under the window to the expected resolution of the model's input. For example, maybe we take a bigger section that's 96 by 96 and resize it to 48 by 48 before performing inference. This would keep inference fast, and we could scan larger sections of the image. It also might allow us to look for dog objects that are closer to the camera. However, it might miss dog objects that are farther away, as the model was not trained on images with this scale. While it might allow us to highlight the dog without computing the extents of several bounding boxes, we run the risk of missing the dog altogether if the stride is too high, the dog is too far away, or if the model is not picking out the correct features due to the resizing operation. Even with a small overlap as shown here, we'd still need to perform 48 inferences per still image. And I'd still need to drop the right and bottom edges without doing some sort of padding or less than normal stride amount for the final windows along the edges. Let's say we have a fairly small model that can perform inference in 100 milliseconds, and we don't need to resize our windows. We would still need to spend around 4.8 seconds per image to locate our object. That would give us about 0.208 frames per second if we wanted to do this on a live video feed. Your project might be fine with such a low frame rate, such as if you just needed to check for the presence of a person or animal every minute or so. However, this assumes that we can find what we're looking for in the frame using a square bounding box. Let's say we're working on a self-driving car that needs to watch for pedestrians and other cars. These square search boxes would only be capable of covering a portion of the object in question. Even if the classifier identified the piece as belonging to a person or car, we'd still have to combine them in some way to denote something as just one object rather than several. That can be a tricky problem. One option is to scan the image with a variety of window sizes ranging from small to large. While this might help spot single instances better, you run into 2 issues. It's hard to determine the exact location of tall or flat objects. For example, is the identified person in the middle, left, or right of the bounding box shown? You would not be able to tell if you just got the coordinates and size of the bounding box. It also means many more inferences need to be performed to scan the image with different window sizes. Taking this a step further, what if we scanned the image with a variety of bounding box shapes and sizes? I've removed the potential boxes for the car as it only cluttered the image. Here, each location, or every few pixels, could be scanned with 6 or more differently shaped windows. The area under the window could be resized and skewed as necessary to match the input dimensions of the convolutional neural network. The network would be trained to know how to work with scaled images like this. From here, we could select the bounding box with the highest score for that object. Ideally, we would end up with something like this to predict the location of our pedestrian. However, as you probably guessed, this is incredibly time-intensive for both training and inference. Instead of sliding many windows over the same image, forcing us to perform inference hundreds or even thousands of times, what if we used another algorithm to propose possible windows for us? This might be a clustering algorithm that groups similar pixels together, or even another convolutional neural network that picks out what it thinks are interesting areas in the input image. Note that they may or may not contain objects. They're just proposed windows that contain something interesting. We then send these windows to our convolutional neural network for classification. This process of identifying potential regions of interest is known as region proposal. Using a convolutional neural network to perform region proposal is known as a region proposal network. These areas are known as regions of interest. Hopefully, our classifier, which we trained to identify vehicles and people, would be able to correctly identify the cars and pedestrians in this image. We'd combine or pick the best window for our bounding boxes and end up with something like this. This saves us a lot of time over the sliding window method to identify objects in an image. Region proposal as a way to feed an image classifier forms the basis for the region-based convolutional neural network model, which we'll look at in a future lecture. Even though object detection methods may have many different parts, we can treat them as a single machine learning model. You can often train some or all of its parts during the training step. The ultimate goal of these object detection models is to locate and classify all of the objects of interest in the photo. For example, let's say I trained this model to identify my dog, his tug toy, and his ball. The output of such a model will often look something like this. You'll get a list of 0 or more objects where each object contains the predicted label and information about the bounding box. If you're working with Python, this might be a list of Python objects you'll have to loop through, or it could be something like a JSON string. The XY location might be the center of the box, or it could be the top left. You'll have to read the documentation for whichever model you're using to determine that. The class prediction will likely come with a probability score from the softmax output. With this information, we can then draw the predicted boxes on the image. We could also use the X and Y information to perform some task, like shine a laser for a cat to play with, or move a camera on a servo to face a particular object. The width and height of the bounding box might also provide some insights into how close an object is to the camera, assuming we have some information about the size of that object. There are a number of popular models that perform object detection like this. These models can be very complicated, and so the inner working details of them are outside the scope of this course. However, in a future lecture, we'll briefly go over a few of the models and demonstrate how to use one of them in Edge Impulse. I will also make sure to list some articles in the recommended reading sections if you'd like to dig more into these concepts and models. Before we look at any object detection models, let's take a moment to go over some performance metrics. You'll want to have a basic understanding of these metrics in order to evaluate the different models that are out there. In the first course, we introduced the concept of a confusion matrix and how we can use it to calculate a number of metrics. The confusion matrix is usually filled out with predicted and actual label counts from the validation or test set. Here, let's say that I'm only looking at the metrics for the dog class, as I'm evaluating a model that tries to detect any dog, ball, or tug toy items in an image. If you recall from that first course, we can calculate the precision score for one class by dividing the number of true positives by the sum of the true positives and false positives. With that, we're trying to get a measure of the percentage of positive predictions that was actually correct. Another popular metric is recall, where we calculate the proportion of actual positives that was identified correctly. To get that, we divide the number of true positives by the sum of the true positives and false negatives. Something else we covered in that first course was the idea of setting a threshold for the output confidence score of a particular class in order to label the class positively or negatively. You often find a threshold of 0.5 to start. For example, if our model gives us a confidence score of 0.5 or higher for the dog class, then we would assign the label dog to that item, which would be a single region of interest taken from a larger image. In many machine learning systems, you won't often find a clean divide between the different labels, and you'll end up with some false positives and false negatives regardless of what threshold you choose. With this threshold, we can calculate the precision and recall values using the given number of true positive, and false negative results. We can then plot that point on a graph of recall versus precision. As you move the threshold up, you generally expect the number of true positives to decrease as well as the number of false positives. However, this also means you gain more false negatives. We can then calculate a new set of precision and recall values with this threshold. With a smaller set of false positives, you generally expect precision to be really good, but your recall will be terrible as you have a lot of false negatives. That might give us something like this on the precision recall plot. As you lower the threshold, you generally expect the number of true positives to increase while decreasing the number of false negatives. However, it also means you see more false positives. From this, we expect the precision to be low but the recall to be high, so we might end up with a point like this on the curve. We would continue sliding the threshold around between 0 and 1 and calculating the various precision and recall scores. We plot all of them on a precision recall curve and we might get something like this. Note that this is not the same as the receiver operating characteristic curve that we saw in the first course, as that plot uses true positive rate and false positive rate instead of precision and recall. After plotting all of the precision and recall points, we would end up with a curve like this. From here, we can calculate the average precision for our dog class. The formal definition of average precision is the area under our precision recall curve, which requires computing the integral of the plot. This would give us a number between 0 and 1, and the closer to 1, the better the model is at predicting the dog class with few false positives and few false negatives. However, because this line was measured, it's likely impossible or nearly impossible to get a good mathematical equation to describe it, and even more unlikely that you'd be able to compute the integral. As a result, a few papers describe methods to sample points along the curve and compute the average to get an approximation of the average precision. One popular method is detailed in the Pascal Visual Object Classes Challenge paper published in 2009. Here, 11 precision values are sampled that are taken from equally spaced points along the recall axis. These precision scores are added together and divided by 11 to give us an approximation of the average precision score. Once again, this is a number between 0 and 1, where 1 indicates a model with perfect or near perfect classification. You might see other ways used to approximate the average precision score, but this 11-point method seems to be one of the most popular. Remember that this is only for our dog class. We would need to compute the average precision scores for the other classes as well if we're trying to judge the total effectiveness of the model. We'll go over a way to combine those scores, but let's talk about how this works with object detection first, as we've only been talking about classification problems so far. When creating your training, validation, and test datasets, you will need to hand draw bounding boxes and label each of the associated objects. Let's say that this is one such example in my test set, and I've drawn the bounding boxes shown here. bounding box information is usually not stored in the image itself. Rather, you'll often find a separate file that contains information about the bounding boxes. There could be one text file per image or one large file that associates image files with their respective bounding boxes and object labels. We run this image without the ground truth bounding box information through our object detection model, and the model gives us these boxes and labels as predictions. An object detector's classifier will have a non-object class that it is capable of predicting, which I'll call background. You will generally not get background class predictions as output from the model, as this would be every region of interest that was not classified as containing one of our desired labels, and, as a result, would have a large imbalance in labels favoring the background class, which might influence our recall and precision scores. Rather, we can check label accuracy by comparing the predicted classes to the ones noted in the ground truth bounding boxes. That provides us with a simple accuracy score, much like we've seen for other classification problems, and we don't need to take the background class into account. For example, as the ball object was not detected, that would be a false negative. The toy box is obviously not covering enough of the toy object. Measuring how closely the predicted bounding boxes match our ground truth boxes requires a little math. One popular way to measure the success of bounding box predictions is to use the intersection over union, or IOU formula. The intersection is a measure of the area that the predicted bounding box overlaps with the ground truth box. This could be the number of pixels, width and height in inches, and so on. The area doesn't have to be rectangular if you're working with a non-standard bounding box shape. The union is the area under both boxes if you combine them into one shape. You compute the IOU by dividing the area of the overlap by the total area of the union. This is a ratio and gives you a score between 0 and 1. 0 means that there is no overlap and that the predicted box isn't touching any area of the ground truth box. 1 means that the predicted box perfectly overlaps the ground truth box. From here, you can set a threshold as to whether you count the predicted box as being good enough to detect the intended object. A common IOU threshold for models is 0.5, but you may also see 0.7 sometimes. So an object is considered detected if there is an IOU score at or above 0.5 when comparing the predicted bounding box to the ground truth bounding box. Trying to get an IOU score of 1 for every predicted bounding box in an image is a goal of many object detection models, and may even be used as a loss function during training for some models. Let's go back to our image example. Here, the detected dog object might have an IOU of something like 0.9. If we set the IOU threshold to 0.5, this would be considered a true positive detection and classification. However, let's say our toy box has an IOU of only 0.2. As a result, this prediction would be considered a false positive. Because the ball object was not detected at all, but there was a ground truth label for it, this would be a false negative. True negatives are all the parts of the image where we detected no objects and there were no ground truth objects listed. Because there are a lot of true negatives in most object detection systems, we generally ignore this metric while focusing on precision and recall. Let's go back to our precision recall curve. We would only count a detection as a true positive if the IOU value between that prediction and the ground truth label was at or over 0.5. Because this IOU threshold would affect our precision and recall values, we can keep it constant for now. Remember that this is a plot from the perspective of just one of our classes. We would need to generate precision recall curves for all the other classes that our model is capable of identifying. In this case, we would create a precision recall curve for the ball as well as for the tug toy, and they might look something like this. From there, we can introduce the concept of the mean average precision score, or MAP. All we need to do is calculate the average precision scores for each of the classes and then average them together. Note once again that this is still assuming our IOU threshold is 0.5. Using a single IOU threshold might give you a good enough MAP score. The Pascal VOC 2007 challenge used an MAP value with a single IOU threshold of 0.5 for its scoring system. Often you will see MAP scores reported with a single IOU threshold of 0.5 like this. Let's go back to looking at the precision recall curve of just the dog class for a moment. If we vary the IOU threshold, then we would expect the curve to change. Generally, as you increase the IOU threshold, the model has to be more precise in its bounding box location to be counted as a true positive. As a result, you would expect the average precision, or the area under the curve, to decrease. You might end up with something like this for the dog class. The COCO 2017 challenge introduced a new scoring metric where the mean average precision was now an average of all the mean average precision values over 10 different IOU thresholds, ranging from 0.5 to 0.95. In other words, all average precision scores from all classes and a set of IOU thresholds were averaged together. This method rewarded models that were better at precise localization of the objects in the images. However, you'll still often find that many MAP scores assume an IOU threshold of 0.5, as shown in the top equation. I hope that this has helped you get an understanding of how the mean average precision is calculated, as it's one of the most popular scoring methods used when comparing object detection models. Previously, we looked at a brute force method of locating objects in an image by sliding a window across the image and then performing inference on each of the sub-images underneath that window. Now, let's look at a few models that attempt to do all of that much more quickly and efficiently. We saw that instead of sliding differently shaped windows across an image, we could use some other algorithm to propose various regions of interest in that image. This forms the basis for the region-based convolutional neural network, or RCNN, first proposed by UC Berkeley researchers in 2014. Here is the original RCNN paper. I'll make sure to include a link to it in the recommended reading section if you'd like to dig into it, but it can be fairly complex. The first figure does a great job at explaining how the proposed RCNN model works. It combines several methods to produce this object detection structure. It first proposes around 2,000 regions of interest in an image. These regions are warped or scaled to match the expected input of the convolutional neural network, and then inference is performed on all of these proposed regions. The region proposal method is not specified in the paper, but they offer several ideas on what you might use, such as selective search or constrained parametric min-cuts. We won't get into these methods, but know that RCNN was a very important breakthrough in solving object detection problems. The other interesting part of RCNN was the use of a regression model to better predict bounding boxes. It would learn how much to vary the XY coordinates and width and height measurements of the box based on the supplied proposed region and ground truth labels. My dog enjoys playing tug and fetch, and he will sometimes bring me either his toy or ball, depending on which one he wants to play with. Let's say I want to train a model that identifies my dog, his tug toy, and his favorite fetch ball. This is a slightly silly way to test object detection, but it's a fun way to see how well I can pick out 3 different objects on an embedded system. Note that going forward, and at least for the time being, you will need to use color images. Many of the popular object detection models rely on color information to help determine regions of interest or to make object classifications. You can technically use grayscale images, but you'll need to find a way to copy the grayscale array to each red, green, and blue arrays. A more useful application might be something like this. Edge Impulse has been working with researchers to track elephant movements in the wild. Part of this also includes watching for poachers to help protect the animals. Cameras could be set up and alert authorities whenever an elephant and human are in close proximity. Embedded object detection would allow us to do this. You could also set something up to notify you if there's a person too close to a package on your porch. This might alert you of a new delivery or a possible theft. But back to our RCNN example. Here is the basic structure of the model. A region proposal algorithm finds around 2,000 sub-image portions that are fed to a convolutional neural network. Note that the CNN used here is just for feature extraction. In the original RCNN paper, the features are fed to a support vector machine, or SVM, instead of a densely connected neural network for classification. The output of this part of the model is a prediction of the class of that particular region of interest. Note that the region could contain just background, so an extra class is added to denote that the region does not contain one of our desired classes. The location information of the regions along with the feature maps and class predictions are fed to a regression model that tells us how we should update the location and shape of the bounding boxes. dx and dy give us how far horizontally and vertically we need to move the bounding box. dw and dh are how much we should adjust the bounding box's width and height from the original region of interest proposal. This information should ideally give us a much better idea of where to draw the bounding box rather than relying solely on the original region of interest location. The biggest problem with this architecture is that once you've identified all possible regions of interest, you still need to perform feature extraction and classification on each region. This could mean up to 2,000 runs of the right side of the model shown here. In 2015, a Microsoft researcher proposed a modified version of RCNN called Fast RCNN. Here, the features were extracted separately using a convolutional neural network. This would create a feature map like we've seen previously. Region proposal would still be done on the same input image using a method like selective search. However, the region information is used to extract sections of the feature map rather than the original image. A method called region of interest pooling takes this information, combines features as necessary, and generates smaller feature maps with all the same size. These new feature sets are passed through a few fully connected or dense neural network layers and then flattened to create one-dimensional vectors. This information is sent to two different dense neural networks. The first provides the classification of the pooled feature subsection, and the second performs regression to provide a better location and shape of the bounding box. The information we get out of this model is the same as RCNN, but it's much faster, as we no longer need to compute new feature maps with convolutional layers for each proposed region. A year later, researchers proposed the faster RCNN model. Instead of performing region proposal on the input image, the model does region proposal on the feature map instead. They introduced the concept of a region proposal network, which is a neural network that can output a series of boxes containing regions of interest along with their objectness score. This score is an indication of how much the network believes there is an object in the proposed region. These regions are used by the ROI pooling layer to create a series of feature maps with the same size, just like before. The rest of the model works just like fast RCNN to output object classifications and bounding box locations. Note that the convolutional neural network that acts as a feature extractor could be the feature extractor portion from another popular classifier architecture like VGG19 or MobileNet. We can even use pre-trained weights from those networks to allow us to do transfer learning on the rest of the model. The big issue is that even though this architecture is faster by doing region proposals on the feature map instead of the images, we still need to perform full classification on each proposed region. In 2016, the same year that faster RCNN was proposed, a different group of researchers put forth a new type of architecture that didn't rely on region proposals or multiple classification steps on those regions. In essence, they used the location information embedded in varying sized feature maps to locate objects in the input image. They called this approach the single-shot multi-box detector, or SSD for short. A known good convolutional neural network like VGG19 or MobileNet would be the feature extractor for this model. Like with faster RCNN, you would need to drop the classifier portion of the network and just keep the convolutional layers, which ultimately produce a series of feature maps with the most salient features highlighted. This feature extractor would form what's known as the backbone of the model. More convolution layers follow this backbone that continue to reduce the size of the output feature map. Each of these feature maps works as a sort of localization grid. Each cell is used as a center point for multiple anchor boxes with different aspect ratios that are used to match with objects in the feature map. As the feature maps get smaller, the grid cells and corresponding anchor boxes increase in size relative to the input image. This helps the model identify objects of varying shapes and sizes in the frame. Each output series of feature maps from the convolution layers shown in blue along with the feature maps generated by the backbone CNN are fed to convolutional classifiers known as heads shown in green on the right side. These heads produce a series of classifications for each of the default anchor boxes. Each head also contains a regression model used to update the x, y coordinates and width and height of the default anchor box to create a bounding box. All these predictions go through a non-maximum suppression step, which we'll talk about in a second. The output is a list of bounding box objects along with their associated class predictions. Without the region proposal step used in the previous models, the SSD loses some of its accuracy. However, the SSD architecture is extremely fast as it can produce a series of object predictions with a single forward pass, which is where it gets the name single shot. SSDs are well suited for mobile and embedded applications because of their speed and computational efficiency, even if it means they're not quite as accurate. Because SSD outputs many different classifications in a single pass, we need a way to deal with potential overlapping bounding boxes. That's where non-maximum suppression comes in. Let's say we have a series of bounding boxes for the dog label like this. Any classifications below a threshold have already been filtered out. So we're only dealing with boxes that have over, say, a 0.5 confidence score. Even then, we still have several boxes that overlap on the same object. To start, we select the predicted bounding box with the highest confidence score, which is 0.92 in this example. We then calculate the intersection over union score for each box that intersects with the highest confidence box. Finally, any box with an IOU score over some threshold is removed. You'll often find an IOU threshold of around 0.6 for non-max suppression. What we're left with should be the best bounding box for the object in question. This is repeated for all classes and all non-intersecting boxes of the same class. The idea is that we should ultimately get an output of bounding boxes and confidence scores that uniquely identify the various objects in the input image. The hope is that objects can be of any shape or size and any distance from the camera. However, SSD struggles with very small objects in the frame as there are simply not enough pixels to sufficiently describe that object. Also, default anchor boxes may not be small enough to catch some objects. The only way to deal with that right now is to increase the size of the input image and retrain your model to work with higher resolution images. Also note that many of these object detection models rely on pre-trained backbone networks like MobileNet. These networks were trained on a known good image set like ImageNet or Coco. However, if you're trying to identify objects that were not represented in the dataset used for pre-training, you might run into problems as the convolutional filters were never trained to look for your particular custom object. For example, I don't think my specific dog tug toy is in the dataset, so I expect an SSD model pre-trained on ImageNet or Coco to struggle finding this object if I only rely on transfer learning. The ball might also prove difficult as it's rather small with such a low resolution. Here is a pre-trained SSD model with a MobileNet version 1 backbone. The MobileNet feature extractor can be seen at the top of the model in Netron. You can see where the output of this series of convolution layers goes to a pair of convolution heads that give us a set of object classifications and bounding box locations. The SSD convolution layers also feed into similar pairs of convolution heads that give the same kind of object detection predictions. All of these predictions are fed into a post-processing step that performs non-maximum suppression and combines the predictions into a list of object labels and box locations. The following paper from 2017 gives an overview of various object detection models at the time. Figure 2 gives a great depiction of how well the various detectors performed using mean average precision as the scoring system. We looked at faster RCNN and SSD, and you can see various versions of those detectors with different feature extractor backbones. SSD with a MobileNet version 1 backbone is not very accurate compared to some of the others, but it's one of the fastest, which makes it popular for embedded systems. There are other models out there that we didn't cover, like RFCN, which stands for Region-Based Fully Connected Network. Note that the models here were trained on the COCO image dataset with non-maximum suppression IOU threshold set to 0.6. The mean average precision score is taken as an average over IOU thresholds ranging from 0.5 to 0.95. We can make improvements to SSD by using more advanced backbones like MobileNet version 2. Additionally, we can introduce other concepts like feature pyramid network or FPN. The blue squares in these images are the feature maps that are generated from one or more convolutional layers. The top left shows how we can resize images, run them through a series of convolutional filters, and then use those feature maps to make predictions about the contents of the images. We see something similar with B in the top right. However, here we use convolutional layers that reduce the dimensions of each subsequent feature map, and we only make our predictions with that final layer. This is how our traditional convolutional neural network classifier works. We can combine this with a region proposal system to get an object detector, just like we saw with RCNN. Next, we have the pyramidal feature hierarchy, which predicts features based on all of the intermediate feature maps. This is how our SSD model works. The paper proposes the image given by D, which is the feature pyramid network. In this, a new series of convolutional layers are introduced that actually upsample the smaller feature maps. Feature maps from the first set of layers are combined with the upsampled feature maps before being sent to the classifier heads. This has the effect of expanding salient features from the filtered feature maps into higher resolution maps with the intent of raising average precision and small object detection. Here is a look at a single-shot detector I trained to look for instances of dog, ball, and tug toy. The top part is the MobileNet version 2 backbone, which contains a series of residual blocks. Some of the feature maps from these residual networks are copied to sections below, which make up the feature pyramid network. Here you can see that 10 by 10 maps from this convolution layer are then continuously upsampled using more convolution. Feature maps from earlier in the network are added to these upsampled feature maps, which go all the way up to 40 by 40. These combined feature maps are sent to prediction heads, and the smaller feature maps are also sent to prediction heads. The output of these heads are combined to give us a list of detected objects and their bounding boxes after a round of non-maximum suppression. YOLO, or You Only Look Once, is another popular model that we didn't cover. This paper from 2020 covers version 4 of the YOLO model and introduces some advanced techniques that make it faster and more accurate. At the bottom of the paper, you can see a chart comparing YOLO to other models, including SSD. You can see how it compares to SSD and other object detection models. Note that the size and speed of the model will depend on the backbone used, as well as other features and layers in the model. Both SSD and YOLO are popular for their small size and speed, and they are getting more accurate with each revision. Don't worry if much of this seems really confusing. This was supposed to be a very broad overview of the last few years of research into object detection models, and I left out a few concepts that go into creating these models. If you'd like to dig deeper into them, I'll make sure to link a few articles and original papers in the recommended reading section. Now that we've briefly seen how object detection models work, let's train our own in Edge Impulse. Object detection models take up a lot more space and require a lot more computation power than simple image classification networks. As a result, you need a more powerful board when you go to deploy the model. I recommend the Raspberry Pi 4 with the Pi camera for the project in this module. TensorFlow Lite for microcontrollers does not support some of the operations required at the time this course was released. So, while the OpenMV H7 Plus might have enough memory and processing power to run an object detection model, it simply won't work for this project right now. If and when support for object detection models is added to OpenMV, I will update the materials in the course to include it. To collect a dataset, you'll want to capture a bunch of images that contain the objects you are trying to look for. You'll also want to have them in PNG format, as that's what Edge Impulse works with. In this case, I am trying to train an object detector that looks for my dog, his tug toy, or a ball, as you can see in this image. The idea is that every now and then my dog brings me one of these toys, whether it's a ball or the tug toy that's the little red figure 8, to me when he wants to play, and I want to train a detector that lets me know that the dog is near one of these toys and possibly wants to play. I don't know how ultimately useful this is, but feel free to train your own detector for things like people, other animals, cars, fruits, other foods, or maybe road signs if you're trying to make something like a self-driving car. Notice that these images are full color. The object detection model that we're going to be using expects full color models, not grayscale. So don't try to save on space by converting all your images to grayscale. They need to be 320 by 320 pixels, as that's what the model expects. You can have Edge Impulse crop or resize your images, but I like to capture things in the exact format that's expected by the model. So everything I've collected is 320 by 320, and I have a variety of different rooms, backgrounds, lighting, angles, the dog's in different positions, the toys and the ball are in different positions. These help to train the model to look for the objects in various positions and lighting conditions. I also try to include a variety of things like just the toy by itself, the toy and the dog by itself, or maybe all three in the frame, which you can see in this image here. You'll want to have about 50 instances of each object. That doesn't mean you'll have a total of 150 images if you have 3 classes, but spread across these images, you'll want to have about 50 samples of those objects. If you have 50 images and each of those images contain your 3 objects, then you only need 50 images. If you're working with the OpenMV, I recommend using the image capture script I gave you earlier in the course. Here, you'll want to keep it as RGB565, which is color rather than grayscale, and you'll want to change the width of the frame and height of the frame to 320 by 320. Additionally, you need to adjust the frame size, as QVGA captures things in 320 by 240, and so we're just going to set this to VGA, and then we're going to crop down to 320 by 320. When you run this, you should see a color image show up in your viewfinder, and after about 3 seconds, it will capture an image and store it on the SD card of your OpenMV. From there, just take out all of your images and store them somewhere on your computer so that you can upload them to Edge Impulse. Note that if you're capturing from OpenMV, everything's probably going to be in BMP format, so you'll want to convert it to PNG. Finally, if you're doing things with the Raspberry Pi, I recommend running the PyCam capture script. Here, you'll want to change the image width to 320 and the image height to 320. From there, just run this script on your Raspberry Pi and it should capture color images in 320 by 320 resolution. Then just copy those images from your Pi, make sure they contain the objects you intend to look for, and we're going to upload those to Edge Impulse. Head to Edge Impulse, log into your account, and let's create a new project. I'm going to call this one Ball Dog Toy Detection. Feel free to be a little more creative than me in your naming schemes, but this at least lets me know what kind of things I'm looking for. From here, I'm going to exit out of the pop-up screen. On your dashboard, you're going to need to scroll down and head to Project Info. There, look for Labeling Method, and we're going to change this to bounding boxes, as that's going to change how we label our items. Note that we're going to be labeling or providing ground truth bounding boxes in Edge Impulse rather than using a third-party program or trying to do it manually by creating a file with a bunch of labels and bounding box information. From here, head to Data Acquisition, and then click to upload your files. You're going to want to leave it as automatically split between training and testing and infer the label from the file name. This does not really apply since we're going to be making bounding boxes on each of the images. Select Choose Files, and find where you've created your data set. Highlight all of your images. I do recommend going through these to make sure that your objects are clearly visible. As soon as an object moves out of the frame, it might make it a little harder to detect unless that's something you're looking for where you're okay detecting part of an object in the image. Let's upload these. We'll click to begin upload and wait just a second while it uploads all of the images. From there, head back into data acquisition, and you should see a new tab that's appeared called Labeling Queue. Click on that, and you can start labeling your objects. All you'll do is click and drag to create a bounding box, and you'll enter a label. Here I've got dog, and I can move the bounding box around. You'll want to make sure that it barely captures your object in its entirety without leaving too much extra space around it. And I'm going to move it over, and then I'm going to draw another bounding box for my next object, which I will label as toy. Here I'm going to move the bounding box again so it's just capturing the object, and I'm going to adjust its size, and I'm going to click Save Labels. In the next screen, I'm going to do the same thing. I'm going to find where my objects are, and I'm going to move my bounding boxes around. I'm going to do the same thing with dog. Resize that one, click Save Labels, and continue. You'll want to keep doing this for all of your images and for all of the objects in your images. This might take some time, so be patient as you go through it. When you're done, I recommend going back into training data, and you can look through all of your images here. You can see the labels that are associated with the objects in those images, and you can see the number of labels for objects in those images up in the right corner here. You can also do the same with your test data. If you made a mistake and you need to relabel something, you can click on the drop-down menu on that image and select Edit Labels. This will bring you to a new screen where you can move the labels around, add new labels, change the label names, and so on. I don't need to update this, so I'm just going to X out of that. You can also get a preview of where all the labels are on your objects, so I recommend taking a look at those to make sure they're good. If you missed any, go back and redo them. When we're done, head to Impulse Design. Take a note of the text here. For object detection, at least for right now, we must use input image sizes of 320 by 320, so I'm going to leave this to be the default. If you don't have it already, you'll want to add an image processing block, and you may not have anything here, so you'll want to add object detection images. Save your impulse, and then head over to your feature extraction tab. We want to keep the color depth at RGB because the object detection model expects color images. It will not work with grayscale, at least at this time. Save these parameters, and then click Generate Features. This should not do a whole lot other than maybe tagging the images and creating a file or something that contains all of the bounding box information. It additionally compresses the dimensions of the various objects found in the images so we can see them in the Feature Explorer here. You should see some decent separation among the object classes. However, I don't see a whole lot between the toy and the ball, which means I'm not sure that this model is going to work very well, but we will see. From there, head to your Object Detection tab. I like to increase the number of cycles. I find that 25 is a little low to work with. Something in the 50 to 100 range works pretty well for me. I'm going to leave the learning rate and the score threshold alone for now. I don't have many options at this moment. There's only one model that Edge Impulse supports at this time for object detection, and that is a single-shot multi-box detection, or SSD, architecture with a MobileNet version 2 backbone used for feature extraction. It also contains a feature pyramid network, and that's all converted to a TensorFlow Lite model when it's done being trained. In this case, we are using transfer learning, so it should train a lot faster in a matter of minutes rather than hours or even days. Do note that Edge Impulse says it's able to locate up to 10 objects with an image, so there is a limit to the number of objects it can detect, at least on this version of the model. We are going to go ahead and use that model, and let's begin our training. So just click Start Training. In a previous lecture, I talked about how the backbone for this SSD model can be pre-trained on a known good set of images. In this case, the MobileNet v2 backbone is trained on the Coco set of images. If this set does not contain some of the things that I'm looking for, like maybe the tug toy is not in that training set, the filter parameters may have a hard time picking it out, whereas dog is likely one of the images in that training set, so the filter parameters kind of know what to look for, and there's a lot of complexity that goes into animals. They have repeating patterns like fur, they have legs, they've got faces, ears, eyes, nose, mouth, maybe a tail. There are things that the parameters can look for to help determine that that is a particular animal, like dog. So I expect this model is going to pick out my dog a lot more easily than it does, say, the tug toy. The ball is an interesting one. Simply because the ball is a very simple shape, I would figure that some of the simple lines that go into creating the ball, at least when it comes to creating an image of a ball, should be pretty simple and straightforward. However, it's a weird color, which I'm not sure matters in this case, but the idea of a basic circle might be actually tough for something that's looking for more complex features. We'll see when this is done. The other thing that concerns me is that at least for 320 by 320 resolution photos, the ball is relatively small. I think it's on the order of 10 by 10 or maybe 20 by 20 pixels, which going into the network is going to be a relatively low number of features coming out on the other side of all those convolution filters. However, that feature pyramid network, that FPN portion of the SSD, should allow the network to work with smaller objects. We'll see if it works for the ball object in this case. With training done, we can look at the model's performance. Here you can see that it scores about a 73.1% with the validation set, and that's with the 8-bit quantized model. We can also look at the float32, but you'll notice that it takes a little more flash. In this case, the precision goes up to about 85%. Generally, when working with a lot of these embedded systems, you'll want to use the quantized model where possible. The other thing that I recommend doing is going to Model Testing, and then clicking Classify All. Wait for just a moment while it tries to detect all of the objects in the test dataset. As you can see, it's only performing at about a 67%, which is not great. I recommend taking a look through your test dataset to see where the model is failing. In this case, it's looking like it's failing on ball and toy. We can select Show Classification, and I'm going to do that for a number of these images where it failed to label one of the objects. So let's open these up. Once you have them open, you can see where the ground truth labels occur. In this case, it looks like the model tried to classify the ball with an 83% confidence. However, it completely missed the toy, and that's likely because the toy was shown on its side here. And if we keep looking at the images, it missed the ball when the ball was next to the dog. Once again, it missed the ball when the ball was next to the dog. It did successfully classify the toy object here. It's looking like the ball is not classified whenever the ball is next to my dog's light-colored fur. And that could just be because the feature extractor isn't seeing any edges, or it's considering it to be part of the dog. I'm not exactly sure what's going on, but this does appear to be a common problem. And here, it just completely misses the toy, even though the toy is in plain view. It misses the toy, but the ball was found. The ball wasn't near his light-colored fur, but it was on this light-colored piece of rug. But it did miss the toy. That's interesting. Once again, it missed the toy, and this might be too small of an object because it's so far away. It looks like the model is struggling to find the toy, and once again, the toy is missed, but it did double classify the dog, which is not great. It looks like the non-maximum suppression failed here as it considered this 0.54 object to be the dog, even though that is not correct. From what I could tell, it struggles with the toy object, and it struggles sometimes when the ball is next to light-colored objects like my dog's fur. The toy object I'm not particularly surprised about, simply because I don't think it's something that was in the original training set. So I'm asking the model to try to identify the toy using filters that weren't trained on something that looks like this toy. That is something important I recommend keeping in mind, that you should probably stick to objects that were part of that original training set and using those as a starting point for what kind of objects you should be looking for. You can get away with training new objects that aren't in those original classifications, but the model might struggle to find those. When you're happy with the results, and in this case, I could probably go back and train a bunch of images with the ball next to my dog in various positions in order to try to get the object detection to find the ball in those cases. And an option for the toy might be I have to use a different toy, one that looks like an object that was part of the original training set classification scheme, or I might have to train that backbone from scratch, which At this time, Edge Impulse does not support, so that would be a little more involved. When you're done, head down to Deployment, and you can download a library containing all of the feature extraction and model information ready to be deployed to your system of choice. And in this case, remember that object detection takes a lot more RAM and flash memory, so you will want to use a very powerful microcontroller or something like a single board computer.